My name is Manfred Breu. I was for a long time a professor for software and systems engineering at the Faculty of Informatics at the Technical University of Munich. At that time, I was basically doing research on systems engineering around a number of topics which are also very interesting for avionic applications. Today, I'm the president of the Center of Digitization here in Bavaria, and our goal is to make sure that these digital technologies, which are very rapidly developing, will be used in a number of applications. We organize our work in a number of so-called theme platforms. One theme platform there is a platform on mobility. This platform looks at all different kinds of mobility and tries to understand how digital technology can support questions of mobility. And here we are close to a field which is also part of our mobility platform, but is a field on its own. The application of digital technology in the field of avionics. In principle, the step into systems engineering in avionics was done during the Second World War for a number of reasons. One of the reasons was the upcoming radar technology, which really changed a lot the way military aircrafts were doing their duties and tasks in the Second World War. After that, in the 60s and 70s, we had a development of jet fighters, and jet fighters needed a lot of support according to digital technologies. They used what we call embedded systems, which in the 60s were also filled up with a lot of software. And therefore it's interesting to study how the field of avionics developed under this technology pressure which came from the digital technology. One of the first very interesting points was the introduction of fly-by-wire. Fly-by-wire means that a pilot no longer operates his aircraft directly, but operates his aircraft by giving input to a computer, where the input is done also by joysticks, so that the pilot may have the idea that he directly controls the aircraft, but in the end he only controls the input to a computer, and the computer activates actuators which in the end make sure that the aircraft operates the way the pilot wants this. This was interesting in particular for aircraft fighters like the Eurofighter, who is an aircraft that cannot be operated manually without the help of a computer according to its particular styles of operating. Later, this idea was taken over also for civil aircrafts. And as a first large aircraft producer, Airbus decided to introduce fly-by-wire into its aircrafts. The result was that the fact that in the days before there were 3 persons in a cockpit, 2 pilots and an engineer, ended up with a situation where there were only 2 persons needed, 2 pilots, and the engineer could be replaced by the technology according to fly-by-wire. Nowadays, aircrafts are really flying computers, and the pilots are supported not only by fly-by-wire techniques, but by a lot of other systems which are based on digital technology. What is in particular interesting is the very specific man-machine interaction that is introduced in aircrafts today. The pilots are supported in many respects. One interesting example is that nowadays the machine has processes which allow to observe whether there is a cognitive overload for the pilot and make sure that the pilot gets exactly the information that is needed, in particular in critical situations. And what is done in an aircraft is a very interesting example also for other areas of application of man-machine interfaces. But it's not only the pilots, it's also everything around an aircraft or inside an aircraft which is supported a lot by digital technology. be it the infotainment system of the passengers, be it the service systems around the aircraft, what's going on the ground, and also how a passenger today books his or her flights, how a passenger does the check-in, and how a passenger is informed at the airport about changes is very much based on digital technologies. So we can see nowadays there is a kind of a synthesis between digital technology and aircraft technology leading into a very specific field which is really demanding a lot of systems engineering. But this is not the end of the story. Currently, we see that a lot of other things are coming. For instance, one thing which we can observe is big data. Aircrafts collect a lot of data, and in the old days, this data was not really analyzed. Nowadays, we have machines and computers which are powerful enough to analyze all these data sets that are recorded by the aircraft and use the results of the analysis of the data sets to bring in additional support. An interesting example would be predictive maintenance, which allows us to recognize that there might be a problem with a certain part of an aircraft even before the problem is explicitly there and visible. Another good example is artificial intelligence, which allows to support, first of all, the man-machine interface, but also to take over a number of tasks quite independently. So we could even imagine that in the future we will have aircrafts which fly completely on their own, autonomous, completely controlled by their digital control systems, and that no pilots are no longer necessary. Perhaps there will be one person in the cockpit which does some supervision of what's going on, but it's no longer really taking part of the really process of flying. Another example is blockchain. Blockchain is a technology which allows to record data in a distributed manner, such that the recorded data cannot be changed later. This is interesting for logistic purposes, but it's also interesting for safety purposes, so we can record important parts of that. Another example would be the platform companies, and I believe that aircraft carriers and also aircraft producers are on their way to become platform companies which are based on software platforms for the different services they offer. So what we observe is a kind of a synthesis of different disciplines. Disciplines of informatics and of digital disciplines with disciplines classical engineering of aircrafts. They will come together. They are already today about to form a unique discipline of systems engineering, and this will change the world. In particular, it will change the way we produce aircrafts, we operate aircrafts, and we use aircrafts.
Hello, I'm Gunter Reinhardt and I teach production engineering at the Technical University of Munich. Welcome to our module Digitization in Production of the online course Digitization in Aeronautics and Space. Just a few words about me. I studied mechanical engineering at the Technical University of Munich and I completed my PhD at the same university with assembly applications by robots. Later on, I took a lot of experience in industry as well as in science, experience about production technology, production engineering and all. In industry, I collected my experience together with B&W and with IWKA, which is a big production equipment manufacturer in Germany. Last but not least, I would like to announce that I'm a member of the national platform Industrie 4.0, what I will remark later on. My colleague Klaus Drexler beside me. Klaus, would you like to introduce yourself?
Yeah, my name is Klaus Drexler. I'm the head of the Institute for Carbon Composites here at the Technical University of Munich. I studied aerospace engineering at the University of Stuttgart and completed my PhD there at the Faculty of Aerospace Engineering. My industrial career started at Messerschmitt Bölkow Blohm in Ottobrunn and ended after some positions at Daimler Chrysler, at EADS. So my background is aerospace and automotive, but always with a focal point of composite technologies. And this will also be the focal point of our discussions today. I will bring some examples how fiber placement technologies influence aerospace production technologies in the future. And so hopefully we will have an interesting hour.
Thank you. Digitization in production is our topic today, and we know that digitization has taken place in airplanes since several decades. Digitization in terms of airspace control, in terms of fly-by-wire, in terms of navigation or autopilot. Also in production, we use digital systems and digital approaches since several decades, beginning with the 1960s. Digitization of production means the automation of production, autonomous production systems, assistant systems, or the connection of production modules or production equipment using digital linkage. But let me step back to production. What is production at all? Production is the process beginning at the customer requirements up to the shipment of goods. And process steps of this chain are research and engineering, which is to define the product, the production planning and department which prepares the production in terms of manufacturing of parts, of assembly of products, of check the quality and so on. Besides these steps, there's the production control department, which schedules all those process steps for finishing a product, and the materials scheduling, which task is to procure, to supply the production with parts and materials. At the end of the chain, downstream, we find the good being shipped. This is the chain of technical order processing downstream to the customer. Upstream, in the other direction, goes the commercial order processing chain, which means the mirror of all the technical steps evaluated in money. Typical departments are procurement, calculation, finance, and so on. And of course, those functions are supplied by other functions like HR, factory security, legal department, and so on. A corporate management observes, controls, monitors all those projects, process steps, and controls the proper steps. This is the conventional order processing in a factory. What is now digitization? Let me step backwards to the Industrial Revolution. We all know from our history lessons at school that the first Industrial Revolution was inspired by James Watt with his steam engines driving a mechanical loom. This was in the 18th century, and this was the first step against industrialization. It evolved very properly, and a lot of machining and industrial processes have been mechanized and automized. Frederick Winslow Taylor founded the second Industrial Revolution, proclaiming that labor in mass production can be divided into two parts, two segments, the brain work and the hand work. This means that in mass production there are two kinds of people working. On the one hand, the white-collar people thinking, planning all those processes, and on the other hand, the blue-collar people doing, operating those planned processes. This was a huge entrance into mass production, into cheap products for everybody, like cars, like dishwasher and so on. In the 1960s, the third industrial revolution was introduced by integrating computers into production facilities, into production machines, like robots, like numerical control machines and so on. The first robot at all was introduced by the MIT in the US in 1965, and really in 1972 the first robots have been integrated in a car manufacturing plant in Germany. This was the beginning of the third era. In 1910, 1912, the fourth revolution raced into the factories using modern information technology equipment, modern software modules by doing production jobs. Production equipment has become more and more intelligent, interlinkable, and was able to communicate in between or between human beings and machines. And this was the area of intelligent communication and connection of production systems. And this was the beginning of the fourth industrial revolution, which we in Germany call Industrie 4.0. Why Industrie 4.0 and not Industry 4.0? Well, this is a German brand mark announcing all people in science, technology, industry to be innovative, using IT equipment, using modern software modules, using modern networks, computer networks. Well, Industrie 4.0 is not a product. You can't buy it anywhere. It is not a project, and it's not a process. What is it? It is a kind of campaign asking people to use IT technology within production. And therefore, we have a lot of features included with the term Industrie 4.0. Features like systems, big data, CPS, digital twin, and so on. A lot of features. We just want to introduce you 4 of them: the cyber-physical systems, assisted systems, digital twin, and robotics. Those 4 features are major parts of modern factories right now. Let's start with cyber-physical production systems, the CPS, or cyber-physical production systems, the CPPS.
Constant cost pressure, growing numbers of variants, and increasing quality requirements are daily challenges for production companies. In order to remain competitive, manufacturing companies have to produce smaller batch sizes more cost-effectively, which leads to an increase in the degree of production automation. Nevertheless, sufficient or even increasing flexibility is to be realized in the systems. This can only be achieved if the production systems and their elements are closely connected and can react to each other. So-called cyber-physical systems connect the real world with the digital world by enabling the physical systems to communicate with each other via sensors, actuators, and the corresponding software. Through this close connection, processes become more transparent and changes can be handled more efficiently.
Cyber-physical systems. What are cyber-physical systems? Well, this term addresses the fusion of the cyber world, the world of computers, with the physical world, the world of machines, of products, airplanes, cars, whatever you want. And let me give you an example of a cyber-physical system out of daily life. You all, I guess, drive a car and you all use your smartphones. You know, those both items can be interlinked. You can hear music from the smartphone in the car system, the car sound system. This means a smartphone is a cyber-physical system and a car is a cyber-physical system too. They are mechanical devices, they carry software, and they use internet technologies to communicate. The car as well as the smartphone. And this is the idea of the cyber-physical system in terms of they are characterized by the linking of real, means physical objects, and processes with information processing, means virtual objects. And those processes are driven via open, partially global information networks that are connected to each other at any time, at any localization. We can transform this principal approach into the production to factory. Means we use cyber-physical system for production with this cyber-physical production systems, CPPS. And they enable now decentralized production. They enable the interlinkage between production systems, between machines, for instance. Even the connection between human beings and machines, or products and machines, and even carrier systems with robots and human beings. All those items, those components can now communicate, they can describe their skills, their ability, and can work together autonomously. This is the principal idea of cyber-physical production systems. And this principal idea brings us now to a revolution in the automation approach of a factory. In the past, the communication paths in a factory were strongly organized in the automation pyramid. You can see it here. This means we have several levels, several layers, beginning with the field level where the process runs. There are sensors and actuators working on the process. They are controlled by a computer control system, and those several computer control systems are connected and linked by a supervisory system at the supervisory level. Before operating, processes are planned, as we discussed before. Therefore, we have a planning level. And of course, even a management level is available, reporting to the managers of the factory how production is running, how problems are being solved, and how jobs are done. In future, we guess that this strong pyramid will be opened, will be left, and we can connect cyber-physical production system as we want. We can connect each part at any level with another part. This means a very powerful communication between those components. On the other hand, this means we need new organizing structures in order not to end in chaos in the production systems, but to have a very autonomously, very variable, but systematically ordered production system at all. This is the future idea of interlinking computer aided production systems in future. Let me give an example. Here you see the typical scene of factory, human beings, robots, machines working together. And in future, all those components, even the human being, will have 4 abilities. First ability is the spontaneous connectivity. Whenever a component meets another, it connects to the other and switches into communication mode. During this communication, the components are able to describe their own abilities, their capabilities. I am a screwdriver, or I'm a robot, or I'm a human being, and so on. The third ability is the task-oriented programming. Means, in future, we do not need to write specific code on a very low level. In future, we give commands, we give tasks to our facilities, and they know how to operate, how to fulfill it. The fourth step is the automatic device parameterization. That means that sensors, for instance, can adapt their own ability to the product they have to detect. And if a new product comes with new shape, for instance, the sensor itself can adapt its awareness, its measuring system to the new requirements of the product. Those 4 abilities are abilities of a typical cyber physical system. Let me give you an introduction of a future-oriented scenario which will be conducted in production in future. For instance, sensors are able to communicate their needs or their abilities. And we can, as we can see here, a camera can say, I can detect parts, I can detect production equipment, or so. The part can say, I need a screwdriver for driving a screw into the case. Means the components are able to self-describe. Mm-hmm. The second step is the virtual modeling of resources in assembly or in manufacture. Means that the ability, as remarked before, the ability of the components is now mirrored, is now simulated by digital models. And we can now study, we can now investigate the function of the components, of the sensors, of the production equipment in the digital model and optimize it and, of course, plan it, automate it. Automatically, a computer program can plan now the conduction of an assembly sequence. The part knows first comes the screw, second comes the cover, and so on. Third comes the wheel, the gear wheel, for instance. And now it can require all the components, the production equipment components, which fulfill the assembly sequence. That means in future we will be able to automatically plan the whole manufacturing and assembly sequence. Well, this is the theory. Let us now come to practice. And Klaus, I would ask you, how can you give us some examples of cyber physical systems in the practice of airplane manufacturing.
Yeah. So in aerospace engineering, aerospace manufacturing, we have plenty of production technologies based on aluminium, on titanium, and more on composite materials. The most modern aircraft like the A350 consists more than 50% of carbon composites. And the unique thing with carbon composites is that the material is produced during the production. So we need know-how on material science, on structure mechanics, but also on production. And of course, in aerospace, we have quite different requirements to production compared to high-volume automotive industry, because our production number is much lower. But anyway, despite we have a lot of manual processes still in aerospace production, Industry 4.0 is very important because it can help to improve the quality, and it can help to reduce the engineering, the development time. And I will focus in the talk today on one technology, that's the fiber placement technology, where we are combining mainly robots together with so-called prepregs, where the matrix and the fiber is combined in a semi-finished product. And by the control of the robots, with all the understanding of the structure mechanics, we can automatically produce shell-like structures, but also very complex components in very high quality. And you see here an example of a fiber placement machine. And so what you can see also here on this screen is that we are combining robots. We are combining a fiber placement head where the fibers are placed to a tool. And this is really a chemical factory, you can say. So it's controlled by the pressure of the head. It's controlled by the temperature. The temperature itself is controlled, for example, by a laser system. And this ensures that we have a high quality during the placement of the fibers. The robot itself, of course, has to steer the fibers. So the fiber directions, which are important for the mechanical performance of our components, are controlled by the robot. And altogether, we have, of course, a computer, and this computer is collecting a lot of data, because in this fiber placement head, we can, of course, measure the temperature. We can measure the steering of the fiber, the direction of the fiber, and also we can measure the pressure, and all this together defines the quality of our part. So after the collection of all parts, we can, for example, ensure that the quality of the part is very good, and we can reduce the effort in the non-destructive testing, for example, which is up to now very important. And so we can improve the quality, and we can cut down the cost by this automation. And some more examples, modern production facilities, like you see at Premium Aerotech in Augsburg, have several of these production machines, and in future they will communicate. They can exchange information, and if we have several parts, a big shell or very complex door surrounding structure, so these machines can optimize their process by themselves by using all the data they are collecting, and all the logistics of the material can be controlled, because we have to work with the material which is cooled down. It's stored at minus 18 degrees centigrade, but during production it has to work in room temperature. But at room temperature, we can only handle this material for several hours. And so logistics is also very important. And to improve, for example, the waste rate, it's very important that starting from this material storage up to the production using several machines to the quality of the final part, all these things are connected together. And therefore, I think it's a very good example for cyber physical systems. So some more examples. You see here the production, for example, of the A350 center fuel element. So very big shells being produced by fiber placement technologies. You see a wing structure of the A350, so fully automated to ensure a good quality and to have competitive, cost-competitive production. Here you see some productions or some examples for very complex structures, like the A350 keel beam or the door surround frame. So again, it's very important that we understand the material science, how we work with these prepregs in the fiber placement head. We have to understand the structure mechanics. So we have to understand how the fibers have to be steered in the or placed on the tool. And then, of course, we need the robot system, the robot control, to guarantee that the fibers are really placed automatically on this tool. Yeah, some more examples. We can work with various metric systems, thermoset or thermoplastic systems. And here you see another example. It's a space structure of the Ariane 6 rocket, a booster casing being produced by thermoplastic fiber placement, where we are using a technology where we automatically place the fibers, but we consolidate it to the final stage. So it's a one-step process, and we do not need a second step in an autoclave or in a press. And so this is very interesting for big structures, but using the same technology, the same steps I discussed before. And finally, we will show a video of a technology we call fiber patch placement. It has been developed together by Airbus and my institute, and now the company Sevotec, a spin-off of my institute, is industrializing this technology, and it's a very good example, I think, of all the 4 topics of Industry 4.0 you will present.
What is the difference between this Sevotec system and the systems we have seen before, with the large ring producing system?
So we are not placing now tapes, but patches, and this gives us much more flexibility. And we have integrated in this.
Produce smaller radii?
Yes, and very complex systems. So we can really use what we have learned in structural mechanics in the production. And in this one system, in the FPP system, the machine we will discuss later on, we have 2 robots. So we are using combined robots. We have a lot of integrated sensors in the structure. And I think it's a very good example for all the 4 points and focal points of Industry 4.0.
Indeed, a cyber-physical system.
Yes.
That brings us to the next item, the digital twin.
The increasing complexity of production systems and simultaneously decreasing innovation cycles raise new challenges for today's companies, which can be counteracted by the use of digital tools. The digital twin forms the basis for using these tools throughout the entire product lifecycle and for optimizing production processes through the use of simulations. This digital twin serves as a digital representation of the real plant, which accompanies it from development to operation. This enables a virtual commissioning already in the development phase, in which the control logic can be validated and, if necessary, optimized before the real plant is put into operation. Because even in seemingly simple automation tasks, inappropriately selected parameters can lead to inefficient processes or even malfunctions.
Let us skip to the next item of our Industry 4.0 scheme, the digital twin. What is a digital twin? Well, this is the image of a real component in production. And we can use those digital twins for simulation. Simulation is a very often used tool in production planning. And the definition says it is the representation of a system with its dynamic processes in an experimental model, a digital model. In order to reach findings, we are transferable to reality, back to reality. In particular, the processes, they are developed, the tools, the products, and so on. And we can investigate using this simulation system in order to get new findings about the change or modified production system. This is the general view of modeling in simulation, of using digital twins. Simulation, by the way, has been used since many decades. In the 1960s, physicists used simulation to show, to explain physical effects like magnetism. In the 85, simulation was used to show the behavior, the movement under stress and strain of products. And end of the last thousand, we used simulation for investigation of production systems. We can simulate the geometry of the systems, we can simulate the physical behavior of those systems, and even the organizational data like reliability and so on can be imaged, can be mirrored by using simulation systems. In the last decade, the area of using simulation system was widened until the whole life cycle of a product. The simulation of the production, the simulation of the usage, the simulation of the dismantling, the recycling. And this whole simulation model is called digital twin, as a combination of the design of the product or the machine and the data collected by the operation and during usage of the production. These digital twins are able to be used to accompany all physical products through the whole product life cycle. For instance, the physical products with specific instantation, the virtual representative or digital companion. And even in the practice of planning a production system, we can use those digital twins. As you can see here on this device, you can see a future product integrated with the real environment of a production line in reality. They are fused together and the production planner can receive new knowledge and new achievements. This digital twin is also used to show mirror the image of product and process, production processes working together. How does a production process modify a product? What is the impact of the robot welding a beam of a car and so on? This is also a feature of simulation and production planning. With other terms, it means we can collect design data, we can collect production data, and we can collect operation data of the product and fuse it into one single model. And this is what we call the digital twin. On the one hand, we have the model being described by the designer and the production planner, and on the other hand, the data collected during production and operation of the car in this case, and those together in one model is called the digital twin. Since we have the possibility to use such digital twins for just one machine, we can now widen it, broaden it to many machines, to human beings, to robots, to carriers, to a whole factory. And this is what we call the digital factory. The digital factory is a strong tool to investigate the whole factory, the future factory, in order to detect mistakes or bottlenecks, in order to see the impact of some production facilities upon the product, and in order to investigate the reliability, the output of the whole factory. And therefore, there exists a definition for digital factory given by the VDI 4499. The VDI is the German Engineering Association, and it reads, it is a digital factory, is a generic term for a comprehensive network of digital models, methods and tools, including modeling, simulation and 3D virtual reality visualization integrated by continuous data management. Means we need digital images, the models, we combine it to a system, a production system, and we can investigate this system in order to get new findings.
Especially for the operative employees on the shop floor, the demands on their work are becoming more complex as they have to produce faster, better, and more flexibly. Additionally, the number of variants is growing, for which different workflows have to be carried out. In order to meet these requirements, assistance systems are increasingly being used to support and relieve employees in a wide variety of tasks. Mobile devices in particular, which have been an indispensable part of private life for several years, are now increasingly finding their way into production halls.
Our next item is assistance systems. Assistance systems raised during the last 5 years in our factories, and they are established in order to give aid to the human beings in the production process. Those systems assist people in the increasingly complex world of production in terms of improved documentation, employee-specific support, competence development, increased process reliability, and accelerated work process. And the expectation is to improve quality and flexibility with shorter lead time, less cost, and less stress level using those systems. Well, there's meanwhile a manifold of assistance systems available. Those systems which support people, support worker in her actions. And therefore we can bring some structure into those manifold of assistance systems. We can divide it in two major parts: the cognitive support, supporting the brain work, and the physical support, supporting the work by hand. And even the cognitive support can be divided into perception assistance and decision assistance. Meaning those systems can help to see mistakes, wrong parts, or can help to decide how the next step has to be during the process of production steps. Physical support systems can help to carry heavy parts or to achieve quite difficult or difficile production processes. This is the principal idea of cognitive and physical assistance system, and those systems can be used in very, very many applications, like warehouses, where we can register incoming goods in a very simple manner, where we can identify components or the localization of a component in the warehouse. We can support the order picking from the storages, from the shelves. Assistance system can be used for production processes to improve the accuracy, to improve the quality, or even to document the result of a process step. Last but not least, outgoing goods can be checked by an assistance system whether they are complete or they are in good quality. The whole processes are being documented. For instance, in the airplane production, we have to document all those processes with their parameters, and assistance systems are able to help human beings to do a good job. This is the idea of assistance systems.
The variety of variants in production requires flexible possibilities for automation. Robot systems that can be used for a wide variety of tasks due to their design and free programming are suitable for this purpose. Since not all tasks can be fully automated, humans will continue to perform tasks, and the two resources can share the work. Mobile robots consist of a robot arm and a mobile platform, and can move autonomously in the production area. This results in additional degrees of freedom, so that the robot is flexible in terms of location and can therefore process tasks at various points in the production or perform transport tasks. Robots that work together with humans have sensors that are responsible for detecting collisions and thus do not endanger humans. When working together, the robot can support the human by taking over tasks that are, for example, not ergonomic.
Robotics is the last item we want to address. Of course, robotics is not pretty new. As I remarked before, robots have been used since 1972 for almost 40 years. But during the last 5 to 10 years, there has been a very, very exciting development within the area of robotics. Coming from the conventional use of robots in terms of single-purpose programming of robots, in terms of execution of the same tasks over 5 to 10 years, we are now able to create flexible robots, to create mobile robots, and to use robot-man collaboration. With other words, since we had a lot of changes in production, variants, new products, shorter product life cycles, we need robots which are able to react on the changes in the products and in the product lot sizes. New robots, new generation robots, are able to aware the environment, the new products, and to react with changes in their movement, in their working cycle on those changes in the products. Together with automated guided vehicles, they are now able to realize a very, very flexible production environment. And even robots are combined with mobile vehicles, which we call mobile robots. And those mobile robots can change their workspace. They can come to human beings and help them doing some tricky, difficult jobs and so on. Current trends in robotics are the human-robot interaction. Means one or more robots collaborate with human beings in one workspace. This requires new communication methods, new communication abilities. We do not have to program each single step of a robot movement. We just have to give them tasks, and they have to solve these tasks into steps of movements, into logical steps, and so on. We come to a much more easier programming of robots, and we communicate with robots by speech recognition, by gesture recognition, or even by eye tracking. The robot follows the eyes of a human being in his environment. And even more than one robot work together with more than one human being. This is the highest end of human-robot interaction we are working on in research. This slide shows us a scenario in a real factory, a gear manufacturer, and you can see the robot collaborating with a worker working on the assembly of a gear. Typically, the robot fulfills the difficult steps, like the position of the housing. The housing is quite heavy, and it's very easy for the robot to position this housing, picking it out of the bin and bring it on the table. The human being transduces the difficile parts of the production sequence, like the packaging of the transmission or the sealing of the housing. Therefore, human being and robot divide their tasks, split their tasks, and each part or each unit of this work system does those jobs which are mostly suited to the robot or the human being. Other examples for robots are, for instance, warehouse operations. Pick and place jobs in order to pick the correct parts from the bin, or the processing of parts, delivering the parts into a turning machine or another machine tool, supporting assembly lines with delivering of parts or even spare parts for the assembly machine. And last but not least, the palletizing. The output of a machine, produced parts, are picked by the robot and palletized on those containers. So far, the robots.
So in aerospace industry, robots have very specific tasks. So in a
That's
factory
right.
of aerospace, you do not see normally hundreds of robots in a street producing hundred thousands of parts, because normally we produce only few hundred parts. So the tasks are very specific, but also the challenges are very specific, because they have to be very accurate. For example, to place the fibers on a tool. And they also have to be very affordable, because, like I said, they do not produce hundred thousands of parts per robot, but only a few parts.
Yeah.
So assisting a human being producing big parts, all this is very important, and they must be very flexible. For example, to produce one day a big shell and the next day a very complex part. And that's only one example, the fiber placement. There are various examples you have shown, but with different tasks and different challenges in aerospace production.
Indeed, that's true. And that's the reason why I told you about the task-oriented programming. You cannot write a lot of lines of code and describing each step in assembling the shell and so on. You just tell the robot, please produce this shell or that shell, and it has to solve the single steps to be done.
Yes, and that's quickly, because we have to
and
be
automatically.
quick and automatically.
Yeah.
Yes.
And the other point is, we need a lot of sensors within the process, which conduct the robot along the right movement, along the right path. We cannot program each single step of millimeters in the path. The robot has to take intelligent sensors and follow the part using the sensor data.
Yeah. And in parallel, we have the virtual system, so we know how the fibers
Exactly.
have to be placed based on the structural-mechanical investigations,
Yeah.
and we know the knockdown factors. If we can guarantee that the angel is 95
Really,
degrees,
yeah,
but it's
yeah.
60 degrees.
Yeah.
But then we have to justify this by the sensors, and we have to know, is this acceptable? Is this knockdown factor acceptable? And the part is then good to fly, or it's waste, and that has to be avoided.
In the simulation, in the digital model, we have the ideal path. Let me say ideal path. But the transfer to the real path in production has to be done by sensor-guided movement.
Yeah. And so we will see many more robots in future aerospace factories.
Intelligent robots with sensors, actuators, and so on. Klaus, as far as I know, you brought a video with you showing us some collaborating robots within the very exciting job tasks of fiber patch placement. Perhaps you can have a look on that video.
Yeah, it's not only on cooperating robots, but it's also a cyber-physical system, so Industry 4.0 in a new development of a production technology. What you see here, it's the fiber patch placement technology, and not like in the fiber placement technologies where we have endless or near endless fibers. Here we have patches we are placing. These patches can have a various size depending on the productivity we want to have. And you see here also the cyber-physical system. So we are simulating the process. We have a link to the structure mechanics. So we have an optimization program in parallel to the development. And so according to the loads and the geometry, we can calculate the direction and the place of these patches.
And the optimization program uses a digital twin.
Yes, and it's transferred to the machine code, and so the whole production system is then automatically transferred to the system with the two robots. You see, one robot is handling the mandrel, the tool, and the other robot is handling the patches. And the patches are cut to pieces, and these pieces are then controlled in an online process monitoring system by a laser system to guarantee that the patch is there where we need it and the patch has the right direction. And so we have an online quality assurance system. And like I mentioned before, we do not have only the control at the end by non-destructive testing.
This is an assistant system for quality assurance. I see. And the patches are being used for avoiding waste, is that true?
Yes, So the thickness of the part in each dimension, each geometry has the right dimension, and the fiber orientation has the optimum. And you see here the length of the patches and of these grippers can be controlled, and so we can control also the productivity of this system. And here we have the final part. It's now a dry fiber placement technology. So these patches are dry carbon fibers. And in a second step, they are injected by an epoxy resin to have the final part.
Okay, very impressive. Thank you. Therefore, I thank you for your attention, and I hope you enjoyed it.
Thank you very much.
A very warm welcome to our current topic, workload and human factors analysis. I would like to present you topics around the man and the human factors topic. My name is Harald Schaub. Workload is the amount of work an individual has to do. Actual amount of work and individual perception is what workload makes. Assessment of operators' workload has a vital impact on the design of the human-machine system. Occupational or work-related stress is a response people may have when they presented with work demands and pressures that are not matched to their knowledge or abilities and which challenge their abilities to cope with. This may lead to inefficiency, to inadequate man-machine cooperations, and to human errors. Prevention of inadequate workload and occupational stress increases efficiency, reliability, and safety of complex systems and support accomplishment of mission objectives. Human errors. Human errors are about to 70% of individual accidents are directly related to human errors or caused by human errors. 70%. This is due to bad design of the technical system. For example, the system is non-intuitive. This is due to inadequate or failed processes, for example, not supporting situational awareness. This is due to management problems, for example, unclear lines of responsibility. And this is due to improper training, for example, not training of problem-solving skills. 30% of industrial accidents are caused by failures in technology and organization. But let us put the question, who designs the system? Who manages the system? Who maintains the technology? This is also people who run the technology, who build the technology and run the organization. Human error is not intended by the actor. It's decided by a set of rules or external observers. It leads a task or a system outside its acceptable limits. Human errors are not only the primary cause of contributing factors in disasters and accidents in industry, but also the major contribution in inefficiency. Human error is a deviation from intention, from expectation, and from desirability. We are able to evaluate workload. Evaluating the workload of the operators, we can doing the design of the new system, we can iterating with existing systems and with problems such as workload bottlenecks, overload, and inefficiency can be identified. The human error is a central part of the human-machine system, the correction of the problems, if necessary, of the operations for a safe and efficient system. Mental and physical stress, inefficiency and unsafe acts. The workload or human factors analysis identified the human issues for mental and physical stress, for inefficiency and unsafe acts. We can do this on several levels. We can do this on a skill-based levels where action, communication, man-machine interactions occur in the operator's execution of a certain routine. Or on a decision level where actions, communications, where man-machine interactions occur when the operator proceed an intended set of actions, an intended set of measures. Or on a perceptual level, where actions, communications, and interactions may occur when the operator's sensory input is degraded or when decisions made upon faulty information. We have certain preconditions for stress, for inefficiency, for unsafe. We have preconditions which are related to the environment, for the physical environment, the technical environment. We have preconditions which are related to the condition of the operator himself, of his current mental state, of his physiological state, of his mental limitation. And we have preconditions which are related to certain other personal factors, for example, crew or team factors, or readiness level of people or training level of people. In a workload and stress situations, there are certain aspects we can control when we design the system. The first part we can control is the system suitable for the task? Is the complexity of the operation, is the functional range, is the complement of the requirements, is this really built up within the system? Second aspect we can control to monitor and to design a situation is the question, is a system self-description? Has it a self-description ability? Has the chance that the operator understand what the system says, what the system do? The third aspect is controllability. Which functions are controlled by whom? By the operator, by the system. Let's imagine a car. You have the steering wheel. Controllability is to the person. If you have another function within a car, for example, the inner state of the engine, this is controlled by technology. The first aspect is expectation confirmation. Is the system behave like the operator expect? Is the cognitive expectation of the operator fit or matched to what the system really do or what the system may do in the future? Error robustness. Is the system tolerant in relation to errors done by the operator? Does it correct the errors? Does it monitor the errors? Does it give it a chance to rehearse the errors? Individual awareness. Is a system adaptability to the owner, to the operator's desire, with colors, with font size, but also with the overall behavior? And gives the system the possibility to learn how to control the system, to learn how to control the functions done by the system. Especially the last part, learning from the system, may come crucial in our new system, which are more and more running in an automated way where the operator has nothing to do, and so he has no chance to learn from the system because the system, in most of the situations, the system is doing all the function by itself. A crucial point is the role of the organization at all, and especially of the supervision and of the management in stressful, inefficient, or in unsafe situation. We quite often have inadequate supervision where the management will not take the role or the tasks they have to do in controlling and managing the situation. We have quite often badly or inappropriate planned operations where the plan is not really fitting to the requirements of the situation, and sometimes you can have the impression that the plan is designed to fail because it's improper. We have failing correcting known problems where people will not take the problem, will not start problem solving, just ignoring the problem, and the problem becomes bigger and bigger and bigger. And we have supervisional violations where the management will not act as they have to do, will not act in controlling the situation, will not act in giving guidance, will not act in giving goals and aims. The factors controlling all this is related to resource management, of course, which is related to the management of the technical resources, but also, of course, related to the management of the personal resources, of human resources. And the crucial point is fitting these things together. The technical point and the personal point or the human factors point fit together, that the right technology for the right task with the right people are on the right time in charge. And perhaps one of the most crucial aspects is the organizational climate, the organizational culture. Is there a kind of an error culture of talking about errors, of reporting errors, but not blamed to make errors? Is there a culture of talking about the own experience of stress, of inefficiency, or is there a culture of not talking about these things and or ignoring these things and dealing with these things when it happens and not in advance? You have to put all these things in a kind of an operational process where you can expect that people act different when they are under stress, that they act different when they see or when they expect to be inefficient, that they act different when they see or when they produce unsafe acts. You can expect this or you can manage this with an appropriate operational process. We have certain methods to analyze human factors at all or a special workload. One of the most appropriate method is direct observation within a current, within the actual situation on the workplace, in the situation, on a board of a submarine or within a ship or in a plane or within a car or in a plant or in a team situation. What we're doing there is observing the people with psychological and with subject matter expert observers. We use technical systems to directly observe. One very appropriate method is eye tracking, where you can focus where people's conscious is, what the amount of workload is. And you have certain physiological measures you can do also, heart rate, for example. And of course, you can do interviews, talking to the people, observing what they are doing. It is very accurate when you are within the situation. You have a very valid and good access to the workload because you measure it within the situation itself. The problem is it is quite costly and it's consuming time in the realization. The system needs to be there. For example, if you are just building a new system, you cannot do direct observation within the system because the system is actually not there. And you interfere with steering the system. When you're driving a car, for example, and you have in your car 3 psychologists sitting and looking at you, you will definitely behave different to the situation where the psychologists are not within there. So the recommendation is one of the methods of the choice, direct observation, but you have to add additional methods to analysis human factors and workload. What you also, of course, can do is surveys and questionnaires. Surveys are quick, they are cheap, they are comprehensive. The problem is they are not very accurate and often invalid for the current situation and for the determining the workload here in the situation, because asking people on a certain amount, what is your workload in the situation, people are often not able to understand this question, because they have not really access to their own workload. Especially in very stressful situations, people are not able to recognize their own stress levels. So surveys and questionnaires are okay for some tasks, but not for all. But in combination with the first method, direct observation, it produces a better picture. One method we have from software engineering is a cognitive walkthrough. Is a psychology-guided mental simulation of the situation, where you go through the certain steps you have to do. Open the car, starting the engine, making the gear, running on the street, and all these things. So step by step, you produce a walkthrough, a mental walkthrough through the situation, and try to determine what you have to do, what is the problems you have to do, what is easy to do, what is routinized, what is a problem-solving task, and so on. The Pro is very accurate and it's a very valid method, but it's a simulation, of course, and you have to deal with certain experts who have a good experience with this situation. It is good for situations or for systems which are in producing or in designing and new, where we have not the possibility to access the system itself. For example, if you are building a new ship or a new car or a new plane, you can make a cognitive walkthrough with the people and supported by technical things like a CAD picture of the system, for example. When we combine all this method, direct observation, surveys, questionnaire, and cognitive walkthrough, we typically get a good picture of the workload of people in a certain situation. When we talk about human factors and workload, it seems we are talking about psychology. That is not really true. We're talking about how people manage a task, how people manage a certain workflow. They have a certain input in the situation, which are goals, which is the task itself, which are some dependencies and some additional external factors. And they have to produce an output, which is information, which is a new task, which is a report, which is a communication act, or what else. So the interesting point with human factors analysis and determining the workload is not only looking at the person itself, but looking at the person doing a certain task or a certain workflow. To understand the influencing factors within the human factors environment and to better understand workload, you have to take into account certain aspects. One of these aspects is what you can call human factor system design. That is, you have to encounter the psychological capabilities and limitation of people interacting with the system. You can use things like thinking tools to support people, or you can have additional sensory abilities to make them act in a certain situation. But the crucial point is you have to understand that people have certain limitations, cognitive limitation, emotional limitation, stress limitation, but they have also capabilities which can use, for example, problem-solving capabilities, intuition, creativity, and all these things. A perfect system design is a system design where you take into account the capabilities and limitation of the technical system and the capabilities and limitation of the people involved. The next part is health, human health. Psychological and mental stress or fatigue produces problems, produces unhealthy situations. You have to think about how long will people stay in a stressful situation, what can I do to support them in a fatigue situation, and so else. You have to see an overall system safety approach. System safety does not only mean you have to produce a safe technical system, a safe engine, a safe machine, a safe car, a safe plan, but you have to ensure that the whole system, including possible human errors, are safe. We have on one slide the amount of 70% of the causes of an error or the causes of an accident are to human error. So it's a crucial point within an overall system design to reduce human error. Not necessary to substitute human error by a machine, but to take into account what errors could occur. You have, of course, the aspect of training. training for human performance, training for crew resource management, training for preparedness and awareness for the current situation. But you have to be careful with the topic of training. We quite often see that we have a bad system design, a bad technical system design, and people say, okay, then we have to train the people. You cannot use training as a joker for a bad system design. A bad system design is bad, and you cannot solve it or heal it with a training. You have to reduce the training only on these aspects to interact with a good designed system. Acquisition, which is about testing, is about evaluation of system, which is about finding the right ergonomic system, finding the right man-machine interface for the current situation. And of course, the overall manpower and personnel, which kind of preparedness do I need, which kind of expertise do I need, which kind of amount of people do I need. When I take all these factors into account, all these influence factors on task and workflow, I am on a good way to not reduce workload to zero, of course not, but to reduce the workload and the human factors erroneous to a level which is handleable. So far for today, and thank you very much.
Hello, Professor.
Hello, but please call me Harald. How shall I call you? What's your name?
Call me Pepper. I would like to interview you today about digitization and human factor aspects. Can we get started?
Yes, sure. Let's start with this interesting topic.
Will robots eventually take over control? Like in the movie Terminator?
I think we will see that robots and intelligent algorithm, artificial intelligence, will take more and more control over different parts in our society. We see it until now. We have it on a stock exchange, for example, that intelligent algorithm produce a huge amount of different aspects in interchanging money and other things. And we will see that in military aspects, that intelligent algorithm take over certain weapon system. So we'll see more and more that intelligent system, intelligent algorithm will take over control. I'm quite sure that we will not have the scenario from the Terminator where we'll have a kind of a war between mankind and robots. But what we will see that our daily life will be more and more get impacted by robots and intelligent algorithm like we have it today. If you have an automatic teller machine, it's kind of an intelligent algorithm who gives you money or not. If you cannot change that, you cannot discuss with him to give you the money. If he makes a decision not to give it to you, he has the control over that. So we will see more and more this kind of control in the next years. A certain aspect might be the kind of fighting robots within in a war scenario, and there's a big discussion about will we really have this kind of robots, we will really control whether they use weapons or not, but I think that it's a more ethical and political discussion than a technical discussion. Is it possible? Now it is possible to develop these kinds of robots, these kinds of technology, and we'll have to decide whether we'll use this in certain aspects and give them more and more control.
How will jobs evolve in the future?
We will see that robots and intelligent algorithm, artificial intelligence will take over more and more tasks of jobs people doing now. So we will have really to face that some jobs will diminish and people have to care for a new job. That will happen, but we will also see that new kinds of jobs will develop. So there might be a kind of a balance between job reduction and increasing of jobs. But what we also see will that certain tasks which are not possible now, or certain aspects which are quite complicated and expensive now, will be done by robot systems, because we have a changing society. We will need robots in production, we will need robots in service, and we will help needs their help in certain aspects to increase our efficiency on a more and more complex environment in a situation where we have in Europe especially less people doing certain tasks. So we will have a great impact on the development of jobs and work environment in the next 2 decades, yes.
What are the challenges staff and managers are going to face?
I think a crucial challenge will be that we will have more and more kind of mixed teams between humans and robot kind of colleagues. So this will change for me as a colleague working together with a human colleague and a robot-like colleague or an artificial intelligence program, but it will also change for the manager how they have to lead this kind of teams, how to have to coordinate this kind of teams, because they will have in the next 10 years teams of men, human, women, robots, intelligent software, artificial intelligence, and all have an impact on doing the task and doing the work. So they have to change their understanding of how leadership will function. It will definitely change, especially for the management level, I think.
How can or should we prepare for this?
I think we should take part of this development, not only the technology development, how we can improve artificial intelligence, how can we improve robots, but also on the ethical, political and psychological aspects of this development. We can try to shape what we will have in the near future, how we will replace certain tasks, certain aspects of our environment by robotic systems, by intelligent systems, by artificial intelligence. So I think we should be part of this development. Otherwise, if we try to avoid this development, we will see that we will have in 10 years or 20 years, we will have systems from all over the world which have a certain behavior, a certain philosophy behind them, and we cannot really change that. We have just to consume that. So taking an active part in the development, in the technical development, in the ethical development, political, and also the psychological aspects should necessary to shape the future.
Will there be a robot factor science alongside the human factor science?
What we see today is that the processes in a neural network are not fully understandable, why and how a neural network comes to a certain decision. Systems which comes more and more complex are not understandable on a basic algorithm process or algorithm perspective. So we have to deal with, or we have to develop robots and intelligent algorithm which can explain their inner state to us. I have to ask you why you draw this decision, why you make this, why you show this behavior, or why you didn't draw this decision. And so that the interaction between robots and humans will be in a more communication way than in the only programming and reprogramming system. So we'll see a development which goes in that direction, that we will have a kind of a robot psychology to understand the inner states, to understand and to predict how a robot will behave in a certain situation he is not programmed for. Like we have to understand and predict how humans will behave in a certain situation.
Is it possible to form collaborative teams comprising both humans and robots?
Yes, sure. And actually, we have this kind of teams until now. We have quite simple working robots on a manual way, on a physical way, interacting with human co-workers. And we will see more and more of this kind of teams. And we'll see more and more teams which are not only working in manufacturing and doing things on a manual basic way, but we will see teams which interact on this level of cognitive, intellectual aspects, on a problem-solving aspects, on decision-making aspects, and of course, perhaps on an aspect of, or on a level of leadership. So I think the future will be collaborative teams between not only robots and man, but also between artificial intelligence and man, which can improve our ability to do something and reduce our need to care and to do things we are not really good as humans, for example, things which are boring, things which produce fatigue and all these things where we are quite bad. And you are better in because you have not to sleep, no need to sleep.
Where would you position me, Pepper the robot, in the working world?
I think the robots we will have today are a kind of a state of development, and in this process in development, better and better and more intelligent and more not only human-like but human-helping system. So I think you are a perfect prototype to understand how we can interact with robots, how we can develop their physical and psychological and behavioral impact so that they can help us doing certain tasks, but also how can we accept that we are helped by a robot and interact with a robot, and it's not only fun and work, but it's also kind of empathy and understanding why you ask me, for example, a certain question, why you doing a certain behavior. So I think we will go in that direction, yes.
What else would you like to tell our viewers?
I think a crucial aspect for the next years, next decades will be that we understand that we will develop more and more systems which are highly interacting, interdependent from each other, which produces intelligent actions which are not only understandable or not only developed by one discipline. I think we will see in the next decades that psychologists, developers, that engineers have to work more and more close together to shape a new working environment which is built up from certain aspects, where we have man, where we have robots, where we have intelligent algorithm within the system. So we have many different technology or many different realization of how can we do information processing, how can we do problem solving, how can we do decisions. There might be a human-like way, there might be a robotic way, there might be a way of neural network and artificial intelligence. But at the end of the day, we have to understand the whole system to understand and to produce a better decision and at the end, of course, a better world.
Thank you for your time and for the interview.
Thank you, Pepper, for your time and your questions. Thank you very much. Bye-bye. Welcome to our topic, Digital Leadership, the psychology of the future leader, the leader in a digitalized world. In the past, digital was just what the IT department and what accounting are doing. In the past, managers mainly communicate with other managers. The CEO with the vice president with the department manager with the team leaders. Only the team leaders themselves are at the lowest level communicating and talking to the subject matter experts doing the real tasks. Common sense was quite often enough for the upper management to understand the own processes, the own business, the own products of the company. And the opportunities and risks of the environment was just in a common sense understanding. In the future, this will change. In the future, new IT will be part of the core function of most of the companies. Currently, we are on the way on that, but we will reach a situation where IT or new IT will not only be a supporting function, it will be in the core business. In the future, the manager have not to communicate with other managers, they have to communicate with employees and with their employees of the generation Smartphone Plus. And they have to talk to and they have to communicate with non-human employees, with AI. experts or AI functions or robots. Future IT processes will play in a world that is very far away from our everyday world. This denies access to common sense and intuition. Daily business or business in the past was quite close to common sense and intuition because it handled the work we can understand. Future IT processes are in an IT world, in a digitalized world, in a world which has no easy and no sensible relation to our day-to-day life. The world of future organization will be technology and IT dominated, of course. But social and psychological factors such as trust, empathy, responsibility will become not less. I expect they will become more meaningful. For example, social hacking is one of the most common and successful methods for cyber attacks, which is scareware, phreaking, phishing, dumpster diving, all these things. We have highly protected technical systems, and to enter the system, to attack the system, we use social and psychological mechanisms. We have certain strengths and weaknesses people have and which are related to our past environment, to our past working environment. Humans are bad with permanent attention, they are bad in timing activities, they are bad in monotony, they are bad dealing with rare events, and they are bad in dealing with senseless activities, senseless to the subjective expectation of the person, not nearly senseless at all. Machines are or were better at speed, at force, at calculations, at reps, at parallel activities, and with dealing with short-term memory aspects. People are definitely better in the past and now where it comes to creativity, problem solving, curiosity, intuition, and of course responsibility, values and ethics. But what will be tomorrow? What will be in a digitalized world, in a world where AI functions become more and more crucial? Perhaps curiosity, problem solving, intuition will also be possible for machine. And only responsibility, values and ethics may rest for us, and we are reduced to just controlling and checking whether the system are running in a reasonable, responsible, value and ethical based way. Unclear for today, but possible for tomorrow. Let's have a look at the psychological perspective. We have certain psychological basic aspects which may or might change about perception. The old picture of the world will not longer be appropriate because we have new definition of what the world, what the business will be. Cognition, common sense was yesterday. We have to develop a new kind of common sense for processes and for IT world of tomorrow. Knowledge. We have better to understand the new core process. The new core process is not only the production process we have in the past, producing a car, building a certain product, but we will have a kind of a digital twin within the IT system. We have to understand how digital twin and the core process or the original process are related. About motivation, the leadership style will change, or furthermore, future leader will have multiple leadership styles according to the requirements of a certain situation. Emotion. We have to have trust in the intelligent, intentional technique of the new system, to trust a system which have no human interface, which decides something, which gives information. We have to trust that this information is valid or this decision is good. Affiliation, we have a kind of new teamings. We have human-machine teaming. We'll have human-machine leaderships. The future leader will have teams with people, with men, with women and robots, for example, and have to understand how I can deal with this situation. Will be the future leader able to lead in the way he did in the past? Will he be able to be a kind of a role model for AI? In the past, a leader made something and employees said, oh, this is a cool person, I will do it the same way, I will do it how he did. That will not be possible. Or will it be possible with certain AI system and with robots in the future? Will it be able to develop some empathic relation to a robot to understand why or what is the robot is doing, and vice versa? Will the robot develop a kind of empathic understanding what I do? Do I have stress? Do I be angry? Do I have a certain kind of inefficiency? The common sense will change in a world of bits and bytes and milliseconds. The common sense we have is from the past, from 10,000 years ago, and not be really able to understand what happened within future IT system or even within current IT system. Intuition. It is desired from the experience, our intuition. For future, digital leadership does not have this experience because the situation, the processes, all aspects will be new. So they cannot deal only with intuition. They have to develop a kind of a new problem solving and understanding of the situation. Communication and interaction requires a common mental model of all agents within the situation. So we have to develop a mental model understanding an AI system. The AI algorithm have to develop a kind of a mental model of me as a human being. Concerning leadership styles, there are many leadership styles possible, from controlling, via monitoring, via delegation, and many more. In the past, it was enough for a leader to have one or two of these leadership styles. So today's leader need to master only one or two. In the future, they have to master nearly all of these styles and had to adapt the kind of leadership to the particular requirements of the situation. The future leader have to understand that his leadership have to serve certain requirements of the future situation, and he have to adapt to the situation in changing his style of leadership. We have many challenges. For example, human-machine teaming on the management level. We have not only human-machine teaming on the operating level, people in the production area using a robot, but we have also on the C level when we have intelligent systems, when we have AI system, which produces information, which produces decision. And on this level, people have not only to understand the AI system and communicate with the AI system, but they have also to understand the situation of young people who learn to develop, to understand a world in a smartphone plus picture and have a different understanding how systems and processes work. And of course, even on the C level, on the management level, we have to interact with a kind of robots. It must not be these human-like robots. It might be an engine, it might be a certain system, but it might be an intelligent system. Leadership have to break down. We have dysfunctional leaderships even today, but tomorrow it will be more problematic because the impact and the kind of the new situation will be stronger. We have a kind of toxic leadership will mean that the leader or the leadership feels like he is the only item or the only person or the only situation defining the situation, which is not true. Even more worse we have today and in the past, and will be a problem in the future, with no leadership. The problem is, if not understanding what the requirements are, I will not be able to lead. We had on the last slide the impact of many new leadership styles. If are not possible to adapt to these leadership styles, to the necessity of a certain leadership style in the current situation, I cannot lead. And we have the problem of problematic technocratic leaderships, which mean that people only hand items, situation, information, but will not lead people. We will have the problem of an inadequate understanding of the situation because we build up, or the future leader will build up, wrong mental models because he did not understand the situation. He develop or he will use an improper intuition because intuition comes from the past and will not adapt or will not fit to the new requirements of the new situation. We will have simple mind, common sense, kind of a daily understanding what AI is, what IT system does, and we have an understanding or lack of understanding of the new social and psychological components of these new situations built up of intelligent systems, of robots, of humans, and of all the interactions between them. The future leader will have a situation which is digitalized, which is psychological, which has new requirements. In this module, we have talk about human factors 4.0, which means we will have a new kind of interaction with new kind of system. I will say thank you very much for being here, for hearing these episodes and for hearing these issues, and hopefully you get a better understanding of human factors within a new digitalized world. Thank you very much.
Welcome to my lecturing Managing Maintenance, Repair and Overhaul for Civil Aircraft. I would like to introduce myself first of all. My name is Josef Mendler. I'm aircraft engineer since most 25 years and working now as a compliance verification engineer in various companies, design organizations. So I'm highly involved since a couple of years, more than 2 decades, in this world of certification. And here in lecture 1, I would like to focus on the world of certification covering CAMO, which means Continuing Airworthiness Management Organization. First of all, let's have a look to the phases of aircraft development. Here in these phases, 3 parties, main parties, are involved. It's the engineering, the manufacturing and maintenance. Engineering is mainly oriented and guided by the requirements of aircraft engineers. That means consisting of compliance with verification and certification requirements in correlation with significant load cases, functional specifications, etc. Customer liaison and in-service support is an additional challenging task which has to be taken into account in the very previous and early stage of phases of aircraft development. And engineers are definitely interested in applying cutting-edge technologies in their new aircraft they are going to develop. The second party is the manufacturing. These are manufacturing facilities, and those are mainly driven by cost. And here, cost reduction, of course. Costs are mainly composed by recurring costs and non-recurring costs. Non-recurring costs are determined by engineering staff. Customer support is also a major issue of manufacturing facilities because customers are interested in getting spare parts in order to perform specific repair procedures they are accredited for or allowed for. Robustness of the manufacturing process is another challenging task which has to be fulfilled by manufacturing facilities. Manufacturing facilities are at least in the duty to guarantee a repeatable high quality of produced parts. And last but not least, the cutting edge technologies should also be applied within manufacturing, but of course those applications are overcovered by cost reduction demands. The third party is the maintenance facility. Maintenance, at least, is interested in having robust structure and systems. That means the system must be inspectable, it must be repairable, at least it must be accessible. Corrosion resistance is another driving factor which determines at least the fatigue life limits, and large inspection intervals means that's in correlation with those determined factors. Low cost of spare parts is another item which means that the design operating costs could be kept small. Those 3 parties, engineering, manufacturing and maintenance, also cooperate along the line of certification. Certification of an aircraft is at least determined by 2 major milestones. That's the type certification and the aircraft certification. Type certification is issued by the authorities. In national terms spoken, the Luftfahrtbundesamt, or in European terms spoken, EASA. For North American market, the FAA is responsible. But at least the input must be provided by engineering. Engineering, which takes into account the certification requirements. Here for fixed wing aircraft civil, it's EASA Part 25 or the FAR 25. Here, with this conformity and after check of the authorities, the type certification is issued. In the next step, the production and manufacturing facility is required. Here, the conformity to the requirements, to the documents, to the design documents must be stated by production, and after checking and being issued by the authority, aircraft certification is cleared and is issued. Then the aircraft is able to be put into operation. The operator at least is interested in maintaining the certification, and that means maintenance is a major challenge for those operators. So these operational items and maintenance items are determined by EASA Part 145. In order to repeat these terms, these very significant and important terms, let's have just a look at those three topics. Type certification is a prototype assessment, which at least checks the conformance, and the certification of the prototype assessment is the base for the accreditation of the aircraft. Then we have the aircraft certification, which is the statement of conformity issued by manufacturing. Declaration of accordance of manufactured aircraft with approved prototype means it is the airworthiness of the single part and the system. And the certification is at least the base for the flight accreditation of an aircraft. And in the third step, we have the maintenance check. It means that the declaration of the accordingly accomplishment of maintenance is issued, and the certificate of the maintenance check is implemented. That means this certificate of the maintenance check is the base for the further operation of the aircraft. Let's look at the cooperation of EASA Part 21J, 21G and Part 145 in order to understand the cooperation of engineering, manufacturing and air operation. Engineering, first of all, is accredited according to Part 21J. There, the standards and regulations, the certifications, for example, and the specifications accordingly are stated, and the engineering provides a compliance statement. That means aircraft is compliant with the specifications which are issued by EASA. EASA then releases the type certificate. If that's issued, then again the company, the manufacturing company, accredited according to 21J, which is also taking into account the standards about how the aircraft is manufactured, at least then states the conformity. That means the aircraft is manufactured in conformity with the certified type. That means according to all the documents which had been issued by the engineering. In our case in Germany, the national authority Luftfahrtbundesamt then issues the certificate of airworthiness in German Verkehrszulassung. The aircraft is then put into operation. There again the aircraft is accompanied by standard manuals and also by a definite maintenance program defined by design organization based on in-service experience. For maintenance, which is again according to EASA Part 145 accredited, standards and regulations are of driving factors. Maintenance, repair and overhaul is a major issue which at least finalizes the statement of conformity. After that, aircraft can be put back into operation again. Maintenance according to EASA Part 145, which at least covers CAMO, means that the maintenance organization are allowed to perform all activities only on the basis of approved maintenance data of a design organization. Common maintenance requirements are described in specific documents. For example, the Aircraft Maintenance Manual, AMM, or the Component Maintenance Manual, CMM. Also, Engine Manual or Structural Repair Manual are of major issues in order to provide some scales for maintenance activities for the maintenance company or the airliner and the operator of the aircraft. Those manuals then are designed for one specific aircraft type only. Maintenance also may only be carried out within the officially approved scope. And for this purpose, a distinction is made between three basic maintenance approaches. There is an A rating, that means covering the complete aircraft. Entitled to maintain the aircraft includes also aircraft components, that means, for example, the engine, or the APU, that's the auxiliary power unit, provided they are in the installed state. The B rating refers to the engine rating, entitled to maintain the dismounted engine and APU with associated aircraft components, and the C rating is at least the component rating for maintaining dismantled aircraft components, excluding the engine and the APUs. Documentation, as I already mentioned, is a wide area which has to be associating the aircraft at least, and is issued according to the Air Transport Association specifications. So we have the general requirements which are at least issued by the authorities, FAA, EASA. Then we have the product design requirements. These are the drawings, the documentation from stress department, fatigue department, and so on. Of course, based on that, safety, reliability, and maintainability manuals, the AMM, are issued. Also the certification and the qualification, ACD or SJR, structural justification reporting. And the customer support is at least supported and accompanied by the SRM, the structural repair manual, and the IPC TSM. IPC means, for example, illustrated parts catalog. So coming to an example, we also can see that according to EASA Part 145, maintaining is performed according to a typical interval sequence, which is also correlated to a definite duration and also to a definite effort. So for example, starting out with a drip check, it's just in front of each flight for a duration of half an hour. So it's a quite limited man hour of half an hour. Again, walk around, cockpit checks, visual checks are the typical work steps to be performed. Ramp check, service check, A, B, C checks, and up to D check, which at least lasts for a longer time of 4 weeks, and a typical interval for that is 130 months. And you can see that the effort is quite high, up to 30,000 man hours. That means here the overall of the complete structure and system is performed, contains all the above mentioned inspections, painting and polishing. So just to provide an example, what are the implementing rule continuing airworthiness? First of all, we have a terms of approval. Maintenance organizations are allowed to perform all activities only on the basis of an approval provided by the authorities. These limitations can also be seen in the above mentioned manuals. Then we have the facility requirements. Facilities are provided appropriate for all planned work, ensuring in particular protection from the weather elements. Specialized workshops and bays are segregated as appropriate in order to ensure that environmental and work area contamination is unlikely to occur. Then, last but not least, we have the personnel requirements. The organization shall appoint an accountable manager who has corporate authority for ensuring that all maintenance required by the customer can be financed and carried out to the standards required by this part. This accountable manager shall ensure that all necessary resources are available to the accomplished maintenance. So let's conclude on that. I provide here a set of literature and will be happy to guide you to the next lecture. Well, Welcome to the lecture Managing Maintenance, Repair and Overhaul for Civil Aircraft. Here in lecture 2, I will guide your interest onto the significance of testing concerning maintenance of aircraft. First of all, let's have a look at the relevant certification tests. Afterwards, we will address design philosophies addressing maintenance, and at least I will show you some examples on component tests and full-scale tests. What are the certification tests? Certification tests can be mainly oriented along the test pyramid. You start at the very bottom with Coupeau testing. That means you determine stiffness, static strength, fatigue and damage tolerances, also taking into account environmental effects in moisture and temperature. After that, you are going to manufacture elements, for example joints, shear webs or structural details. If you finalize those tests successfully, the material qualification at least is successfully performed. After that, you manufacture details like stiffened panels, major joints, sections, and are going to test that according to the load conditions and boundaries you define in advance. After that, subcomponents are manufactured like wing boxes, and completing those test scenarios successfully, the manufacturing process qualification is successfully performed. After that, components are tested like wing or empennage or fuselage structures in order to aim for the full-scale aircraft testing. That means also testing the static loads and also fatigue and damage tolerance loads. And at least performing those tests successfully, the full aircraft qualification is accomplished. Let's look at design philosophies addressing maintenance. First of all, we have two approaches. There's a safe life design, and the second one is the damage tolerant design. Safe life design means that we are determining a scatter factor for load level, material, manufacturing process and geometry. At least here we do not determine any scheduled inspections, but that definitely affects material selection, design principles, stress levels with KT factor, manufacturing quality and health monitoring. The second philosophy path is a damage tolerant design. Here we have, first of all, a fail-safe principle. Fail-safe means several items of the structure and the load path can fail. In order to prevent hazardous effects, we can use crack stoppers in order to limit the results and the effects of those local failures, or also we can use the multiple load path philosophy. Crack stoppers and multiple load path philosophy then determines the design principle, the residual strength, which is at least the strength after a single failure occurred, of course also the inspection intervals in the inspection program, and the health monitoring, which also determines that we have a crack growth velocity which is determined in advance and also a significant basis for certification. Of course, for multiple load path philosophy we have to provide that by functional tests. A second potential for damage tolerant design is a safe crack growth, but that's definitely determined and based on a detailed knowledge of material. So material selection is a challenging path. Design principles are of course also determined by that. Stress levels are then of significant item. Initial crack size, critical crack length determines at least the inspection program and also the health monitoring. To show an example for a fail-safe design concept, let's have a look at the wing fuselage attachment of a 328 Dornier 328 wing box aircraft type design. Here, let's have a look at the right side of this transparency. Here we see that we have a 3-layer bracket. Outer layers are aluminum, the inner layer is titanium. That means titanium so far in a undamaged status is not loaded, not covered by any load. It means as soon as an outer bracket of aluminum fails, the titanium will take over the part to transfer the load through the sections. Let's have a look at some potential examples and component tests, full-scale tests. Again, looking at the structural test over a program of the Dornier 328, which could be an example, but which is also definitely transferable to all other civil aircraft testing programs. Here we have the component tests and we have up to full-scale tests. Here you again can see the major items of the test pyramid. But at least we have to perform those 4 test scenarios. We have the static test, we have the dynamic test, we have combined static and dynamic tests, and we have full-scale test specimen. Of course, that's determined by specific boundary conditions. Here we have the extreme load conditions, also including the environmental knockdown factor, which at least takes into account environmental effects like moisture and temperature applying composite structures. In the second stage, we also have to provide and substantiate the reliability and integrity of the aircraft structure. Limit loads without visible damage must be withstand, and life at least is a major item which determines inspection program and at least the maintenance. Here you can just see a test setup for the A400M wing horizontal stabilizer. In the background of this picture you also can have a look at the fuselage of the A400M. This test specimen was performed by IABG in Dresden. Full-scale test, what is the purpose of that? Well, at least we check and verify and substantiate the main load paths, what we at least as engineers determined in advance. Of course, we also have to provide the correct deformation behavior. That means, is the stiffness adequate, what we at least designed and manufactured and assembled. Then the verification of the comprehensive analysis, which is at least gaining major importance in the age of digitization. Strength and rigidity of the overall structure is a very important aspect, again, to provide safety for aircraft operation. Stability behavior, again, another failure scenario which has to be taken into account. And last but not least, the verification of the life requirements has to be substantiated and at least has to be proven that those are in accordance with the requirements issued by the authorities. Here you can see the wing of the A380, again a test setup of IABG. Load introduction is here in red colors shown by load pads and just positioned underneath of the wing. That's a look at the fuselage. In German it's Rumpf fuselage, where you also can see that it's pressurized, so you have to incorporate and implement a specific test load introduction in order to provide the pressure increase within the fuselage in accordance to the outer ambient pressure. The full-scale test usually is concluded by a residual strength test. That means you just load the structure until it will break. That's here in this example performed by the horizontal stabilizer of the Dornier 328 aircraft. And here you can see on the right side of the picture how this structure fails. It's a complete CFRP, composite fiber reinforced plastic structure, incorporated also with repair areas, and here you can see the black patches which are repair patches. So let's conclude on this item, the significance of testing concerning maintenance aircraft. Again, some literature are mentioned here, and I will come to the next lecture within this session. Welcome to the lecture Managing Maintenance, Repair and Overhaul for Civil Aircraft. Here in lecture 3, I would like to focus on the importance of the supply chain within maintenance, especially addressing in the first chapter supplier qualification. We have to take into account different levels of approvals of the supplier. In an upper level, we have the suppliers with approval by a civil authority. In the next level, we have suppliers without the approval by a civil authority. In a third level, the suppliers do not have any approval of a civil authority, a design organization approval, or a certified quality management systems. Then we have manufacturers of articles with their own approval, means type certificate or production certificate, or TSO means technical standard order. On the manufacturing level, we have manufacturer of standard articles, we have manufacturer of on-ground equipment, and we have distributors. Let's have a look at the different levels in detail. Suppliers with approval by a civil authority, these are suppliers that manufacture, overhaul or repair devices, components according to specifications from the type certificate or supplemental type certificate holder and have their own approval by a civil authority as an aviation organization according to 21J, 21G, Part 145. Supplier will have approved design data and authorization from the design holder to manufacture the product. Each time the supplier is involved with a deviation from a certified but undelivered product, supplier must recertify the product under its approval. The supplier manufacture and maintain the supplied item under the supervision of its responsible civil aviation authority. They must ensure that these activities are authorized by the production limitations record, capabilities lists, or at least also operation specifications. Let's have a look in the next step at suppliers without approval by a civil authority. These are suppliers that have documentation provided and approved by the TC or STC holder, that may manufacture components and also overhaul components, assemblies or parts not approved by a civil authorities. The supplier definitely works under the responsibility of the OEM, which is original equipment manufacturer. Usually it's the TC holder, and this OEM approves and the supplier's technical documents, production plans and inspection instructions as necessary. The manufactured products or the tests performed with provided production plans can only receive airworthiness approval from the OEM. So the TC holder must be informed if the approved process is changed, and an approval for the new process must be obtained. So the TC holder must approve subcontracting also. That means he must be definitely informed. The TC holder will monitor serial production by means of routine audits, addressing type of product, production process, third-party monitoring results, and at least quality of delivery. What are the suppliers without approval by civil authorities, design organizations, or a certified QMS? As a general rule, it's not possible to deliver articles to the OEM under those circumstances, but the supplier can be approved on a case-by-case basis for limited deliveries. In this case, OEM Quality Assurance Department will conduct a quality system audit and will approve based on the results. Manufacturers of articles with their own approval. For articles that the supplier owns the design responsibility and is the holder of the approval through the Civil Air Authority, the CAE, of country of manufacture. The supplier is obligated to manufacture the item under the supervision of its CAE and the regulations of its organizational approval. The OEM is to be informed immediately if this approval is surrendered, suspended, or at least revoked. Articles are to be marked and delivered with an authorized release certificate which indicates the approval number. Then we have manufacturer of standard articles. The manufacturer supplier is obligated to comply with ISO 9100 requirements or an equivalent. Articles will be delivered with a certificate of conformity unless otherwise noted. Manufacturer of an on-ground equipment, the supplier's quality system is obligated to comply with ISO 9100 requirements or an equivalent. And then at least we have the distributor. The distributor is responsible for purchase, storage, splitting and sale of products without affecting product conformance ordered by the OEM. The supplier's quality system must comply with the AS/AN 9120, which relates to aerospace series quality management systems based on ISO 9100 requirements or equivalent. So how to control the article and at least the material flow under those aspects? First of all, aviation companies have to take the responsibility for quality assurance and the integration of products that are purchased from suppliers from all over the world and at all levels of the supply chain. Obligations to ensure the compliance of the parts and materials is another major step. Materials used with a specification and a reference to the source of manufacturer and supplier. And a very significant item is the demand of traceability. Means traceability back to serial number or batch number. Traceability of the product development and difference between target status and actual status, that at least also steered and controlled by the configuration management. And at least also traceability of all products from a raw material lot up to the final use. So traceability is relevant and very significant and important for safety critical items that relates to system and structure. And the level of details, how far you perform this traceability, is definitely under the responsibility of the aviation company. Consistent and transparent material tracking requires a standardized process and must meet the high demands placed on documentation management, master data management with correlating base data, traceability to be provided by enclosed certificate. One major item is subcontracting, and here you can imagine you also have to follow some restrictions and consider the requirements. What are the possibilities of the value chain of aviation companies performed by subcontracting support? In-house performance or subcontracting as an extended workbench could be performed and covered by aviation approval of the customer, if that's internally. External performance is covered here by aviation approval of the supplier. But what must be defined? At least the scope of outsourcing, type and extent of aviation approval, the schedule and the milestone, responsibilities, also very important communication lines, which at least determine interfaces and interface information which have to be transferred. Then also the documentation to be provided by the customer. That means, is it approved data? Are there specifications available? Lists, what to be delivered, documentations by the suppliers, that means enclosed certificates, and supervisions of the supplier by the OEM, by the aviation companies, for example, through audits. Again, a list of and a set of literature, and here with this I close this section. Welcome to the lecture Managing Maintenance, Repair and Overhaul for Civil Aircraft. In lecture 4, we will have a look how maintenance and product life cycle are going to interact. Let's have a look at the maintenance tasks. Maintenance tasks are mainly defined by DIN 31051 and subdivided in 4 columns. Here we have the service operation, which at least tries to maintain and intends to maintain the target state. Then we have the inspection, which at least focuses on determination and assessing the current state. Repairing is the 3rd column. Here the requirement heads out for restoring the target state. And the 4th column is concentrating on improvement activities, which means increasing functional safety without changing the function itself. Those maintenance tasks have to be reflected within a quality management system, which is at least based on a maintenance organization of Part 145 according to national aviation authorities. The quality management systems can be influenced and targeted along the requirements of ISO 9001 or 9100 series, and definitely is infected by the authorities according to EASA and Luftfahrtbundesamt. JAA, by the way, does not longer exist here. JAA is a former joint aviation authority by the EASA authority, now superseded. Quality management. Quality management consists of several elements of a QM system. Here we have the responsibility of board of management. We have at least to fulfill and look at and regard customer requirements. Also legal requirements must be considered. Quality assurance strategy is a major task for the board of management to be determined. Then the QM system, what we at least saw on the previous slide, has to be established, and also the quality management assessment. Of course, the planning is a major responsibility of the board of management. Then the operational level, operational management means engineering development processes must be established and documented. Procurement, customer relations, production, and also MRO, which is at least maintenance, repair and overhaul, which must be determined and guided by operational management. Then we have the resource management, which reflects quality of personnel, of material, of infrastructure, also information flow, communication and working environment, which also has to be taken into account by safety issues. Controlling means supervising the processes in order to ensure quality requirements. Risk mitigation is of major task in order to be aware where quality could be failed. Failure management is a correlating and corresponding issue. Data management and continuous improvement are a subsequent discipline for the controlling item. Documentation, you can imagine documentation is requirement for a functioning quality management system. On the basis, you see, we have the standards, we have the specifications, we have production plans, material specifications, and also work instructions. Based on that, processes are described, processes are fixed, processes are defined, and procedural instructions are then issued. And that at least is transferred to operational handbooks, which are necessary also to guide the quality management system. Operational handbooks, which are, for example, the design organization handbook, production organization handbook, or maintenance organization handbook. What are the correlating elements then for product lifecycle management in order to illustrate the interaction with the maintenance? Here you can see a typical setup of a product lifecycle management systems. We have definite interfaces. We have definite interfaces to the engineering, to the supplier, to the factory, and to the customer. And this all disciplines are then headed by and guided by management, which also overtakes responsibilities and tasks within the product lifecycle management. Let's look at the product data management. Here we have definitely the interface to the engineering. We have taken into account the design architecture, the document structure, change management systems, which at least is also followed by config management and the release management items. Production development management is at least adjacent to the engineering department, also guided by and functioned by the PDM. Here for the production development management, we have manufacturing and assembly processes, we have manufacturing data management, we have tooling equipment, we have facility layout, but also we have analysis data management, which is at least provided from engineering to production facilities. A major interface here is the factory and also the digital factory, which is at least also determined by and configured by digital data setup. Material sourcing must be provided by the supplier. That means here we have to assess the supplier, at least also the strategic supplier, which has to be provided on the basis of a certification platform. Then also data exchange is a very important task which has to be performed and delivered to the interface of the supplier. And also change management, where the supplier has to be kept informed how the design is developed. And then also we have to take into account the customer needs. This must be managed by requirements management. Functionalities, configurational aspects has to be considered, and also the after-sales aspect has to be performed and has to be delivered to the customer on the basis of spare parts and services. As I already said, management is heading those different areas and overtakes some responsibilities and tasks. That means portfolio, program, and project management. Risk mitigation is a very significant item which is performed by management and at least guided. Cost control, which is also linked to lifecycle management, governance and compliance, and also analytics and reporting. Again, finally, some literature for your orientation. And with this, I close lecture 4. Welcome to the lecture Managing Maintenance, Repair and Overhaul for Civil Aircraft. Especially in lecture 5, I would focus on the maintenance in the age of digitization. And here we have, first of all, to look at relevant maintenance strategies. Let's again start out with the setup of maintenance strategies according to the 4-column: service operation, inspection, repair and improvement. All those activities are covered by cost aspects, by the direct operating costs, DOC. And these are subdivided and can be subdivided into operational, service aspects and depreciation. Of course, here for maintenance aspects, we have to take into account 2 qualities and 2 scenarios of maintenance. First of all, it's a scheduled one, and the other aspect, which definitely happens also during aircraft operation, is the unscheduled maintenance. In order to rank that, to categorize that, we have to have a look to the evolution of maintenance. First of all, you can operate your aircraft, your system, up to a failure. That means you fix the failure when it broke, or you fix the system when it broke. The next aspect is the preventive approach. It's time-based activities. There you just change the potential system or structure when it's potentially going to fail. Then we have the condition-based aspect, means based on indicators, but especially at this level you already have to work with some sensoring systems, which at least indicates that some failure could happen in the future. Then we have the predictive aspect and the predictive maintenance. So that means action is performed just in time. And last but not least, and which is now relevant for digitization, it's the prescriptive maintenance. That means adjustment of maintenance measures to assure the required maintenance where and when it's needed. Monitoring of the system with the help of Internet of Things in real time regarding the condition of the equipment. And this results in a flexible maintenance strategy in which maintenance is only used when and where is needed. And this type of maintenance is the so-called prescriptive maintenance. So what does it explicitly mean? First of all, let's look at some maintenance scenario. We have a part of the plant maintenance, we have event-oriented, and we have also the integration of a sensoring system for health monitoring aspects in the aircraft system. Usually we have an input from load and usage monitoring. We get, based on that, the possibility to perform diagnosis. Then we have, on a virtual basis, for example, finite element models, damage models, which can at least use to forecast some failure scenarios, some failure occurrences. But what's very essential here, we also need to take fleet data into account for health management, which is event-oriented. If that's successfully installed, also based on these prescriptive maintenance approaches, we have no unplanned maintenance, we have improved operational planning, aircraft is utmost in operation, optimization of downtimes is correlating to that, and the direct operating costs are reduced. So what does it mean? Prescriptive maintenance offers the opportunity to drastically change maintenance practices through case-specific decisions, supporting best action which improves over time based on sensor-related feedback mechanism. And as a part of the cyber-physical system approach, it builds on advanced analytics technologies that enable more customer-centric business models. It also enables the reduction of human input in decisions. And as a first example of prescriptive analytics in MRO planning, for example, production, prove the advanced TRL, that means the technology readiness level, and the significant economic potential, which is documented by studies on MRO work scope planning. With regard to future visions, prescriptive maintenance approaches in business models such as automated maintenance and services, for example, blockchain-based smart contracts related to all maintenance matters. That means self-executing codes in a blockchain that automatically implements the terms of an agreement between parties. This approach can be elaborated furthermore to the usage of reliable sensoring systems, but also the application of validated software codes. With this lecture, I will close my lecturing on maintenance in the age of digitization.
Hello! In today's video I would like to talk about digital transformation and what digital transformation means for the aerospace industry and in particular for Airbus Defence and Space. My name is Peter Wegesser. I'm the Digital Transformation Officer of Airbus Defence and Space. Digitalization is a term that we hear very often and widely today. And actually, what's called digital transformation is, from my viewpoint, the biggest transformative event that we have seen in industrial history. And I would like to explain why I think that this is the case. Actually, digital transformation is a transformation that happens in any industry. It will impact or has impacted every company in these industries, and it will also impact every individual working in these companies, no matter in which function you work in these companies. I would like to give you a couple of examples why I believe this is so transformative. Other transformations have happened in manufacturing or in the office space, but digital transformation changes everything and it happens everywhere. Some examples that everybody knows is, for example, the digital transformation of retail or of entertainment. If you look at retail today, the whole ecosystem of retail has completely been transformed by companies like Amazon within a very short time frame of 10 years. And this is not only impacting all the companies who are active in the retail value chain, but it has significantly changed the consumer behavior and probably will also continue to do so. The same is true actually for entertainment. If we look at the transformation phase from, well, digital media, from CD-ROMs, DVDs, to downloading digital content, to now streaming digital content, this is also a transformation that has not only changed the ecosystem, has changed the customer behavior and the way how we consume digital media. And, of course, it has also changed completely the landscape of companies participating in that. Now, these are two examples which are early adopters of digital transformation. I firmly believe that this digital transformation will take place in every industry and in every company, so I encourage everybody to embrace digital transformation. After the introduction to digital transformation in general, I would now like to talk about what does digital transformation mean in particular to Airbus Defence and Space. If we talk about digital transformation in Airbus Defence and Space, we usually look at two dimensions of digital transformation. One dimension is where we ask ourselves the questions, how do we get significantly better at what we do today? And what do? We design, we build, and then we help our customers to operate extremely complex products like aircraft, like satellites, and many other really cool things. The challenge in these products is that they have an extremely long life cycle of up to 50 years, from the first idea for that product, the design manufacturing phase, and then we have an extremely long operations phase of these products. The digital transformation in this core process, which we call product lifecycle management, is really answering the question, how do we produce, develop the next product in half the time, half the cost, and at a significantly higher level of quality than the last product that we introduced into the market. And this is a question where we need to work on continuous process improvements, and some of these process improvements are pretty significant improvements, because we will not write libraries of specifications anymore and then develop against these specifications, but we completely change our processes, starting from a model-based systems engineering approach, going into concurrent engineering of the various engineering disciplines, mechanical engineering, electrical engineering, software engineering. We will, in the future, more and more validate and certify our products in the virtual world. So that includes, of course, all virtual testing simulations before we build the first real product. And actually what we do for the product, the virtual development of a product, is true also for the design and creation of our manufacturing equipment. This will also be done completely in the virtual world. It will be simulated, and the manufacturing process is also completely a digital process in the creation phase. So at the end, we create digital models, 3 digital models, which we also call digital twins. A digital twin of the product, a digital twin of the manufacturing equipment, and a digital twin of the manufacturing process. Once we've created these digital twins, we have simulated all this, done a lot of certification also in the virtual world. We are really at the point where we build up our manufacturing equipment and finally manufacture the product. But this is not the end of the digital journey. Once we transfer the product or sell the product to our customer, of course, the most significant part of the life cycle of this product starts. The customer starts to operate the product. The product starts to create lots of data through that life cycle, which we feed back into our digital model. So we close the digital loop from the real product to the digital model, compare the behavior of the real product in operation with all of our simulation, which helps us to predict potential errors in the product, or even improve our digital models to design an even better product in the next phase. This process is pretty disruptive already for us as an organization, because it totally changes the way we operate. It changes the way how we work together between various engineering disciplines. It very much changes the way how we cooperate between engineering and manufacturing. And it very much changes the way how we work together between our customers who operate the products and various internal departments in Airbus, like engineering, manufacturing, and services. This will also have an impact on our organizational setup in the future that needs to be adapted towards these new business processes. And all this is being done following these principles that I introduced early, where we ask ourselves the question, how do we get to market faster? How do we get to market with an even higher quality and a better cost position? Now, this is the right side on the slide that you can see. And this is called incremental improvements. Incremental for us means that we do not change our business model, but we stay within the boundaries of our existing business model, but try to get better on a daily basis. Now, this is the one dimension of digital transformation, that we optimize our processes end to end and support these processes with the best-in-class tools that allow us to build the digital twins and then a product that behaves like the digital twin. On the other hand side, we also need to look at the second dimension of digital transformation, which is even more disruptive and which is really shown on the left side of the slide in the background. Here, we have to ask ourselves the question, is our business model still sustainable? Or do we need to find new ways how to meet our customers' expectations? Do we have to develop completely new value propositions? Do we have to take our products to market in a completely different way, or address completely new customer groups? So this is even more challenging for all mature organizations like Airbus than the first dimensions, because it requires much more an outside-in thinking. And I would like to share a few examples where competitors are already disrupting our business model today, and also areas where we try in Airbus Defence and Space to disrupt our own business model. What you can see on the slide is an example of a competitor, SpaceX. SpaceX has kind of revolutionized the launcher industry by creating a business model of reusable launchers. This is something where most experts believed for a long time that this is not financially sustainable. SpaceX has proven to all these experts that it is, and that they can get into a much more competitive position with this approach. This is very disruptive, and and Airbus is more reacting to this competitive threat. There are a couple of other areas where we believe that we can proactively drive this disruption, and I want to mention a couple of examples here. Airbus has been active in satellite imaging for a couple of decades already, and this is a business which was mostly created for government customers. And with our capabilities of about a dozen satellites that we have in orbit with very sophisticated imaging capabilities, we are deeply convinced, and we see that from the customer demand, that we can commercialize these capabilities also outside of our existing government business and going into many commercial areas like retail, like insurances, like agriculture, and commercialize a capability to a totally different industry, which requires different technical systems, but also a different go-to-market approach. This is why we have created a startup in Berlin that we call Up42, which uses these satellite imaging capabilities, but takes them to market in a non-government, in a non-defense industry, which also requires a completely different approach how to partner with an ecosystem that is being created. And of course, interacting with customers that we had never interacted before. This is, of course, an approach which completely creates a new business model and a completely new value stream and business stream for Airbus. Two other examples that I would like to mention. All the world is talking about journey to cloud and how the use of public cloud services significantly improves IT operations. Now, in our defense business, we have the same challenges to get more productive every day, but for sovereignty reasons, we cannot use any of the public cloud solutions. This is why we have developed at Airbus a private cloud platform, which we call Infinity, which very much is being operated like a public cloud. The commercial model is very similar like a public cloud. It's a consumption-based model, which we use internally to significantly improve how we provision IT services within Airbus Defence and Space. And we now see that this is also being asked for from our defense customers, but also more and more emergency responders and other critical industries are very much interested in using this cloud, which meets all sovereignty and criteria that we have in Europe. And lastly, mentioning one example where we also go into a completely different market, where we provide aircraft position information in order to optimize aircraft routing, aircraft separation to customers like airlines and air traffic control, where we are going more into a software or data as a service business compared to our classical business, which is selling large and complex assets. And AirSense is one of these startup activity which also was started 2-3 years ago and is already creating now significant revenue for Airbus. So if you look at this second dimension, I hopefully was able to show that this is not only or digital transformation is not only helping us to optimize and significantly get better in our established business model, but it also allows us to create new value streams, new revenue streams, and at the end of the day, new business models that augment our existing business by completely new value propositions. I would like to summarize. Digital transformation is essential for the future of Airbus and of course also for all the other industries. So I would encourage everybody to fully embrace digital transformation and look at digital transformation as an opportunity. I also would like to point out that most people initially think digital transformation is about all these digital tools that we introduce. But this is only one aspect, and usually this is not the hardest aspect or challenge of digital transformation. Digital transformation is very much about how do we find new value streams, how do we create new revenue streams, how do we optimize existing business processes, how do we get significantly better at what we do, how do we embrace the change of way of working, how do we embrace the development of people, how do we upskill our organization, and all this whole package is really relevant on digital transformation, and this is what needs to be tackled by any organization. This is my short introduction into digital transformation at Airbus Defence and Space. Thank you very much for your attention, and I wish you all the best for your digital transformation endeavors in the future.
But we always have to remind ourselves that we are not only consumers of data, but also sources of data. So our whereabouts, our details, and so forth are also of interest for others. And we feel that we cannot always really protect ourselves from that kind of, well, data greed, if I may say so. And I see that we all still have to get used to those roles, and we cannot say that we already are very proficient in that.
Digitalization had a big impact already on communication. So how you communicate, how you can exchange data, this drastically increased on private as well as on business.
Many things are becoming easier. For instance, booking a plane or booking a train. Some are more complicated, but at all, things are very, very fast. And this is really a challenge.
Digitization has really a good impact on my life, so I reach now really a paperless office, and I have all my documents available online. I can access them from my office, at home, at the airport, in the train, and that's really something which simplifies my work life and makes me really more efficient.
So by digitalization, I think we have much more data available, much more information. We have access to so many things, but of course we have to deal with this. We have to compare it, we have to work with it. And so I think it's a big advantage, but it's also a challenge. Things are more complex.
Digitalization makes my life easier. I'm working at the university in Bamberg in the north of Bavaria. I'm working for a company in Munich in the south of Bavaria. I'm quite often on the road, I'm in a customer's place. So it makes me easier to access all the information, the documents, the processes, the tools I need, and I can use it on any location where I'm being, and I can use it on any device I have. So business life makes it quite easy. But also personal life. I stay in contact with my friends, with my family, with my child, with my grandchildren. So it makes the situation quite easy.
We see a dramatic evolution of functions, actually. Well, actually all over the place. You can buy such model aircraft drones already that are really depending on, well, digital flight control stuff like that. But even further on, there will be much more opportunities to use such systems in our daily lives.
The risks and the challenges of digitalization is in the changing kind how we work and how we perceive the world. all these things will change. Our brain is built for a situation some 10,000 years ago, and we adapt to the new situation. I'm sure we can adapt to this, but we will adapt, and this will change things. Work environment, workplaces, the kind of communication, the kind of perceiving the world, the kind of expectation, what we can expect, what we will do, what we'll need, how our goals are, how can we satisfy our needs, will change.
Digitization requires an increase in security in order to protect the privacy of the citizens and to ensure the proper use in various safety-related applications. Therefore, one of the big challenges in the future is really to find the right means in order to increase security.
In general, I guess we have to consider that on the one hand side, to share information and knowledge very easily is quite good. But we also have to keep our knowledge somehow separated.
I see a certain risk that a number of papers and publications and statements are now available online, and it's slightly more difficult to have an overview on what is important and what is not.
Welcome to the lecture Space and Digitalization. My name is Professor Förstner. I'm from the Bundeswehr University here in Munich, and I am the head of the Space Technology Institute. Here today we are at the Space Test Centrum of IABG. It's the national largest test centrum, and for example in the back you see a big test chamber where space environment can be simulated and satellites and equipment can be tested. The lecture Digitalization and Space is divided in 4 parts. We will start with a general introduction into digitalization, followed by application and services, so looking how the services and the products from spacecrafts, from satellites are influenced by digitalization. The third part will have a look at manufacturing, development and operation of satellites, because not only the products of the satellites, but also how we design and build satellites will be different in the future due to digitalization. And the last part is about new risks and threats which are introduced by digitalization. Of course, also this we have to have a look and be aware of all these new risks we are facing. So let's start with a general introduction. First of all, I want to point out what digitalization is not. Digitalization is not if I'm using a computer. In the spacecraft development business, we are using computers for many, many years, digital data for simulations, but this is not what digitalization means really today. So for example, if I run a simulation in my design process, I have digital data, of course, from computer simulations. I put this data in a Word document, all digital. I send it via email to a colleague. He reads it and maybe copies these numbers he needs into his own simulation. So everything is digital, but still this is not digitalization. This is just using, let's say, digital devices for processes that we have done also in the past, maybe with paper. So digitalization is more than this. Then another thing that's important to mention in the beginning, you will in the literature encounter 2 types of words. One is digitization and the other one is digitalization. It's a small difference in spelling and it has also a slightly different meaning. If you hear about digitization, it basically means transformation of analog data or physical items into a digital representation. So if you scan a document into Word with a scanner, this is digitizing a document from paper into a digital representation. But digitization does not stop at this point. You can go further and maybe using a text recognition software which recognizes the scanned words, and then you can use a software maybe to count words or search for a specific word in the document. So digitization means transformation from analog data, from physical items into a digital representation, and applying, if needed, some automation. So having automated processes. That's digitization. If we talk about digitalization, it goes beyond digitization. Digitization is a prerequisite for digitalization, but digitalization also means that you are changing your ways of interaction, your ways of communication with your colleagues, with your customers, because you are using digital data. So you need digitized data, and then your working flow is changed completely. You are not doing as you would have done it before. You will change your workflow completely. An example could be if I want to order a book today, I take my mobile phone, I can unlock it with my fingerprint. So this is already an interaction between physical and digital items. I go to the Amazon app. I get already offers due to my past ordered books. It has been analyzed what I like, and then I get proposals which books I may like and want to buy. So I want one, I click on it, I buy it, paying with PayPal, all digital, and eventually it's shipped and maybe in the future even delivered by a drone. Or if I'm all digital, I order the ebook and can read it on my mobile phone. So this is an all digital process, but it's also a digitalized process because it's a completely different way of buying a book than it was 20 years ago. So that's roughly the difference between digitization, digitalization. Digitalization is the integration of digital data, of humans, of manual processes in a mix, but with a newly adapted workflow or process. I want to try to visualize a little bit what digitalization means. And therefore, let's consider 3 items. We have physical items, physical entities, the physical world around us. They are the humans, we interacting with the physical world. And since the invention of computers, we also have the digital world or the digital entities. And these 3 entities and the relation of these 3 entities is changing and has been changing over time. And this is what I want to show in a simple sketch, in a simple model. So let's start. We have the physical items, and we as humans, we always had some connection to the physical items, interaction, of course. We are living in this world, and then computers have been invented, and we have the digital entities. First, we had a relative, let's say, weak interaction with the digital world. We were using computers basically to do massive calculations. The computers could do much faster than we humans. And we could call this the age of calculation. That's basically what we used computers in the beginning. There was a rather weak interaction in the beginning between the digital entities and the physical entities. Then, with the introduction of more and more computers, the internet was invented and was spreading over the world. With new computers, smartphones, tablets, we got a more and more connection all over the world via the internet. And this led to the fact that these 3 entities basically were coming closer together. And we can call this actually the age of networks. That is now the humans, the physical items, and the digital entities were coming more closer together, and especially we humans were much more interacting with the digital world, so we had a very strong interaction with the digital world in the age of networks. There's of course still the connection between humans and the physical world, but also more and more we had a connection between the digital world and the physical world. So this was and still is the age of networks. And now what we see currently, a transition. The networks are established in a good part of the world, not all over the world yet, but now data become more and more important. And we can call this actually the age of data. So data, some say, is the new oil. This is where you can make lots of money if you are the owner of data, like Google or Facebook. They earn a lot of money because they own data. So what's happening in our model, if we look at this new age of data, we are here, the humans, we have the physical items, and the digital items are now almost blending with the physical and the human world. So we have strong connection now between all these three entities, and this is basically what currently digitalization means. This blending of the physical world, of the humans and the digital world. This is where we are. Maybe just a brief outlook what comes in the future. I mean, nobody knows, but if we look at the model, there's something that still could happen, and that is, if you look closer, the humans and the physical items are not yet blending, but in the future this may happen. So also the blending between the physical items and the humans may take place, and we see this already by first attempts to implant sensors into the human body, which then transmits blood pressure or something like this. So I guess maybe in the future we may become cyborgs and we are all connected, and this is maybe then the world and the internet of everything and everybody. So digitalization, of course, depends on technology, and there can be three types of technology we identified which are crucial for the future digitalization of industry and the world. First of all, this is technology which allows the interaction between the physical world and the digital world. This is things like Internet of Things that is building up slowly. 3D printing, so really transferring a digital model into a physical model. Sensors for data collection, of course, are important to build a database. Virtual reality, augmented reality helps us to interact with the digital world and the physical world. Robotics clearly is the technology needed. And now very important is the technology of artificial intelligence, which of course is also gaining a lot of momentum currently. All this will bring physical and digital world together, and also have the effect that we go from automation to autonomy. So our equipment will become more and more autonomous and maybe able to do decisions on its own. The second technology which is needed is related to data integrity. Why is this the case? We are living in the age of data, of digital data, and one thing compared to analog data is that it is much easier to fake or to modify digital data than it is with analog data. So what we need is to be able to trust our digital data is technology which really guarantees the integrity of our digital data. And therefore technologies like blockchain or quantum cryptography, or in general, cybersecurity technology is very important. And I believe that this is one of the most important technologies to really implement digitalization, because if we can't trust our data, we can't use it for our daily life and also for safety critical applications. And then the last group of technology, which for sure is relevant for digitalization, is all the information and communication technology. Why? Because we have to handle huge amounts of data, and we need the technology to handle the data, and we need technology to transmit the data. And therefore broadband communication, 5G is important, laser communication with high data throughput is important, cloud computing will be relevant in the future, big data analytics, storage, mass memory technology to store all this massive amount of data will be of high importance. And also of very high importance, and this relates to space, is communication satellites. Communication satellites are not only affected by digitalization, but communication satellites and satellites in general are also an enabler for digital technology and digitalization, because in particular communication satellites are a very powerful means to transmit data all over the world. And therefore space and the space sector is also an enabler for digitalization. Coming to the space sector, it must be said that the space sector in terms of digitalization is maybe a little bit behind compared to terrestrial industry. There's industry here on Earth which is much further, let's say, in this process of digital transformation. But space, the space business in general is a quite conservative business. It used to be in the past, and therefore the processes are a little bit slower, but it started. So the digitalization finds its way into the space sectors, and all areas are affected. Products, processes, and also business models are changing due to this transformation. And as a result, we have changing paradigms. Paradigms which were valuable in the last decades have to change. New ways of development, new ways of manufacturing, new ways of operating satellites, and also new ways of how we distribute our services, and also new services, completely new services which were not possible without digitalization. And let's say the core of digitalization is always user-centric, user-adaptive services and applications. And satellites in the future will just be a commodity to provide the relevant data to deliver these new services. So this shall be the end of the first introduction of the digitalization and space lecture. And in the next part, we will have a closer look on the application and services and how they will change due to digitalization. Welcome to the second part of the lecture. And in this part, we will have a look how services, space-based services and products are changing due to digitalization. As pointed out before, digitalization is heavily based on data and processing of data, and it is user-centered, user-adaptive. This is the business of the Silicon Valley, and I like to call this the Silicon Valley approach, which brought us many disruptions in the terrestrial field. We saw this with taxis and Uber, we saw it with hotels and Airbnb, books, Amazon, news, the news business with Twitter, and so on. There's a long list of businesses which really have been disrupted by new services, user-centered services due to digitalization. All these services are based on data and processing of this data with algorithms analyzing this data and then providing services to the users, to the customers at any time in any location. So this is the business model, and this is where these companies make the big revenue with these services. And this is a point where space and satellites come into the game, because satellites are very good means to collect data, Earth observation, or to transmit data with communication satellites. And these companies from the Silicon Valley, basically, they realized, okay, these communication satellites, they are a perfect means to connect the world, because they want everybody to be connected to their computers to collect all the data and make money out of them. So they entered the space sector, but they entered it with their own spirit, rather coming from the information and communication technology field with its fast technology turnarounds, agile projects, and of course also new ways of financing projects. And they entered the space sector and basically were changing the way business is done, introducing new business models, and also now the established players in the space sectors are realizing that they have to change and adapt to this new way of doing business. And we can see this, for example, in a vertical integration of the market, that spacecraft manufacturers not always sell the spacecrafts, but sometimes keep them and rather sell the data of the spacecraft, because with this so-called downstream services and the data, you can sometimes make much more money than just selling the spacecraft. So this is how new space was born. This is what we call new space, when the young and wild guys from the Silicon Valley basically entered the space sector and really changed the way things are done. So the focus is on services, as said, and these services rely on heavily processed data. So nowadays the user is not interested in raw data or something. He's interested in derived information, and this derived information, of course, is a difficult and complex task to transform data from satellites, maybe data from other sources, to the service, the information the user wants. And to do so, we basically need a translator, a middle layer, that is between the raw data coming from the satellites and the users. This layer, this middle layer, needs to know what the user wants, but it also needs to know what satellites can provide in data, and it needs to know how to transfer this data by adding contextual additional data maybe, so that the service for the user can be produced. And we see this in the market, that many companies are currently starting up and have been starting up also in the recent years, which exactly serve as this middle layer, as this translator between the pure scientific or raw data and the user, which just wants the service easy to use, plug and play. And what comes also, what we can see is that data from different sources are integrated. And this integration, what we call multimodal data, I think is even pushing more the limits what we can do, and improves the performance and the usability of these services, that we don't not only use data from satellites, but we combine them maybe with data from a network of sensors or data from aircraft and so on. So this data fusion is a very important task for this middle layer, and producing more and more information that is useful for the customer. The technology is improving for doing all this. For example, information technology, computer processing power, but also artificial intelligence is improving a lot. But if we talk about satellite data, there's also, in addition, some other characteristics which are highly relevant, so that we have suitable data. And what is relevant? This is age of the information, how old the data are, what's the quality of the data, how reliable are the data, what's the coverage, and how available are the data. So this is really a quality characteristics of data coming from satellites, and only if this is adequate, they can be used for these new services to fuse maybe with other data from ground-based sensors and services. For example, Earth observation satellites produce a lot of data, even nowadays, terabytes of data every day. Communication satellites transmit a bunch of data every second all over the world. And we have also navigation satellites, which give us many, many information on localization, but also on timing. And therefore, we could also say that data is the new oil, but satellites are the drilling rigs and the pipelines to get the oil and to transfer the oil to the places all over the world. So, but due to this new approach and the high agility this business is needing, we have to change our approaches, which were established in the last decades in the space sector, and we have to change these approaches. We need more flexibility, we need more agility, we need more reactivity of our business, of our satellites, of our payloads. So this business, they don't want development cycles of 5 or 10 years. They want short development cycles, a short time from starting of ordering a satellite till deployment in space or in the orbit. So we need short life cycles, we need low cost life all over the life cycle. Of course, we have to bring the price down so that it is affordable for many people in the world. And due to this, we see a change in how missions are done. What we first of all see is that there's a trend from one big can-do-everything satellite to smaller satellites. So rather than having a multi-instrument, multi-purpose satellite which can weigh several tons, we see a trend to smaller satellites which are more specialized. And at the same time, due to the fact that the satellites are smaller, less complex, which makes them cheaper and also faster development cycles are possible, we see that we have not only smaller satellites, but smaller and more. So we go from one big to many small satellites. That's basically the trend we are seeing. And going from one satellite to many satellites has some significant advantages. We can have fractionated systems, distributed systems, and for example, improving performance due to more sensors in different locations. And this, what I like to call network dynamic systems, have also advantages in terms of flexibility. We can scale the system by adding or removing satellites. And since the satellites are small, launching them is also not too expensive. You can use smaller launchers for them. It's a good maintainability. So if there's a bad performing satellite in the constellation or a failed satellite in the constellation, we just replace this satellite with a new one. We can gradually update our constellation with new technologies. So gradually replacing one satellite after the other and still having an operational constellation, which of course is much more difficult with the big satellites, which are almost old when they are launched because we have maybe 5 years of development time. And with these smaller satellites, they can be much more reactive in changing markets. And as said, this is a user-adaptive market. These constellations are robust. So if I have hundreds of satellites, if one fails, the mission still can go on and maybe even without any degradation in performance. So it's very robust, these missions. And due to this, we can also accept a little bit higher risk for the single spacecraft. If we have a one-of-a-kind spacecraft, it must be very clear and very sure that it is working. If we have hundreds of small spacecrafts, we can allow a little bit a higher risk for these smaller spacecrafts. And we can do with such many spacecrafts, mission architectures, we can do things we can't do with a single spacecraft. For example, doing a sort of tomography with clouds using 2 spacecrafts and detecting the shape of clouds, for example, like in computer tomography, you know, from medical diagnostics. So this network dynamic systems, formations, swarms, constellations, however you want to call it, they allow us to react much better to the user adaptive market, to changes, what is needed on the market. This is a big advantage, and they are also flexible. With many, I have a good coverage, and I have probably also a lower age of data, because with many satellites, I can revisit several points on Earth more often than with a single spacecraft. So there are several advantages in this transition from going one big satellite to many small satellites. So I want to give you an example now how constellations can be used to reflect the requirements of the users, and this is now an example for an Earth observation mission, a constellation of just 8 satellites, so a quite small constellation. And if I, for example, want to have a high spatial coverage, so really flying over all points on Earth, maybe within 1 day or 2 days, depending on my requirements, I can use such a constellation. This is a simple example, just 8 satellites flying around Earth. And if I now switch to the ground tracks, so this shows the lines where the satellites have flown over points on Earth, and this is now just 24 hours. So we see the coverage of these 8 satellites which I saw around Earth in their specific orbits. So this is now 24 hours, the coverage over 24 hours, and you can see that within 1 day we have quite a good coverage with just 8 satellites. It's a very small constellation, but I can maybe take pictures of almost all points on Earth if I like. So this can be one application, but maybe the user says, I'm not so much interested in every point every day, but rather in one point, but maybe with a short time gap in between. So a sequence of pictures, maybe with just 20 minutes time period in between. So you would design your constellation a little bit different, and I show this here. So this is a constellation of just 4 satellites, and they are basically following each other. You have to adjust the orbital planes a little bit due to the rotation of Earth and drifts of the orbital planes, but this is the task of the mission designers to come up here with the best solution. And if we now look at the ground tracks of this constellation, you see that the satellites basically follow each other and fly over the same point 4 times, because we have 4 satellites in this constellation. So you saw there's the first satellite taking a picture, and then the next 3 satellites also flying over the same spot and can take a picture of the same spot. So you have a high revisit time, how we call this, and a small temporal gap between pictures. If you want to combine this, if you are a customer and saying, okay, I want a global coverage within 1 day and a high temporal resolution, a high revisit time, revisit frequency, then you have to combine, for example, these 2 types of constellations. Of course, this results in more satellites required that are in orbit. Another challenge in such a type of constellation is that you have to transmit a huge amount of data. If you go into this direction, that you really want to have a picture of every point every day on Earth, you generate a huge amount of data, and this needs to be handled, which is quite difficult. There is this trend going in more and more temporal resolution, higher resolution. That means higher revisit times, but maybe less resolution in the images. So we don't need the 10 centimeter resolution necessarily, but rather 1 meter is enough. But I want it with a very high repetition time. This is really the trend, what can be seen, especially from the new players, the Silicon Valley guys, so to say. They are pursuing this direction, and maybe in the future we will really have a sort of a permanent vision of our globe. And we also see already that satellites have the capability to take short video clips. So it's not just still images anymore, it's also short video clips from space of certain spots on Earth. So eventually, maybe in the future, we have a total coverage and real-time video of the globe every day at every time. The challenge, of course, is the huge amount of data they generate. If I really go to this point where I say I want any point any day, means I can take a picture of any point on Earth at any day or every point every day, then of course I generate a huge amount of data. And this is a big challenge, of course, for these constellations to transmit all this data to the ground. If I have this data available, I can now generate this added value, this derived information, which is eventually interesting for the user. The user, of course, is not so much interested in the raw picture. We see that with Google Earth, we can have this nicely every day, but of course, the paying customer is interested in services and derived information. What could this be? Just as an example, I could make pattern analysis of traffic, how ships are moving, how cars are moving. I can then add contextual data, which type of car is this? Is this a truck or a small car, a train, and so on. And examples of services which are already existing, so this is nothing coming in the future, this is already existing services, is for example that I count cars on parking lots of retailers. And over the day I can see if the parking lot is more empty or fuller, so I can actually analyze how many customers are in the shop over the day. So this is really something that is used nowadays as a service and sold to customers, this type of analysis. We can gauge the filling of oil tanks. Big oil tanks, they have a lid which goes up and down depending on how much oil is in the oil tanks. This can be seen from space. And if this is done globally, we actually know how much oil globally is stored, and we see also how much oil is sold. And if I track the ships which transport these oils, I may even know where this oil is sold. So this is also another service currently offered. I can track traffic, as said, of trucks to regions or to an industrial facility, and counting how many trucks are coming to this facility or leaving this facility. And by this, I know how good the business is running for this facility or what's the economic strength of a region by just analyzing transportation traffic with trains, with trucks or aircrafts, depending what I'm looking for. Another example is that I can monitor construction sites. If big buildings are constructed and built, the competitors could check how good the others are doing, or they can supervise or monitor the progress of their own construction sites if they are distributed all over the world. So this is another application of this Earth observation data together with other data. Again, data fusion, data analytics is very important. And again, the cost play a role, and the availability, how old the data are. Usually the customers are more interested in actual data than data that is 5 weeks old. So this all needs to be balanced, and this is the big challenge for these new businesses, these companies who are selling these services, to find the right balance and what the customer really needs. As I said already, connected to all this is huge amount of data, and communication satellites are a very good means to distribute this data all over the world. But this, of course, results on new requirements. So we need high bandwidth on the communication satellites. We need low latency of the data. It should be quick, the transmission of data, and we want global connectivity. Otherwise, Internet of Things or machine-to-machine communication is not working if we don't have this global connectivity or hyper-connectivity, as we may call it. So the goal for communication satellites is really connect every point on Earth with every other point, or every device, which is millions or billions of devices, with any other device every day at every point in time. This is a big challenge because we need a global coverage. Each device has to see at least one communication satellite. We need satellite-to-satellite communication to transmit data from one side of the Earth all the way to the other side of the Earth. And this is where the so-called mega constellations come into the game, and you probably heard of them. OneWeb or also SpaceX wants to launch these mega constellations. And these mega constellations are communication satellites. They are there to connect the world. Why? Because these companies like Google, Amazon, Facebook, they make their money because the world is connected, and all the data that are transmitted, of course, are analyzed, collected, and then used for services you are all aware of, I guess. Therefore, satellite communication is an enabler for digitalization. It is highly important for networks of sensors, for autonomous mobility. If I want to introduce autonomous cars, they need connectivity to the internet, to servers. They need satellite navigation data. So autonomous driving, autonomous mobility in general is highly dependent on space segments, being it navigation satellites, being it communication satellites, or augmented services with traffic advisories from real-time images from space. So there's many connections. Communication satellites can serve as a backhaul for mobile communication or as a redundant communication system in times of disaster where the terrestrial infrastructure is destroyed. Space communication still works. If you have a terminal, a space mobile phone, so to say, you still can communicate via satellites even in a disaster area. So it has a high relevance, this sector of space communication, in particular for resilient, highly reliable connectivity like required for safety critical services. And this finds its way already in the technology of communication satellites. We see a trend going towards software-defined functionalities on communication satellites, like software-defined radio, you probably heard already, but more functionalities will be more and more, if possible, defined by software rather than by hardware. Why? Because this gives a higher flexibility. With software, I can upload updates and then change my software. And this is exactly this user adaptive approach we need, that we can change basically the functionality of our payload if the market is changing. We see technology of high data rate throughput, 5G in space, or laser communication, a very important topic currently, really using light and lasers to transmit data between satellites or from satellites down to Earth. And the last technology which is of high importance and has to find its way onto the satellites is clearly ensuring the integrity of data, as pointed out already in the first part of this lecture. Blockchain technology, quantum encryption, cybersecurity technologies are highly important so that we can make sure that we have a high integrity and a high trustworthiness of data that are transmitted over the satellites. Welcome to the third part of the lecture, Space and Digitalization. This part is focusing now on the manufacturing, development, process and operation of satellites. Also this is changing, not just the services provided by satellites, but also the way we develop satellites and the way we operate satellites in the future. There are new requirements due to the new missions, as been seen in part 2. And these new requirements are mass production, fast development times, short times from development until orbit deployment, effective development management, and low cost. So these are the requirements for the manufacturing of these small but many satellites. But also on the operation side, we have new requirements coming up. We have to operate hundreds or even thousands of satellites simultaneously, which is a big challenge for operations. In-orbit upgrade, in-orbit update might be necessary for these satellites. Low latency data delivery, so the operators have to deliver the data very quickly to the users. And again, low cost. Operations is still a quite costly thing in space, in the space business. And also for hundreds and thousands of satellites, of course, the cost per satellite in operations has to come down. To mention another aspect, which is not the focus of this lecture, but to bring up all these satellites, we also need the launchers that are capable of doing this. And we currently see also a quite dynamic market in the launcher business, and many companies are looking into so-called mini launchers. That is, we don't have not just the big, huge rockets, but also smaller rockets, which can launch these small satellites much more rapidly, much more flexible and cheaper. So this is a reaction of the launcher market to this new market for many small satellites instead one big satellite. This is a dynamic development ongoing, which is not the focus of this lecture, but it should be mentioned because it is a follow-on effect of the digitalization. If we look on the processes, how classically satellites have been developed, they are huge, they are complex and one of a kind. Of course, we have to make sure that they're really working, and therefore many tests are done for verification, for validation. And here I am in one of the largest test centers in Europe for space simulations and testing of spacecraft. And this is necessary to really make sure that this big one-of-a-kind spacecraft really function flawlessly in space for 10 or 15 years without maintenance. There's no chance to do maintenance. But this is costly. And it is clear if I'm building hundreds and thousands of satellites, I can't go through this process of testing each satellite on each level. This would just be not possible. So we need new approaches in designing, developing spacecrafts, manufacturing and testing, which means verification and validation of the satellites. All this needs to change, and digitalization basically has found its way already in this area, which we call Industry 4.0. So on the terrestrial industry, this transformation, this digital transformation is already gaining momentum, and the business is changing, and this Industry 4.0 for sure is what the space business also has to do and started already to do. This topic, Industry 4.0, is a huge developing topic, which is far too much to cover here in this lecture, which is of course focused on space. So I encourage you to look through the internet. There's lots of material in the internet, and there's also in this lecture series, there's a lecture about Industry 4.0. So please also have a look at this lecture there. I will just give some indications what it could look like if this transformation from Industry 3.0 to Industry 4.0 is taking place. And first, of course, it depends on technology. Only if we have the technology, which is a digital technology, part of this digitalization process, only then we can do this transformation and In the graph on the screen, you see all relevant technologies displayed, which is Internet of Things, machine-to-machine communication, cybersecurity, augmented reality, big data, autonomous robotics, additive manufacturing, 3D printing, simulations, very important, especially important for us in space, because many things we can't test, we only can simulate. System integration, which equals to systems engineering. The systems becoming more and more complex, combined cyber-physical systems, and we need a very good, strong systems engineering to handle these systems. And another technology very important is cloud computing in the future to handle all the data. So this is the technology we require for our transformation from Industry 3.0. As you can see here on the slide, on the screen, that's the old industry as we have it now. It is hardware-based, functions are bound to hardware, and there's a hierarchical communication, and the products are more or less disconnected from the production process itself. So that's what we have. That's a classical 3.0 industry, but the transformation to Industry 4.0 is this going to networks, connecting the products, connecting the production process, connecting the users in a network. And you see what we have here. We have functions distributed over the network. We have smart factories which are connected to smart products. In the future, we have no hierarchies really. We have rather a network. And this is how the transformation will look like once it is fully done, going from Industry 3.0 to Industry 4.0. How can this be implemented? If we look at the next slide, I won't go into the details. Please take your time offline, so to say, have a closer look into these graphs. There's lots of information in them. But as you can see, it's basically the first step is connecting unconnected things, having sensors and actuators, bringing together physical world and the digital world. Then we have data that need to be managed in the production process for the smart factory. So we have these internal services, internal systems. We have to build up on digital devices, and connectivity is then the next level, having advanced services, applications, new capabilities which are developing from these opportunities the digitalization is giving us. And out of this, of course, we can develop new businesses due to this connection between the production process and the products. So these smart products will have a connection to the company who produced it, so we can have this Internet of Services, for example. So there's new things happening if we implement Industry 4.0. To do so, we also have to introduce new development approaches, new design and development and manufacturing approaches. So what does it mean? We have, maybe in the future, we have digital product lifecycle management. Very important. The whole product lifecycle is really managed in a digital way. We have agile processes, being flexible. We have artificial intelligence supporting us in optimization of design. Digital models, digital twins, connected digital models, model-based product definition. So you see the borders between physical world and digital world really blending and disappearing in this Industry 4.0. We may have 3D massive model visualization, virtual assembly, integration and test, how we call it in the space business, AIT. Really first trying it with virtual reality to assemble the spacecraft, and only then really building the real thing. And then also for dealing with the complexity of the systems, we may have this transition to model-based, simulation-based systems engineering, which is this discipline in engineering which really is responsible to handle complexity of such systems. The new design principles of Industry 4.0 is on this slide. Again, it's many information on this, so take your time offline studying the information here, but just the major points on this slide in terms of design. New design principles is really interoperability, interconnectivity of the machines, of the products, virtualization, virtual entities, as we learned already. This is really a blending autonomous decision, maybe also by our production machines, that they really decide on themselves how to proceed. Decentralization, networks will come into our factories, real-time capabilities, so that we have maybe predictive maintenance, so that the computational intelligence realizes if a machine is not really working fine and may fail soon, so it warns us already in advance that maybe we have to do maintenance with this machine. And then also this service orientation, really connecting the products back to the factory for service interactions with the users. And also modularity and scalability will be a very important design principle in the future, so that we can be, again, flexible, user-centric, user-adaptive again. So we need to be flexible, and this, of course, can be done by modularity and scalable systems. But this new approaches of Industry 4.0 is not only valuable for the new types of spacecrafts and new types of missions, but also for the traditional spacecrafts, the one big, highly complex spacecraft. These new approaches can be very beneficial, and this is seen by a new initiative by ESA, by the European Space Agency, which is called Design to Produce, which is exactly the same thing, the transition from the classical Industry 3.0 to the smart factory. And you see here symbolically how they envisage this. If you have the classic approach, paper-based, so to say, still maybe saved on servers, but this can lead to confusion. We don't know what's the real configuration, and binds a lot of resources to clarify this confusion. Maybe during integration we realize that something is not working, and then we have to go back. So this is the old way, the new way. If we have this connected digital models or digital twins, digital product lifecycle management, we have a much clearer path of information and a connection and also a feedback. So if the virtual integration team realizes during virtual assembly and integration that something is not working, they can feedback this to the design team and they can change it. And only then I build the real spacecraft. This, of course, avoids many misunderstandings and loops, and therefore frees resources of the experts to concentrate on the tricky parts. So all these side effects in figuring out what's now wrong and right hopefully is reduced a lot by these new approaches and frees resources so that they can concentrate on the tricky parts, which are still many tricky parts. If you build a spacecraft, I can tell you it's always not easy and difficult. And if we have resources freed to take care of these difficult parts, this is already a big step forward. But not only the design principles are changing. If we're looking at this huge amount of spacecrafts, of the constellations, in terms of thousands of spacecrafts that need to be produced, we need to have mass production. And therefore we have to introduce completely new ways of manufacturing, like line production, which we are not at all used to in space business. At the most, I guess we produced 20, 30 if it's satellite navigation spacecrafts, but really producing hundreds and thousands of spacecrafts in a line, this is something we didn't do in the past. So we really have to introduce, we have to learn this. And line production means automation, means modularization, additive manufacturing, collaborative robots, cobots, how it is called, smart tools, context-sensitive tools, very important. Imagine You have a machine, an electric screwdriver, and you're tightening a screw, and this smart tool knows by geolocation which screw you are tightening, and then adjusts automatically to the right torque, for example. So the technician doesn't have to take care, okay, which is the right torque for this screw. It's just, it connects to the server and it knows, okay, it's this screw, it needs this torque, and automatically adjusts to it. So smart tools will help the technicians. Augmented reality, the same thing. Wearing goggles and working at the satellite and maybe becoming displayed important data in your augmented reality goggles, so to say. We have automated inspection. So the satellites are inspected if they're assembled in the correct way, automatically by image recognition algorithms, artificial intelligence, and they recognize if everything is on the right spot, for example, and automated testing. So the satellites are automatically connected with test connectors, and then some automated tests are run. So it's not that everything is done by technicians anymore, but many things are automated in this new type of manufacturing. And also, as I mentioned, this preventive, predictive maintenance also of the machines itself. And this has been implemented recently by OneWeb. They built up such a production line with all these tools I just mentioned, smart tools, automated inspection, and so on. It's all described in this picture, so take your time, have a closer look into this picture. It's very interesting what they implemented, and important to mention, the OneWeb production is completely paperless. There's not a single sheet of paper, everything is digital. Smart factory, industry 4.0, that's what we see here. Another point to mention in terms of changing paradigms in the production is that for these constellations, many small satellites, low cost is important, and low cost can you achieve by using commercial off-the-shelf parts, how we call this. So parts that are not specifically space qualified. Space qualifying equipment is quite expensive and a tedious process. So of course it takes time and cost. Therefore using commercial off-the-shelf parts lowers cost, but it's risky. Why? Because they are not qualified for the space environment, and the harsh space environment could result in a reduction in lifetime and reliability of this commercial off-the-shelf parts. But as I said before, with the constellations having many thousands of satellites, I can take a higher risk for the single satellite to fail. The mission is still robust, even so the satellites are maybe less robust than before with the, let's say, low risk approach we were pursuing with the traditional spacecrafts. So we can accept higher risk, and therefore we can accept commercial off-the-shelf parts for this spacecraft. Still, well, not every part, you still have to do a certain type of selection. And what is also now establishing is what is called software-based radiation hardening, especially for electronics. Space radiation is a quite difficult environment, resulting in many failures and breaks of electronical parts. And this, nowadays in the times of digitalization, software-defined functionalities, you remember, allows us to introduce software-based radiation hardening, which again allows us to use more and more commercial off-the-shelf parts on spacecraft. And the last point to mention in terms of new approaches in the development and manufacturing is that we then need new approaches for verification and validation. In the past, with one spacecraft, we had to do many tests and many levels to verify that everything is fine, works fine. Of course, we can't do this with 1,000 or 2,000 satellites of a constellation, so we have to find new ways. And one option would be to do a sort of type qualification. So I take the first model of my satellite and do the classical full-fledged verification, qualification, validation tests. But then, let's say the design and the implementation, the material is qualified. the whole spacecraft is qualified as a type. That's why it is called type qualification. And then for the following 9,999 spacecraft, so to say, I don't do for each spacecraft this very tedious testing, but I rather monitor the quality of the manufacturing process itself. So we bring in quality to the spacecraft by high quality of the manufacturing process. And by this, we make sure if we have a continuous, constant quality of the manufacturing process, the satellites should have the same quality as our first model, which has been fully tested and proven that it works. So with this approach, we have one qualification, verification, testing as usual, and for all other satellites, we basically have to do an acceptance testing, a workmanship testing, so that it works and nothing is broken, but no full-fledged verification. We have to see how this will be implemented. This is not implemented yet. This is just this changing paradigms, and we will see how the space business is accepting such new approaches also in verification and validation. Another important aspect is the operation of satellites. As mentioned already at the beginning of this part, operations has these requirements of 1,000 satellites simultaneously to be monitored, to be controlled, and to be handled if there's a failure. So we can't do this in the classical way, maybe even with 24/7 shifts. This is too expensive for thousands of satellites. So we have to have new approaches, and one important approach for sure is autonomy. Autonomy support on ground, supporting the operators, but also autonomy on board of the spacecraft, so that they can more and more decide themselves what to do in case of a failure. So predictive failure detection, fault management can be done autonomously on board of spacecraft in the future, but also activity planning, health monitoring, and data management. This is something more and more could be done in the future autonomously, first maybe on ground, later on the satellites. And there's a trend on the terrestrial artificial intelligence business that the algorithms get more performant every day, basically. And there's also this push of the deep learning networks, of the intelligence to the edge, how they call this. So really bringing the neural networks, for example, to the edge devices. Edge devices are my mobile phone, for example. And a mobile phone, of course, has low power resources and low computational resources, and that's more or less the same problem we are having on satellites. We are restricted in power and computational resources, so we can't run massive calculations. But with this trend now on Earth, that the artificial intelligence is coming to the edge devices, which means they need to be slim, there is a chance that we now can more and more implement such algorithms also on spacecraft. A challenge, if we want to apply this high grade of autonomy on spacecraft, is how do we verify and validate these algorithms? They are not so much deterministic as the software used to be in the past. So the classical verification approaches for software on spacecrafts are probably not the right approach for this new type of software, which is based on computational intelligence. And also there we have to invent new methods, maybe statistical methods, to verify that the software can handle a satellite in any situation. We have to see, this is for sure an area of research for the future, and still a long way to go to bring up high grade of autonomy to the spacecraft. Another requirement to operations is in-orbit upgrade, in-orbit update of satellites. So using more and more software-defined functions, then the upgrade and update is easy. We just can make a software patch, loading it up to the satellite, and it's updated. So that's the simple part. But we may also think about in-orbit servicing, maybe for refueling a satellite, prolonging the lifetime in orbit, even thinking of spare part production in space, So a servicing spacecraft has a 3D printer on board and can print a specific spare part. Who knows if this is coming in the future? Or you could think of modular spacecrafts which can be reconfigured in space. A spacecraft built of small standardized functional modules with different functions but standardized interfaces, and you just can plug them like Lego together and then produce a new type of satellite. And this has been investigated by a German study team for the German Space Agency. This concept is called IBOS. You see it here on the screen. So this is really a spacecraft, highly modular, and it can be reconfigured in space. We will see if this is the way to go in the future, but it will be a new approach in operations of spacecraft. And then the last requirement to mention is this requirement for low latency of data transmission. So the data shall come to the user faster and faster. How could this be done? One approach is that we give the data owner more direct access to the spacecrafts. And one model could be that the classical operation centers, they just provide the expensive infrastructure like the big antennas and computers and so on, and then provide an easy to use software to the user, a graphical user interface, which is intelligent enough to help the user to control the payload on a spacecraft or even the complete spacecraft without doing wrong things. So having an intelligence software behind so that the user cannot break anything, and the user just directly controls his spacecraft. And maybe in the future, who knows, I can control my spacecraft with a new app on my mobile phone. So all digital spacecraft operations. The future will show where we will go, but it's for sure a very interesting time currently with all these changing paradigms in how we manufacture and operate spacecrafts. This brings me to the end of this part, and in the last part of this lecture we will have a look at the new threats and risks of digitalization in the space sector. Welcome to the fourth part of the lecture, Space and Digitalization. In this part we will have a look on the risks and threats which are introduced by the digitalization of space. And there are different types of risks that are coming into the game. First of all, if we look at the development process, in part 3 we were talking about changing new development manufacturing processes, and of course this poses a risk in itself. Introducing new processes we are not so familiar with. We have mass production, high production rate, and we have maybe new verification validation approaches. So all this could lead to an initial drop of quality of our spacecraft. So there's a risk when we introduce these new approaches, and it is clear that the companies have to have a close look and monitor these effects very closely so that we don't have high loss of satellites just because of the introduction of new approaches in the development and manufacturing of spacecrafts. Operational risks is another big area if we talk about digitalization in space. If we look at the communication satellite mega constellations, a risk is interferences. We have not so many frequency bands available in space that can be used by the spacecraft, and if we have many constellations, they all need to fight for their frequencies, and so there's a danger for interferences. This scarcity of available frequencies is clearly a risk, and the mega constellations also result in a risk of space debris and collisions, which we will address in a little bit separately. So what is needed in particular for these mega constellations is clearly international regulations so that we can maintain the asset of space also for the future and have a sustainability really of the asset of space in the future. Another operational risk is the autonomy. We were discussing that the introduction of autonomy is clearly to happen if we want to operate mega constellations, but autonomy also poses the risk that the system and the behavior of system becomes intransparent. So the operator does not understand anymore what the system is doing because it's so highly autonomous. And we have some tragic examples from aviation where the pilots did not know what the automation of the aircrafts was doing, and then they took wrong decisions because they didn't understand the state of the aircraft anymore. This is ongoing research, and clearly we have to learn from these experiences when we operate spacecrafts highly autonomous. The topic space debris, another important operational risk, already existing, but for sure amplified if we launch these mega constellations with thousands of satellites. So this really becomes a very critical risk and threat to spacecrafts and missions and the services eventually that are provided by space. So we have many spacecrafts in crossing orbits, so high risk of collision. And then we also have to do something with the spacecrafts at end of mission. If such spacecrafts are dead, failed, they sit there and they are in orbits which are quite high, so they don't deorbit over time, or at least very, very slow. So this is really a critical point, and this end of mission disposal of satellites really needs to be considered in the future from the very beginning. So here again, we need regulations, international regulations. Another means to counter a little bit this risk of space debris is so-called space situational awareness. We really have to survey space with different sensors, and on the screen you see a summary of possible sensors that can be used to survey the space and track all objects in space, being it active satellites or dead satellites or fragments of satellites or upper stages of launchers. So we can use radar, we can use optical telescopes, we can use lasers for tracking or tracking signals, or using even other satellites to track all the other objects in space. And this really needs to be implemented in a very systematic manner. Regulations are needed, and these regulations should introduce what is called space traffic management. In the future, we probably need this space traffic management, otherwise we will have many collisions in space, and then this domino effect, the so-called Kessler effect, will come even earlier than predicted and then spoil the whole orbit, and we can't use it anymore. Another obligation that should be really regulated in the future is that all satellite owners should be obliged to remove their satellites from the operational orbits. So really deorbit them, or bringing them safely on a graveyard orbit so that they are out of the way and don't disturb the operational orbits anymore. So this is an ongoing process. The chapter of the United Nations is taking care of this, and hopefully all spacefaring nations on the Earth are joining these international regulations, because otherwise we probably will sooner or later not be able to use space as we could use it in the past, because it's too much debris up there. Very prominent in the context of digitalization, of course, are cyber threats. Everything you are aware, all the threats you are aware in terms of computers, using computers, being in the internet, all these threats apply also into the space sector once we are more and more digitalized. Our ground control centers, our ground stations, our production equipment, our manufacturing sites, they will be all connected in a network via the public internet. And of course, this gives many access points for cyber attacks. So the operators of these facilities have to be very aware of these threats. This is not specific to the space sector. This is of course specific to the total digital society and Industry 4.0 community. So we really have to take care of the cyber threats with cybersecurity technology to keep up with the threats. Also the satellites themselves, they can be accessed quite directly. If you have an antenna and the communication equipment, you can communicate directly to the satellite. So you can hack yourself, so to say, into the satellite and take control or take over the payload. And this has happened in the past. There are quite a few incidents that satellites control was not really taken, but they would have been able to take control, but they didn't do it. The hackers, maybe just to show that they could do it, or a payload has been hijacked and then something was transmitted over the communication channels of satellites. So this happened, even though the operators of satellites don't admit this or tell this the public too openly, of course, but it happened, and it for sure will happen in the future. So we have to take care of these threats by encryption, cybersecurity technology. There is another graph which summarizes these cyber threats we're having in space. And as you can see on the graph, it's really all segments affected: the ground segment, the user segment, the link, and the space segment. Is command intrusion, payload control, denial of services, malware that can be uploaded, replay, what means I'm recording a message or a data stream and then replay later at a point where it is maybe a wrong time, or spoofing, jamming, hijacking, all the things generally available for cyber attacks apply now also to all segments in the space business, with all these attack points which can be seen here. These attack points are on these different segments. They focus on the weakest element, and then it affects the system, different parts of the system, and this, in the worst case, can really have a consequence on the mission, maybe even loss of the mission. If you look on the satellite communication part, we have another risk and threat which is connected to the integrity of data. We mentioned this already. A huge amount of data is transferred, and I want to be sure that these data are not corrupted, that they have not been modified or faked or whatever. So I really have to take care of this by authentication, confidentiality, integrity of data, availability of the data, and this is really making the data secure and safe, so that I can really rely on them and that they are trustworthy. And to do so, you have to take efforts on several levels. This is shown on this triangle, let's say, with several levels on the screen. On product level, physical safety; people level, so personal safety, security; procedures, which is rather organizational security. You have to take care of hardware, communication, and also software. This is all the levels you have to take care to be hardened, so to say, against cyber threats. Another thing or issue connected to cyber threats is the commercial off-the-shelf parts. We mentioned this in the part 3 of the lecture, that more and more commercial off-the-shelf parts are used for satellites, and this means that I have to globalize my supply chain to produce thousands of satellites, ordering commercial off-the-shelf parts all over the world. So this is high dependency. So this can be a risk that a provider is not delivering due to political issues, but it also bears the risk, and this is the connection to the cyber physical threat, it bears the risk that these commercial off-the-shelf parts are corrupted, so that they have malware or logical bombs integrated and you don't know, and then it's activated after your satellite has been launched. So this is also a risk coming into the game if you use commercial off-the-shelf parts, which is eventually a cyber physical risk. So you see there are quite some risks, new or old risks, which become more prominent with the new space trend and the digitalization of space. If we summarize all these risks, which is in this picture on the screen, you can see all the segments, as mentioned, are really affected. Space debris, hardware failures, software threats, viruses, malware, unauthorized access to the satellites, jamming, interception of the link, replay, social engineering. Sometimes it's the people which are the unsecure part of the system, or even physical attacks to the ground stations, or even in space having physical attacks from rockets or other satellites. So this is all the threats, and there's for sure many more to come to discovered, and it is clear that we have to keep up with this. These risks and threats must not be ignored. They must be proactively approached. Only then we can use digitalization beneficially for us and for the space sector in the future. This brings me to the end of part 4 and also to the end of the lecture. And we saw how the digitalization was coming into the space business, the new space trend coming from the Silicon Valley guys, how it was affecting and is affecting the services and products that are already provided and that will be provided in the future, with new possibilities coming from new technologies like artificial intelligence, new ways of communication, and the effects on the manufacturing operations of satellites, which is clearly changing our world, changing paradigms, and eventually the risks and threats we have to approach actively, not ignoring them. Then the digitalization of space can be really beneficial for us, for the space sector. It's a big chance, and we should seize this chance. And then if we can handle all the risks and threats, this will be very successful for the future. Thank you for listening to me and to the topic of space and digitalization. Bye-bye.
Hello, my name is Thomas Bani. I'm professor for satellite navigation at the Bundeswehr University in Neubiberg near Munich. In this lecture, I want to show you a very specific way of digitization in aeronautics and space, and we will try to understand how satellite navigation as a flexible navigation method will gradually replace classical analog methods and how this will affect the future of civil aviation. We will also include a discussion on upcoming challenges coming from the urban air mobility concept, which includes things like air taxis and drones. For this purpose, we first consider how the aviation market is structured and which current navigation problems need to be solved. This topic will be discussed in the light of the classical solutions for air navigation and modern approaches, which are summarized as performance-based navigation. Here, satellite navigation is the digital contribution to air navigation, and we have to understand how satellite navigation as a primary technology was developed and designed, and we need to understand why a direct use of this technology is not possible for safety-critical application. Then we will introduce some methods to make GNSS or satellite navigation reliable and robust, and discuss then the current performance and the way how this methodology will be implemented in future air traffic management. So let's come now to the first chapter of this lecture. Like the other chapter, it's more or less 10 to 15 minutes long and ends with a few simple questions which should allow you to help to check if you understand the content correctly or not. Of course, if you think that you didn't really understand the content, you are free to rehear this chapter. In this chapter, I describe the size of the civil aviation market, and I want to make a point that civil aviation is really safe, and it also has to be very efficient in order to ensure short flight times or to reduce the fuel consumption, and also other challenges to provide an even higher capacity in this navigation technology. Civil aviation is really safe. Having, for example, a look at the year 2017, which was so far the safest year in civil aviation, I would like to let you know that in that year 3.7 billion of passengers have been transported. I'm now writing this number down. So we had in the year 2017 3.7 billion passengers. And to further illustrate this number, you should know that the average flight duration is around 2 hours. So within 1 day, 12 average flights can be conducted. If you multiply this number by the number of days per year, you end up with a figure of 4,380 flights per year of a duration of 2 hours. And dividing then this 3.7 billion of passengers by these 4,380 flights, we conclude that an impressive number of 1 million of passengers is really constantly in the air. So the year 2017 was really a safe year. So we had only one major accident of a commercial aircraft, and this accident caused a number of 67 fatalities. Of them, 32 were on board the aircraft and 35 were on the ground where the aircraft crashed. This accident is of course sadly enough, but contrasting this again to the number of 1 million people which are constantly in the air and the duration of 1 year, I think you get a good impression how safe aviation really is. Coming now to the market of civil aviation. So aviation is not only safe, but also the market which is affected by civil aviation is huge. We have reported figures here that in the year 2012, the contribution to the global gross domestic product of civil aviation was around 2.4 trillion of US dollars, and the value of goods transported by civil aviation in that year was around 6.4 trillion of dollars. So that's really a huge number, and it also makes clear that any improvement in the regulations and also in the navigation system which is used by civil aviation will finally result in a very large absolute value of economic benefit for our society. Also, the growth of the civil aviation markets needs to be discussed. So, and an easy performance figure to evaluate the growth of the civil aviation market is to simply count the number of instrument flights which are conducted in a certain region. So in this graph here, you see the number of instrument flights conducted in Europe, and this number is collected by public authorities and made then available. We see here that in the year 1960 we had around 1.5 million of flights, and in the year 2009 we had then a maximum number so far of around 10 million flights. So there was really a constant increase in this market, and also the financial crisis which occurred in 2009 had a slight impact on the number of flights, but as you can see, it could not really stop, and the number of flights is increasing again. Also, the other global recessions which occurred after 1970, there were 3 of them, could not really have a large impact on this trend, and some people even say that civil aviation is a very important means to recover from a global recession and to help to restart the global economy. Also, the number of flights, or expressed as the air traffic routes which are used by the airplanes, is a good figure to illustrate the growth of this market. So in this figure you see here air traffic routes which are used by many airplanes, so from 2,000 to 40,000 per year as a red line, and routes which are less often used as blue lines. And there are predictions from international organizations how these routes develop over the years, and in 2020 we may have a figure like this, and in 2030 we will see a figure like this. This is again showing how this market is continuously growing, and that's also considered, this has also to be considered contrasting to the fact that we are really facing a lack of natural resources of oil, and also there's a discussion on the climate warming going on, but we have to note that all those points don't really have to have a serious impact on this market. I would like now come to another aspect of air traffic, which is its vulnerability. We see very often or experience by ourselves events where flights are delayed or even flights are cancelled, and often don't understand why this is happening. And one reason for that is that our infrastructure, which is supporting this vast number of flights, is not really well maintained, and it's coming now to its capacity limits. For example, here you see a newspaper message of a blocked airport, namely in Innsbruck in Austria. And this airport, you have to know that, is surrounded by mountains. So the classic methods of the landing procedure, the instrument landing system, cannot be installed. And the new method, the satellite navigation methods, are still not so well developed that they can be used. So this airport is quite sensitive, and if fog is there, then the airport is closed, and on that day 2,500 passengers had to wait for their flights, and incoming flights were redirected to Munich. This on itself is quite a dramatic situation, but furthermore, this event spreads then out into the whole air traffic system, and also other flights which are relying on the airplanes which should have arrived at Innsbruck are also delayed or even cancelled. And this is simply because of the fact that there are nearly no any free slots on the air routes and on the landing approaches, and therefore a simple event like this spreads out, and often it takes days until recover from that. For example, that's quite interesting to know, in the year 2018 we had around 30,000 flights from, to, or within Germany which have been cancelled or had a delay of over 3 hours. So that's quite an impressive number. And also the route between Munich and Düsseldorf had 320 flights which had been cancelled. The airplanes have to compensate the passengers for these delays, and in 2018 we had 800 million of compensation payments, and in 2017 it was 500 million euros. So that's also a pretty impressive number, and if we can reduce even these compensation payments, it's worthwhile to do research in this area. There are also other aspects of air navigation which need to be improved, and they are shown in this graphic here. So we want to reduce also the cost efficiency of the air navigation means by 40%. Coming again to the capacity problem, we want to improve the capacity by around 100%. Also the environment is considered by this research program, and the carbon dioxide reduction is targeted to be reduced by 10%, and also the operation efficiency targets a reduction of 6% in flight time and 10% in fuel burn reduction. All this research is carried out in Europe in the so-called CSAR program, which means a single European Sky ATM research, and ATM stands for Air Traffic Management. As if there were not already enough channels for the classic civil aviation, I would like now come to this new concept of air traffic, which is this urban air mobility concept. You can see here on the left side an artist's impression of how our urban airspace may look in future, and you see here drones, air taxis, and also helicopters flying around. And all this air traffic has to be as safe as the well-known civil aviation conducted in the non-urban air. So we have to apply the same safety standards, but have much less flexibility installing classic air navigation means. And for this concept, this urban air mobility concept, satellite navigation as the digital method of navigation is the only means which we can think of which could support this new urban air mobility concept. So, and with this, the first chapter comes to an end, and I hope I made it clear that air navigation market requires a really safe means of navigation, and also that it's quite huge. Feel free now to have a look at these questions and to answer them with the material presented in this first chapter, and you should have enough information also to do this simple calculation in the first question. Let's come now to the second chapter of this lecture. I want to show you now how the classic methods of navigation worked. I call them analog methods, and how a new concept called performance-based navigation, which is the digital method, started already to revolutionize navigation. Positioning and navigation was always of a very central importance to aviation. In fact, in the early days of aviation, the onboard team always on the airplane always included a navigator who operated a number of sensors and instruments, and also some calculation machines, you could not really call them computers at that time, to determine the position of the airplane. You can see here on this image how a navigator's workplace looked like in those early days. Navigation methods defined in these early days were of particular simple technical realization, but they were very robust and also simple to use. Due to the long lifetime of an airplane, so a civil aviation, a commercial airplane is used for about 30 years. This innovation cycle is very slow, and all these classic methods of air navigation are still in use. And I want to show now a few of them that you have a better understanding of what I'm talking. So the very first mean of an analog navigation method was the so-called non-directional beacons. These are simple transmitters which are located on the Earth and which are marked in the air traffic charts, and they transmitted a signal, and the airplane was basically able to find the direction to this transmitter, to orient itself towards the transmitter and then fly directly towards it. It did not really know how far it is away from this transmitter, but once it passed over it, it realized that the direction changes by 180 degrees, and then knew that the transmitter has been passed. And the air navigation then more or less looked like that. I'm now depicting here a runway. And then we have here a few NDBs. And then the aircraft lifted off here at this runway, flies towards this first transmitter, realizes that it passes over it, and selects the next transmitter, and so on. The last NDB is expected to be located directly in an extension to the runway, and from that point the pilot should be able to see the runway and then safely descend and end its journey. Another analog method of classic air navigation are the so-called VORs. VOR means very high frequency, VHF, omnidirectional radio, and they are some kind of extended NDB where the transmitting ray, the transmitters emit the rays along all possible directions. So, and these rays, I call them radials now. So if I depict here now an VOR station, then the pilot is basically able to choose one radial from this VOR station, and I draw this now here. And this radial has a certain angle to the north direction. This is maybe the north direction. And we have here an angle phi. There might then be a second VOR, which is located here, with maybe a different radial, and the third one, which is located here. And you can already see that that these radials, they define a real route now. And I'm trying to present how the airplane is now flying along this route. So the airplane may, for example, come from this direction here, fly along this radial, then it sees that the second radial approaches, and then it switches to this radial, sees that the third radial approaches, and then can switch to this one. So we already have here real air traffic road, and airplanes are now able to use it. Also, the instrument landing system, which is basically the main means of how to control the approach to the runway, follows a similar principle as the VOR system. So we have again here the runway. And at the beginning of the runway, you see here these antenna systems which are installed, and they basically emit a certain ray from the end of the runway at a certain slope. And there are also three markers, the inner, middle and outer marker. And the airplane is then and the airplane approaches then this glide path, this instrument landing glide path from, let's say, a VOR-based navigation, follows then this glide path and until it has the touchdown on the runway. This is a very simple and robust landing system. You can see the antennas are pretty big, so it's quite difficult to jam or disturb the system. But a major bottleneck of this analog technique is that the glide path is very unflexible. I mean, it's totally unflexible, so it has a certain slope, and you cannot fly any curved approaches or even change the slope. And furthermore, if one airplane is already on the glide path, then the electric signal is affected by the body of the airplane, and the second airplane, which would be behind the first one, would not receive the correct signal anymore. So as a consequence, only one airplane must be on this glide path at any time. That's a serious limitation in the airport capacity, and I'm pretty sure you have already experienced that when the pilot tells you that you don't have a slot to approach this airport, and that the limited capacity of the ILS might then be the reason for that. Overall, these classic methods of air navigation have then been organized in so-called flight charts, and those flight charts originated from the idea that all air routes are oriented along a certain physical installation. You can see here these VOR installations or NDB installations, and only a very limited number of routes was the consequence. As a positive side effect, this made the air traffic management quite easy, because the air traffic controller knew that the airplanes are only allowed to fly along these air traffic routes, and if there was a deviation, it could be easily detected, and then the pilot could be informed to come back to its route. Already today, we have here the digital method, the satellite navigation method, being used for this purpose, and the satellite navigation impact on the flight chart manifests itself as so-called waypoints. Waypoints are also depicted here in this flight chart. You can see one example here, and they are virtual markers. They have a fixed location, they even have names, but there's no physical infrastructure associated with them. But in this overall context, they are used like NDBs and help to already get the air traffic system more flexible and to have more capacity. So overall, we have, let's say in the very past, the historic method of air navigation, where we could only fly from or to the beacons. Today, we have already a more flexible concept, which is called area navigation, or ANAV, where we are able to have a free choice of waypoints. Also, we can freely select the waypoints we want to use for our travel. But in future, we will even go beyond that, and then we expect that the air traffic controller will define for our flight a dynamically allocated 3D or even 4D route, which we need to follow. And the advantage of these 4D routes is that they can be really optimized for the actual weather condition or the traffic condition, and are by far much more flexible and provide by far a much more higher capacity than these classical air navigation methods. The theoretical concept behind this flexibility in the air navigation is called performance-based navigation. This concept was a revolution in air navigation because in the early days, navigation was really performed as a description of what the pilot has to do in order to safely arrive to the airport. So basically it was a rule, fly to this NDP, then look for this VOR, then fly to the next NDP, and at some point you're expected to arrive at the airport. So the pilot had simply to follow this rule. He did not really even have to know where he is, but the rules were safely defined and brought the airplane safely to the destination. Now, to introduce a new technological concept, we have to step back from this procedure-based navigation, and the concept behind is that we have to separate the navigation itself from its technical realization. So we have to specify now the navigation performance, not as a set of rules, but we have to specify now the accuracy, integrity, availability, and continuity values which describe in a more abstract way how the navigation has to be performed. There's, of course, always a technical idea behind this concept, although it's from its very basic idea, it's technology independent, and the key technology which is expected to realize this performance-based navigation is satellite navigation. Many of you may have heard that satellite navigation is not totally robust, and we are relying here on a space infrastructure which has the potential to fail if, for example, let's say a major earthquake occurs at the control center of the satellite navigation system. And then for this purpose, we need a backup solution. This backup solution will not provide the full capacity as satellite navigation provides, but should at least allow us to do, let's say, very important flights, or at least bring all flights which are in the air safely back to the ground. The technology for this backup system is the so-called distant measurement equipment, but I will not further discuss this here in this lecture. You realize, if you read the text, that one speaks of performance-based navigation if you encounter terms like RNAV or RMP, and this RNAV acronym defines already an accuracy which is associated with this navigation method, and RNAV, let's say RNAV 1, means that the 95% accuracy of this method is 1 nautical mile. RMP, in contrast, has the same notation for the accuracy, but also means that an assured integrity and continuity is used for this navigation method. Another nice example to show this performance-based navigation in contrast to the classic navigation is also to have a more detailed look at an approach procedure. And in this picture here you see a classical approach and a new approach with the performance-based navigation. So the red line here is the classic approach. And you see that the airplane flying along the red line, it flies from one NDB to the next one, and it also has to maintain a certain flight level, so it has to maintain a constant height for a certain period of time. So the slope of the trajectory changes, it's not constant. Finally, we see that the classic approach has a very low height near the airport, and the airplane is flying for a long time directly over the ground, which causes a high noise for the people living near the airport. With the new concept, the performance-based navigation, we are much more flexible, and we not only can maintain a constant slope, which helps us to save some fuel. The slope can also be steeper, and we are thus approaching the airport at a steeper level, and meaning that we create less noise for the people living near the airport. How do we quantify navigation? So this performance-based navigation has to get a little bit more technical in order to better understand it. And there are four key quantities or performance key indicators, which are accuracy, integrity, availability, and continuity. And as an engineer, which you probably are, you should have some awareness of how these terms are defined. So as many of you already assume, the accuracy is the typical difference between the true and the estimated position. For example, if I give an accuracy value of 4 meter, this means that the typical difference between the true and the estimated position is 4 meter. And now I also have to specify what typical means. And this is usually done by giving a percentage value. Let's say we take now here 95%. And this 95% means that in 95% of all cases, this difference is below 4 meter, and in 5% this difference is above this 4 meter value. If you increase this percentage to maybe 99.99%, then also the associated accuracy value increase maybe to 40 meters, but this is still the same accuracy, just the associated probability level is different. The next very important figure is the so-called integrity figure. The integrity is the probability that the navigation system is working as expected and providing a positioning solution with an error smaller than a so-called protection level, which is a slightly different accuracy figure. And this integrity is given as a rate value because the longer you operate the system, the more likely it is that it will fail. So typical integrity values for aviation are then 1 minus 10 to the power of minus 7 per hour. And this means that the navigation system is allowed to fail 1 time in 10 million hours. So this is accepted because it's also clear that you never ever can build a technical system which is free of any failure. Availability, the third one, is more easily explained. It's the percentage of time that your navigation system can be used at a given place or along a given air route. And here we target generally an availability of 100%, but this is also not reached due to this intrinsic imperfection in every technical systems. But typical availability values are then, let's say, at the 99.5% level. Finally, continuity is the probability that the system remains available after it declared its availability at the beginning of a certain operation. That's very important for an approach. When the pilot checks at the beginning of the approach that the satellite navigation system is available, it expects the systems to remain available until the runway is reached. So the continuity is then also given as a probability value, maybe here 1 to the power 10 to the minus 5, but maybe not per hour now, maybe per 150 seconds, assuming that our approach procedure lasts for 150 seconds. So this ends the second chapter. and I hope I could explain what performance-based navigation is and what parameters are used to describe these procedures in a more technical way. In this third chapter, we now have to learn what is the technology behind this new digital method of navigation, and that's satellite navigation. Satellite navigation was created for a completely different purpose, and we have to understand now the design paradigms which were used and why this approach was not really an ideal match for aviation application. Navigation was always of central importance to our society and also to the military. And in the times of the Cold War, the Russians launched a Sputnik satellite in the year 1957, and this satellite broadcast a very simple radio signal at 20 megahertz, which was received by researchers all over the world. A group in the US processed that signal and realized by simply observing the Doppler shift, which is caused by the motion of the satellite, they were able to determine the orbit of the Sputnik satellite. And in a second step, 1 year later, in the year 1958, they were able to invert this process, and for an unknown user position, and assuming that this user also observed this Doppler shift of the Sputnik satellite, and knowing the orbit of the Sputnik satellite in advance, they were able to show that they could locate this unknown user with a certain accuracy. And that really triggered the start of satellite navigation, and the US military then decided to build a transit system, which was more or less a straightforward extension of this Sputnik navigation methodology, but using multiple satellites. I don't want to go into very details, but the GPS system, which was built as a successor to the transit system, used in a slightly different principle behind, but was also targeting the military application from its design motivation, but also had the dual use by civil people also in mind. Just to cut this story short, also the Russian figured out that satellite navigation is a really important technology used for the military, and then they built a quite similar systems with a certain delay, which came operational in the 80s and also provided to the Russian military a good navigation capability. During the next decades, in the 90s and after the year 2000, there was an immense use of this technology also by civil users, and the whole technology sector exploded. And finally, also Europe and China decided to have their own satellite navigation system in orbit for independence in critical infrastructure, and also to develop their own markets and applications with some national control available. Today, satellite navigation can be found in billions of devices, and the most common use of satellite navigation is within a smartphone. And every modern smartphone is equipped with a satellite navigation receiver, or I call them in the following as a GNSS, Global Navigation Satellite Systems receiver. This receiver is able to receive the signals from all satellites and doesn't really distinguish if it's a GPS, GLONASS, Galileo, or Beidou signal. When you switch on the receiver, then it takes only a few seconds, 2-3 seconds, until all the satellite signals are received and the position is then computed. So, coming back to the aviation context, one may ask why not these simple receivers built into the smartphone are used also for aviation, because they are very performant, they have a very fast time to first fix, and also have a reasonable precision on the level of a few meters, which would be by far more than sufficient to be used for many flight procedures. But again, I recall that the design behind the design paradigm behind the development of the satellite navigation system was not the use for safety critical applications like aviation, but was really to serve the military purpose and to provide a certain performance. So the systems are not really reliable on itself, and some additional methods have to be developed, which I would like to show then in the next lecture. But before we do that, we need to understand some technical principles when using satellite navigation. With this, I would like to come now to the math part of this lecture and show you two important equations to make clear how this ranging principle in satellite navigation works. So satellite navigation or GNSS navigation uses the passive one-way ranging principle, which is basically the art of comparing clocks and using this time difference to compute then the position. So I'm drawing now the Earth's surface, and assuming that the user is here on the ground with a certain antenna, and this user or the receiver has a clock built in, which I denote here with this clock sign, and this clock displays then a certain time, which is called TR. R stands for receiver, and this is the true time T, plus the clock is not perfect, it has a certain clock error, plus a value DTR. On the other hand, we have the satellites in the orbit. This should be a satellite. And also the satellite has a built-in clock, which is quite precise. It's an atomic clock, but still this clock has a certain error, and it displays as a time value the satellite time TS, which is the true time T, plus the satellite clock error DTS. And then it took a lot of research by the Americans to figure out how this time value, which can be read by the satellite, can be transmitted to the user. So they invented a certain signal, radio signal, which is broadcast and travels from the satellite to the user. And the travel time of the signal is essential now for the further developments, and this travel time is denoted as tau. So what the user then does, it basically compares the two clocks. So it reads its own clock, TR, and then subtracts the time reading from the satellite clock, so minus TS. Then it multiplies the whole expression by the speed of light c, and he calls this one as a pseudo-range p. Inserting now the definition of these time values, we realize that this can be rewritten as c multiplied by t minus t plus t dr minus the true time t. We are now at the satellite time, and now we have to understand that the signal takes tau seconds to come from the satellite to the user. This means the user sees the clock slightly in the past. So the time value which he or she can read is then t minus the travel time tau, but also including the satellite clock error DTS. In this equation we can then cancel the true time t and end up with the speed of light multiplying the differences of the clock errors plus speed of light c multiplied by the travel time tau. And this travel time is then, and this expression c multiplied by tau is then modeled as the distance rho. So that's the geometric distance between the user and the satellite. This is actually the quantity which we are interested in. But there are some delay values, which are called tropospheric delay T and ionospheric delay I. And they are due to the fact that the signal has to propagate through the atmosphere, and the speed of light in the atmosphere is slightly slower than in vacuum, and this reduced travel speed causes this additional delay in this measurement. But overall, we have now found a description how we can model basically this time difference of these two clocks, and this can now be used for positioning. So these clock readings are performed for all satellites which the user can receive. These are basically all the satellites which are above the horizon, and I use the index I to denote the different satellite, and I assume that a number of n satellites can be received. The measured values pi are basically the input to the positioning method, and our goal is to determine the user position XR, or R stands, I recall this, R stands for receiver, or receiver position, and also we want to determine the receiver clock error DTR. Usually the receiver, the navigation receiver, has a very poor clock, a quartz oscillator or something even more cheap, so we really don't know how wrong it goes, and we have to estimate this from our measurements. So these are the unknown quantities. These are 4 unknown quantities, by the way. 3 position parameters and 1 clock parameters. On the other hand, we have some known quantities. So these are the satellite positions, the satellite clock errors, the tropospheric delay, the ionospheric delay. Yeah. I have now to explain how the satellite positions and the satellite clock errors are determined. So the satellite navigation system is operated from the ground, and this ground segment uses several monitor stations distributed around the world, which are constantly tracking the satellites. They are collecting data from the satellites, and a so-called control center is then able to determine the position satellites and to formulate Kepler parameters out of these position estimates. And simultaneously, also the clock error, the satellite clock error, is determined by the control segment. Those parameters are then predicted for an interval, for example, for over 2 hours, and those parameters are then uploaded to the satellite and then rebroadcast to the user. The user is able to decode this message and finally knows then the satellite position and the satellite clock error. So I connect them now in that way. So these are all known quantities. A similar process also takes place for the tropospheric and ionospheric parameters, which are then also known to the user. And finally, there are also some imperfections in this process, and the imperfections are summarized in this parameter epsilon. This is basically some noise which is added to this pseudo-range measurement, and this noise is caused on one side by the measurement process itself from reading this electric signal which contains the satellite clock reading, but also contains imperfections in the orbit determination process, in the satellite clock determination process, and also the uncertainties in the tropospheric delay and ionospheric delay. All those goes to the epsilon parameter and simply reflects our uncertainty in this whole process. With all those things said, we can now start describing an algorithm how we compute the position. So we have here, again, we have a number of n satellite measurements, meaning that we know this pseudo-range is pi, we know the satellite positions xsi and the satellite clock errors. As well as the tropospheric delays and the ionospheric delays. So these are all given values. I present now a very simple method how to compute the position, but to do this I need to define a helper function. So for an assumed user position xr and assumed clock error dtr, I'm defining now a modeled pseudo-range which I call p-snake, and this is a function of xr, so is a vector, and the clock error dtr, and is basically the distance between the satellite and the user plus the clock error difference plus the tropospheric delay and the ionospheric delay. Yeah. So with this helper function I can now formulate my positioning problem as a minimization problem, and my estimated position xr hat and my estimated user clock error dtr hat. So hat means that that's an estimated value, is then the argument of a minimization problem over xr and dtr, where we minimize the sum over the difference between our actual observations, pi, minus this modeled observation, p-snake, which depend on xr and dtr. And here we take the square in order that we have a real minimum. This minimization problem can be easily solved by using method of linear algebra. I don't want to go into details here. And you also realize that you need then 4 or more observations. So n needs to be equal or larger than 4 because we have here 4 unknowns. And if you have then more than 4 observations, you have an overdetermined minimization problem, and you will have then a unique solution to it. So with this, I hope I could have shown to you what is the basic motivation behind the setup of the GNSS system, and what is also the technical principle associated to it to read satellite clocks, and how from that reading the position can be computed. Again, you find here some questions which should help you to check if you got more or less the content of this lecture. In the last chapter, we learned how the positioning process works with satellite positioning, and that this process relies on the known satellite positions and the known values of the satellite clock error. In this fourth chapter, we get now an understanding on how reliable those values are and what errors or anomalies can occur. We will then develop some methods called RAIM or ARAIM, which are then capable of handling failure in this process. I already mentioned that the process to determine the satellite position and the satellite clock error is super complex. So we have here a system distributed all around the globe with monitor station and the control center, collecting data in real time and then estimating the satellite positions and the satellite clock error. There, many things can go wrong. And it took decades of the US engineers until they got the GPS system so robust that we today don't really notice those errors. But they're still happening. Furthermore, the hardware on board the satellite is also quite complex, and their atomic clocks are operated on board the satellite, and sometimes things simply go wrong there. This would not be an issue if the satellite clock goes wrong, as long as the control segment detects this clock error. But since the value which is communicated to the user is a prediction or for the next 2 hours, it takes for the user in the worst case 2 hours until he or she gets this updated correction, and during that time he or she works with this incorrect value. If something like this happens, one speaks of a GPS anomaly. So we have here the case that we have, for example, the clock anomaly when the satellite clock error TTSE is wrong, or we have another case of a ephemeris anomaly if the satellite position XSI is determined in a wrong way. And then a group of researchers, which are listed here on the lower right end of this slide, took data from 10 years of GPS operation and analyzed how well this orbit and clock determination process worked. So researchers analyzed 10 years of GPS data and presented in this study, which is listed here on the lower right corner of the slide, what all went wrong with the GPS system. And this data is here presented in this table, and you see here, so there were many more incidents or anomalies, and this table summarizes the most important ones since the year 2004 until the year 2010. And you see here that here clock anomalies are reported and ephemeris anomalies. The range or the effective, the error which was caused by this anomaly, which expresses itself as an offset in the pseudo-range measurement, ranges from rather small values of 10 or 30 meters up to medium values, which are 1 kilometer. And in this table, the maximum value is then 112 kilometer, caused by a clock anomaly in the year 2007 of the GPS satellite 14. And I hope I already made it clear, if such an anomaly occurs, then this directly enters in the positioning process, and then also your user position will be wrong by 30 meter, 1 kilometer, or 100 kilometers. And coming now back to this aviation context, I think it's not really necessary to further explain that such an anomaly would have a catastrophic impact of your flight and causing incidents or accidents of all kinds. So GPS engineers improved the system over time, and the number of incidents that occurred are listed here in this right graph now, starting from the year 2000 to the year 2010. And at the beginning of this investigation in the year 2000, where, by the way, GPS was already in operation for 2 decades, we still had 2,000 anomalies per year. This did go down, and so far the best year was the year 2008, where we had only 1 incident. And then the number of incidents to the year 2010 increased again to 3. There is, however, a service commitment from the GPS system provider, and meaning that they commit themselves to have only 3 anomalies per year. So that is the value the GPS engineers think that they're able to provide. But again, coming back to the aviation context, it is clear that you cannot tolerate 3 anomalies per year, because then 3 times a year, we would have on that day we would have major problems in the civil aviation procedure. So we have to live with the fact that GPS is not working perfectly. GPS is still the most robust and reliable system. So the GLONASS system is by a factor of 10 less unreliable. And for GLONASS, there are even reported cases where more or less the whole constellation fails. And for the European system Galileo and the Chinese system Beidou, they are simply not long enough in operation that we could provide those figures. So GPS engineers are doing a good job, but we have a way to cope with these anomalies occurring in this process. And the way to do this is to look at the pseudo-range residuals. This is basically, the residual is the measurement, pi, minus the modeled measurement, which I already introduced, evaluated at the estimated user position and user clock error. This is the residual Li. And if the system works fine, all satellites are in nominal operation, then we would expect that these residuals are quite low because the model fits them to the measurement. If an anomaly happens, then we can also expect that our model will not really fit to this anomaly and the residuals will be large. So we have here basically the case that if the system is, let's say, okay, then the residuals will be small. If the system is bad, then the residuals will be large. And that's now formalized with the so-called test statistics. And it's the basis for the first method I want to introduce, and this method is called RAIM. RAIM means Receiver Autonomous Integrity Monitoring, and is a method which allows the navigation receiver to tell if the GNSS system is working as expected or if something strange happens here. So to realize this RAIM approach, the receiver computes every second, based on the current measurements, a so-called test statistics S, which is the sum of the squared residuals, and compares then this test statistic against a certain threshold t. And if this threshold, if the test statistic S is smaller than the threshold, then it declares that the system can be used. And on the other hand, if the test statistic is larger than this threshold, then the user or the pilot, or better speaking, the flight management system, should not use the GNSS or GPS system. Since the whole measurement process has its measurement errors, and also this orbit and clock determination process has its modeling errors, we can never ever give a very precise distinction between those two cases, and both cases have a certain stochastic behind. And this itself expresses expresses itself as a certain distribution of the test statistics. So in this diagram, I draw now the number of occurrence of certain values of S. So on the x-axis, I have here the value S, and on the y-axis, I have the number of how often this value occurs. Then I will have basically two distributions. So in the case that the system is working okay, this distribution may look like this. This is, by the way, this okay case is also called H0 hypothesis. And on the other hand, so then the residuals are quite small. The test statistic is always positive because it's a sum of squared numbers. And then we go to the other case when the system is bad. We have, and bad means now a hypothesis H1, meaning a single satellite anomaly. And in that case, under this hypothesis, we will have much larger residuals, so the likelihood that we have a small residuals will be low. So we have here very unlikely to have statistic values here, and then when we go to the larger values, we will see that the distribution is centered here. So that's the hypothesis H1. If we now define here the threshold T, we can then analyze the performance of this method, as we have now 4 cases. So the system may be good or bad, and we have a use or don't use flag. And we can map those then now to, in this diagram here. So we have here the good case, the okay case, and the bad case. And we have here the use flag output by the navigation receiver, and here the don't use flag. We have here then now 2 nominal cases, so the system is okay, and the receiver also outputs that it should be used. Then this is this case here, which is very fine. This is actually the case we want to have. Another case which can be tolerated is the case when the GNSS system is working badly and we have one satellite with an anomaly, but also our receiver is able to detect this anomaly and tells us, please do not use the navigation system. So that's that case. However, there are 2 other cases, and the one in the upper left corner is the case when the system is working correctly, but for some reasons, so we are here in this okay distribution, but for some reason, due to unavoidable measurement errors, the test statistic is higher than the threshold. Then we are in this region here, which I draw here, and this is the called false alarm rate. False alarm. In that case, the receiver tells you, please do not use the GPS system, but on the other hand, the system was working correctly. So that's not really a critical case, but at least forces the pilot to look for another navigation method. Really critical is the case, however, when the system is bad, so we have the satellite anomaly, but for some reasons the measurement errors are in such a way that they combine within the test statistics to a case which reduces the value of the test statistics. And in that case, we are in this region here, and that's the missed detection. The missed detection case. So that's still a very critical case, but by choosing the thresholds properly, we can shift this missed detection rate to very, very low values, and such in a way that finally the values are so low that they can be accepted for these civil aviation purposes. Overall, we are now able to build a certain machinery where the navigation receiver receives the GNSS signal and outputs the pseudo ranges to this RAIN machinery. The machinery gets also the satellite positions and the satellite clock errors, as well as the tropospheric and ionospheric delay, and outputs this use, don't use flag. Of course, the estimated position, and also something which is very fancy, and I will explain this now, a so-called protection level. what is the protection level now? So we have now this machinery to distinguish this bad and good case of the system, but there are some anomalies which are small, so small that they cannot be determined by this RAIM, cannot be detected by this RAIM algorithm. And so, in other words, if the anomaly is pretty large, it's easy to detect, and then we have this don't use flag. But there's just a border when the anomaly is so large or so small that it just cannot be detected, and then the receiver outputs the use flag, but the position which it outputs is affected by this anomaly. However, this process can be controlled because these thresholds and the stochastics behind can be controlled, and so this worst case which happens can be computed by the receiver, and it is able then to output a value, the so-called protection level, which then limits the positioning error around the true position. So if I draw here now the true position, then the receiver outputs a protection level value, which can be interpreted as a circle if it's a horizontal protection value around the true position, and then we are sure that the estimated user position is somewhere within this circle. And this includes then not only the good case of the GNSS system, but also the small bad cases. The RAIM methodology was developed for the GPS system. It's now already in operational use, and in fact, every aviation receiver which uses GPS has to use RAIM. However, to also include now more GNSS systems, a different method needed to be developed. Furthermore, this RAIM method was quite inflexible because it was only able, or it is only able, to detect one satellite failure. But there are, in principle, there are many more failure modes which you can think of, especially if you combine the multiple GNSS systems. And that's basically the motivation behind ARAIM, which is an acronym and stands for Advanced RAIM. So the basic input, or the basic difference to RAIM, is that we consider now multiple hypotheses, and you can think of many failure modes, and for each failure mode you define then this hypothesis. We start again with this nominal operation H0, which is shown here, assuming, for example, that we have a GPS Galileo operation, then we may have 10 hypotheses for a single GPS satellite failure, assuming we have 10 visible GPS satellites. Then we have 12 more hypotheses for a single Galileo satellite failure. And then we also may assume that the whole GPS constellation fails and also the Galileo constellation fails. And the way ARAIM handles all these hypotheses is to do a different test statistics. So, for example, considering one failure mode, which I call now failure mode, and I consider now simply the failure mode 7. So what the receiver does, it basically computes in a first step the combined position using all measurements from all satellites, and this combined position is here shown as the value XR0. If the system is good, if the hypothesis H0 applies, then this combined position will be near to the true position. Then in a second step, the receiver also computes a second position solution where it excludes the affected satellite. In that case, it excludes the 7 GPS satellite. For another hypothesis, it simply excludes those satellites which cause this failure mode. And then it computes the position difference between the combined solution and the solution with the excluded satellite. And this position difference is it is worthwhile to note that this position difference is accessible to the receiver. So it does not know the true position, but it can combine this difference between both solutions. Now, if we now look at the case when we have a satellite anomaly for the 7th satellite, then we will see that the combined position will be very far away from the 2 position, but the position where we excluded the 7th satellite will be near to the true position. But the test statistics, the difference between both solutions, will be pretty large in that case. And now ARAM requires that for all failure modes, though the corresponding test statistics, SH, need to be smaller than a certain threshold value. And if that's the case, then the hypothesis H0 applies, and then ARAM flags outputs the use flag, and the pilot or the flight management system is then informed that everything is fine and it can rely on the output positioning solution. Overall, we have then again a very similar machinery as for the RAM system. So also for ARAM, we have the receiver, outputting the measurements to the ARAM algorithm. We also again have the satellite positions, the satellite clock errors, and the tropospheric and ionospheric delays. But the the new ingredient in this ARAM algorithm is that we are now able to inform the algorithm about the prior probabilities that a certain hypothesis occur. I call this now P of the probability that the hypothesis H applies. And this is basically a method to realize in these algorithms or to reflect the different reliability of the different GNSS systems. So GPS would receive then a very high reliability reflected as a low probability of a GPS failure mode, and other GNSS systems may then have a higher probability for its failure modes. The output is again the same as for the RAM algorithm, so we have the use, don't use flag, the estimated user position, and also the corresponding protection levels. So with this 4th chapter ends, and it should now be clear what can be done to make GNSS really reliable and safe, that it can be used for air navigation. And these few questions here should again help you to understand the content presented in this chapter. In this final and 5th chapter, I want now to show to you the performance which can be achieved by the RAM and the ARAM methodology. And I will also discuss some rule of thumbs, how you can compute protection level, and also what impact this highly performant ARAM may then have on the future air navigation system. I will start now with the RAM availability, which is a very important performance figure, and every pilot has to consider maps like this before he starts a flight. This RAM availability is expressed as an outage time when a certain protection level cannot be achieved by this algorithm, and in this case we consider here a limit of 185 meters. So this graph then shows the time per day when the protection level, which is, let's say, also a function of the number of visible satellites, is above this threshold. And we see here indeed in the ASIN region that here the protection level level of 185 meters is not achieved for an outage duration of longer than 70 minutes. If the pilot plans to do a flight in that region, he has then to ensure that he uses a time span during the day when the satellite constellation is better and this protection level can be achieved. But we have also to acknowledge that a limit of 185 meter is pretty large, and this also indicates that the ensured positioning accuracy, which is relevant for aviation, is by far larger than the one which we're used to in normal navigation application. So there is really a need for this ARAM methodology, which includes then additional GNSS systems and brings down then the protection level. And with this I come to the second performance figure, which is the ARAM horizontal protection level. So I'm not showing anymore the outage time, but I show what protection levels can be achieved by two GNSS systems, namely GPS and Galileo. So I consider now here 3 cases of the used GNSS system. So I have in the upper row, I consider the usage of GPS alone. In the middle row, we see the usage of the Galileo system alone. And in the lower row, we see the combined use of GPS and Galileo. Furthermore, we have different frequencies, 2 frequencies where the GNSS systems brought the signals. We have the L1 frequency and the L5 frequency. And they basically, on both frequencies, basically the same information is transmitted. But if you combine both frequencies, you can get rid of this ionospheric delay, which was already mentioned, and this brings down the accuracy and also then the protection level. On the left column, you see the case of using the L1 frequency alone. In the middle column, you see the case of the L5 frequency alone, and on the right column, you see the case of a combined L1, L5 usage. So in the upper left 4 figures, which are shown here as this yellow and the one white figure, we see that the protection level which can be achieved is similar to the RAIN methodology at the 200 meter level, but on the lower left figure, when GPS is combined with Galileo, but still a single frequency is used, we already go down to the 100 meter level of assured accuracy expressed as a protection level. If we then combine both frequency and also combine both GNSS systems, then we are in the lower right graph, which is totally violet. And in this study, which was conducted by a PhD researcher at our institute, we are far below the 40 meter protection level, horizontal protection level, indicating a really big gain in performance. And this gain in performance is then used for new flight procedures, which may then allow landing of aircrafts or even starting to maneuver in the vicinity of urban environments. These protection level computations are quite complex, and you need a complex simulations tool to compute them. So I thought it might also be interesting to have some rule of thumbs to compute this protection level. And these rule of thumbs are based on the so-called user equivalent ranging error. This is a value which more or less describes this epsilon factor of the previous chapter, and includes then all satellite modeling errors, satellite clock modeling errors, atmospheric delay errors, and the measurement errors. These UAE values are typically for a single frequency user at the 10 meter level. There are better GNSS systems and worse GNSS systems, so there's a variation there. This is just a rule of thumb. And for dual frequency users, you have a UERE value of around 1 meter. And then the horizontal protection level is in the range of 10 to 20 multiplied by the UERE value, and the vertical protection level is by a factor of 2 larger. Again, the more satellites you use, the lower the factor is, and this brings them down the protection level, and this is also the main motivation why we want to use multiple GNSS systems to have then here a higher performance. I also want to note that the typical accuracy which you are used to when you do your normal positioning in a car navigation system or maybe with a smartphone is 50 times better than the protection level. So we really pay a price in accounting for these possible satellite failures, and the small undetected failures drive our error budget to and these undetected small satellite failures really increase our error budget and are the cause for these very large protection levels. So with these classical pseudo-range measurements, which I've discussed so far, we may go down to protection levels in the 10-meter case if we use all the technology we have today. This is not sufficient, for example, to navigate a drone inside the city, but there's further research going on, and we can, for example, use a different measurement technique, which are called carrier phase measurements, and a positioning technique called precise point positioning, and then the URE value will go down to 10 centimeter, resulting then in a protection level of 1 meter. And that's really a game changer then for autonomous systems and this urban air mobility concept, which gets then a very safe and reliable navigation method capable of handling an unlimited number of users. So with this, I come now to the status and the outlook of the methodologies presented so far. So RAIM is already certified for air navigation use and is really required for all GPS receivers on board civil aviation aircrafts. Also, the mentioned RNAV navigation method fully relies on GPS and RAIM. The ARAM method is still in a final development stage and more or less in a research stage. There are a number of very difficult, complex physical and mathematical problems which still are discussed. They mostly reflect to the probability that satellites fails and also to some atmospheric effects. So there's currently no operational use, but within the next years we hope that we will get there and then can use this ARAM method. I also have to mention that there are other methods of GNSS usage which require, however, additional installations, local or regional installations, in order to make GNSS safe. They are not so generic as the ARAM method, but are currently in use today, and these methods are the satellite-based or ground-based augmentation systems, but they're not discussed here in this lecture. And finally, I want to mention that this ARAM method is also a very good method to include also other navigation sensors, inertial sensors, magnetometers, odometry, and since this ARAM methodology supports these multiple hypotheses, also other navigation sensors can be included. With this, I conclude with the digitization in air navigation, and I hope I could have shown to you that GNSS is really considered as one of the main technology for future air navigation. It has a high navigation potential, and protection levels down to the 1 to 10 meters are possible. It's really a passive technology which can serve an unlimited number of users, which is important for this urban air mobility concept, and maybe also the only one concept, a navigation concept, which can be used for that purpose. It is, however, very important to have a good understanding and quantification of all the failure modes of the GNSS satellites and the GNSS system in order to make this technology so safe that people can rely on it and that not any life is put into danger. And the ARAM framework provides here a very generic methodology that can also be applied for other applications. The definition of this technology and the use cases are now task for the discussions in the air traffic management community, and those guys will then include this technology in future navigation procedures which can then be used by the pilots. Again, I want to mention that since we rely heavily on the GNSS technology for this technique, we need some kind of a backup system which allows at least to operate the system at a reduced performance in case of a total failure of the GNSS satellite system. And with this, I come now to the end of this 5th chapter in the lecture, and I again present you some questions which you may find helpful to answer in order to ensure that you correctly understood the content of the question. And I also would like to invite you to have a look at the 3rd questions and to a little bit speculate on which air traffic modes may be there in the future, assuming that we have a really high performant and safe navigation system. You can also find the material associated with this lecture, also slides with clear drawings downloadable at this webpage. And I hope you enjoyed this lecture, and I thank you for listening.
Welcome to our online lecture, Digitization of Remote Sensing. My name is Volker Liebig, and I will present you this lecture together with my colleague, Professor Schuh.
So I'm a professor for signal processing in Earth observation at the TU Munich. I'm also heading the department Earth observation data science at the German Aerospace Center. My group mostly developing explorative signal processing and machine learning algorithms for extract geo information from Earth observation data with a particular application focus on global urban mapping.
Yeah, thank you for the introduction. Myself, I'm honorary professor at the University of Stuttgart. And I am advisor for digital systems at Airbus here in Munich. Before that, I was 12 years responsible as director for Earth observation at the European Space Agency, and this included the setup of the Copernicus system, which will play a role in this lecture. And this is also the reason why you will see in the flow of the lecture some slides with the ESA logo, which comes from my former responsibility. So now let's go into the modules of digitization of remote sensing. Welcome to this module of the lecture Digitization in Earth Observation. What will we do together in this lecture? First, we look together in the objectives. What shall you have learned at the end of the lecture? Then follows an introduction, also historic. Where do we come from? Digitization started in the 60s, but of course the major trends I will present to you come from these days and the last years. We will have a module on data sources. We will look then into the further flow of the data archives, access, processing services, crucial elements of Earth observation systems nowadays with the big data amounts we speak about. And in a 5th module, Professor Schuh will present you to a new tool for analytics of data, artificial intelligence, and data science in Earth observation. The objective is to show you how digitization is changing Earth observation. We will introduce important elements of the data flow, show different types of data sources, optical and radar data, the two main data types. We will always give you examples. I have decided that I will present you one public and one commercial example always. On the public side, we will take Copernicus as major example because this has a big impact on the Earth observation scene. The system for global monitoring of the environment and for civil security of the European Union. And as an example for the commercial side, I will show you examples from the Airbus offerings for very high resolution data in optical and radar. We will not only look into satellites when we speak about data sources, but also into high altitude pseudo satellites. You will learn what that means, HAPS, the abbreviation. We will also shortly mention what we do from planes and from UAVs, unmanned aerial vehicles, which are coming more and more to Earth observation. And then, as I mentioned already, introduce modern data archiving and distributing technologies to not have a bottleneck with the big data, the access and the processing. And we also will show Professor Xu and myself examples of online services which are available. And then in the fifth block, the artificial intelligence, deep learning approach for data science, which is coming more and more with the enormous amount of data we have. So let's now look into where we started from in our module introduction. Welcome to Module 2, Introduction of our online lecture, Digitization of Earth Observation. We will look into where do we come from, what is the definition of remote sensing, and why are we doing that. Earth observation is taking place today in a very, very strongly changing and fast changing environment. We have all the global trends of digitization, big data, cloud computing, very high networks, mobile access to data. And on the other hand, we have our changing world with all its challenges, climate change. We have more and more people on this planet, and the challenges which come for that, which asks for more and more data about our environment and about our planet. And this is also why Earth observation has become the biggest area of space activities worldwide in the last years. So if we look into what happens on our planet, I show you here the expected development of the population on our planet. We are at the moment, when we take this lecture, in the order of 7.7 billion people on this planet. But we expect until the mid of the century about 10 billion. And the Food and Agriculture Organization of the UN in Rome has estimated that then we will need about 85% more food on our planet. That is in 2050, so we have only 30 years for that. And we need to produce this food without destroying our environment completely. And so we are in a nexus of climate change, water and food, because food production means also water and water supply. We have to manage our planet in a way, and this grows in a way that it is really to the benefit. And in this context, the UN has also developed the Sustainable Development Goals, which are set, 17 goals, and Earth observation can support many of these goals, especially in managing developing countries, supporting agriculture, supporting water management, and finding, for example, locations for solar and wind energy, city management, monitoring climate change. So this gives you an idea on the spectrum of Earth observation, why we do all that, why we put all this effort into launching satellites, but also into the technologies to distribute and analyze the data. But let's go one step back before we do that. What is remote sensing? What is Earth observation? So let's look into the definition of what we want to do. So remote sensing is the acquisition of information about an object without physical contact with the object. So we are not there, it's from remote. and we don't need this physical contact. Remote sensing is used in many fields, but in the space age, it generally refers to the use of satellite or aircraft-based sensors. We will see this. And when the Earth is the object of remote sensing, because of course we can make remote sensing also with the planets and other objects. So if it is the Earth, we speak about Earth remote sensing or Earth observation. And this is also where the title of this lecture comes from. Here are some applications of Earth observation, which I think for the introduction I would like to mention, also to give the motivation. We speak about monitoring of oil spills. We can measure land subsidence from space with radar technologies. We can make visible the tectonic movements of the Earth. We can observe ships in our oceans. We observe volcanoes, floods, deforestation, vegetation, and so on. And all this from a unique observation point from satellites. And satellites don't know borders, and we get all the data with the same system and with the same methods. And then we can aggregate them to a global view about our planet. So this was what I wanted to introduce you before we start. And the next module will be about the data sources. Welcome to Module 3, Data Sources, of our online lecture, Digitization of Earth Observation. We will look into, as the title says, where do the data come from? And so the question is, which sources of remote sensing data do you know? And the first source of Earth observation data we will look into in more details are satellites. Then we will look into a system, into a platform which is called high-altitude pseudo-satellites. It's new possibilities of platforms carrying cameras and maybe also radars one day between satellites and planes. And then the more classical planes, which are still used for many Earth observation data. And as a fourth category, unmanned aerial vehicles or drones, which are more and more used for many applications in Earth observation. And all these data go together and are processed together nowadays. And you should know the different specificities. So let's look in the beginning, so a bit humoristic approach, the beginning of remote sensing. I show you here this slide with pigeon cameras in Germany in 1903. There were the first tries to connect, in this case, still analog cameras to pigeons, and the birds were flying and taking the first photography. But a bit more serious, in the 60s, we had the first digital images from space, 1960, from the US weather satellite TIROS. It was a spinning satellite, as you see also from the form of the satellite. It was spin stabilized. And also the imager was spinning, and therefore with each turn of the satellite, one line of the photo of the image of our planet was taken. And this is a technology which is still used in some generations of weather satellites which observe our planet from geostationary orbit. Then came the first high-resolution imager from space. The system which we have longest is Landsat, which I would like to mention. It started in 1972, and since then we have uninterrupted data which are all compatible, and this is important. This is why I mention it, because in Earth observation we not only have to understand what is happening now, we have also to compare that with what happened many, many years ago. When we speak about climate, we speak about 30 years at least and longer. And here we have now already data for 50 years from the Landsat series. The Landsat series was then followed by the first European system, SPOT, from France. And this came in the 86 time frame. And also other nations joined shortly after. So India started its first optical imager, and all these series have been continued until today. So we have a couple of systems, governmental systems, mainly in this time in the optical sector, from where we get data for the last 30, 40, and 50 years. A bit later, in the 90s, came the radar technology, which has become very important for Earth observation because radar gives us other type of information about our planet. Radar can look through the clouds and also by night, so we are not dependent on sunlight and the illumination and clear sky. And therefore, radar was developed. And the first really operational radar systems came from the European Space Agency with IRIS-1, IRIS-2, later ENVISAT. In 92 with the first launch. And since 92, we have now also 30 years more or less of radar data uninterrupted. And also Canada joined with its own system, which is very similar to the European approach, and Japan with another wavelengths looking with L-band radar with its GES system and follow-on systems, delivering us also data in this wavelengths of radar. So historically, we have seen this, and I would like to show you two recent systems. I mentioned already when we spoke about the objectives of the lecture that I will always give two examples. One is a public system, and I have chosen Copernicus for that. This is a European system for global monitoring for environment and security, which has been built up and which is accessible for everybody. And a commercial example for very high resolution imagery. This is what the commercial world is covering with the Airbus Intelligent Satellite Constellation. So let's look into that. First, Copernicus. As I said, the European Union some time ago has decided to build a system which turned out to become a real game changer for the whole Earth observation world. So a fleet of satellites is in orbit, 7 at the moment. Radar satellites, optical sensors, and also altimeters and hyperspectral imagers, as well as atmospheric chemistry instruments. As I said, it's already in orbit. The satellites are called Sentinels, from the Italian Sentinello, the guardian of our environment. That was the idea when we defined that. As I mentioned in the introduction, I was myself responsible for implementing this system. I have also helped many years ago to define it in the Baveno Declaration. So nowadays it's fully operational, delivers every 5 days a complete coverage of the planet surface with images, or every 6 days with radar images. And this is for the equator. If you go in higher latitudes, then it's partly daily, which is a real novum in Earth observation. Copernicus was built for some 100 governmental services, but meanwhile, as it has this open data policy, it is used by many, from scientists to startup companies, value-adding companies, private persons, and it gives a lot of input to policymakers in many decisions we have to make about our planet and about the management of our Earth, of our planet Earth. There are different services built on Copernicus, an atmosphere monitoring service, a marine environment service, a land monitoring service, climate change service, an emergency management service, and also a service on civil security. So this is all built on top of this satellite infrastructure. which is existing. And to our surprise, positive surprise, I have to say, the number of users has superseded all expectations. So we are in the order of 300,000 Copernicus users meanwhile when we take this module. And this was unexpected. As I said, the design was originally for some 100 governmental services, which are also existing, of course, but there was a big pickup of data analysts as these data are really repetitive, almost daily available and free for everybody. So besides this public system, on the data acquisition side, we have also commercial systems, and we have divided a little bit this world by resolution. So the public system goes up to or down to about 10-meter ground resolution, sometimes a bit better. And the commercial world is concentrating itself on the very high resolutions. That means from 1 to 2 meters down to 30 centimeters. This is what is at the moment commercially available. And what you see here on this slide is a view on the satellite constellation the company Airbus is offering with some radar and optical satellites. And here you see a bit the capabilities. Very high resolution comes usually with a smaller swath width. That means you can cover a bit less of the Earth's surface when you fly over it. And so when you go on the very, very high resolution end, you have Pléiades Neo, 2 satellites to be launched in 2020 at the time of taking this module. They are not in orbit yet, but I hope a bit later in this year. And then with 2 more launches 2 years later, then 30 centimeter data will be available, optical. What is already in orbit is the Pléiades 1A and 1B with 50 centimeter resolution and 20 kilometer swath width, and similar satellites which are also in the constellation, up to Spot, which are Spot 6 and 7. I mentioned Spot already in the historical introduction. We have more than 30 years uninterrupted Spot data, only that the resolution has become better and better, and Spot 6 and 7 deliver a 1.5 meter resolution at the moment. And then we have the radar satellites. At the moment, this is Tandem X, Terrasa X, and PASS, 3 satellites which are in the fleet of the commercial offerings of Airbus, and they deliver radar data, very high resolution also, down to 25 centimeters, and with swath width, they can, as you see in this little video which is playing while I speak, that there are different modes to take data, and depending on the modes, the ground resolution and the swath width is changing. So this is a short look into what is commercially available. I would also like to mention that the data from satellites nowadays are not only downlinked directly, which is the more classical approach, but a new system of data relay is used, which is based on laser communication. Copernicus, again, is the pilot customer, let's say. So 4 satellites out of the 7 with the imagers who have a very high data throughput, the radar and the optical imagers, so Sentinel-1 and 2, A and B, respectively, carry laser terminals, and they relay the data while they fly on a low Earth orbit up to a geostationary satellite, and the data are then downlinked to Earth. This has solved the problem that we have always to overfly a ground station, otherwise when we have not a data relay system. So the data are much earlier and faster available than without a relay system. The same terminal is available on Terrasa X and will also be available on the next generation of the Pléiades Neo, which will be launched in 2022. Let's now look into another platform from satellites which fly usually in the low Earth orbit, 800 kilometers about, sun-synchronous orbit. We go very much further down in an in an altitude of about 20 kilometers. And here new technologies are coming up. They are not yet fully operational, but they are really in the making in many hands. We call them high altitude pseudo-satellites. Pseudo-satellite because they fly higher than planes. And mainly three principles have been developed to keep a platform as long as possible in an altitude of about 20 kilometers. And this is the balloon technology. It's the most simple one, which you can use. Stratospheric balloons are in use since many decades for meteorology. But this time, the balloons carry cameras to make photos. Then type of planes, but planes flying much higher, and planes who have to be in the air much longer. So we don't speak about hours or a day in flight. We speak about months in flight, and the target is to have 365 days per year the plane in a kind of a orbit in the air, in the stratosphere. So this is a technology like the Sapphire project of Airbus. We will look into that, which technologies are necessary. And then there's the Zeppelin technology as potential third technology, which is also used, for example, by the Stratobus, which is another concept you can use. What are potential applications? So the idea is that you have a platform which can be fixed like a geostationary satellite, but much closer to a city, for example. Maybe in some years from now, at least over the mega cities of the world, we have always a flying platform from which we can monitor the traffic or the pollution in a city, or also we position such a platform over emergency areas after earthquakes or volcanoes. This has already been done. I will show you this. You can also put on as payload on those platforms communication transponders to have after an earthquake, for example, very fast a new mobile communication system running. You can use it for maritime surveillance, for news broadcasting. At the end, if you have enough capacity on board, also for smartphone apps which are directly connected. So all these possibilities are coming up. You see, when we speak about the plane technology, we speak about enormous planes with electric motors driven, 20-meter wing lengths, for example, Sapphire with flying in a 20-kilometer altitude and being covered by solar panels because the electromotors have to be fed and you cannot take fuel with you. So the solar panels and the battery sets must be powerful enough to keep this in this high altitude. Again, the target is to stay there for maybe a year, but at the moment the world record, and it was set up in 2018 by Sapphire S of Airbus, is quasi 26 days, to be exact 25 days, 23 hours and 57 minutes. It was the longest ever flight of an unmanned plane, and so the technology has been really demonstrated. To give you an idea, the whole plane with 25-meter wingspan weighs only 75 kilogram, and you can imagine that this is also a challenge then, for example, to build very lightweight sensors. So what is the best flight altitude? We have roughly said, okay, we want to fly in the stratosphere, so above the troposphere where we usually fly and where the weather is taking place. So what are criteria for the best flight altitude? There should not be so many clouds anymore. in this altitude. It should be above the air traffic because it would be too dangerous to have quasi-stationary plane in the, or zeppelin or balloon in an altitude where the normal air traffic with thousands of movements goes. There should be low wind speed because, of course, these ultralight constructions, platforms, they are all dependent on wind. For the balloon technology, it's even the disadvantage because they drift with the wind, so they will not stay long over the same point, and you have to launch too many. So it's also a question of costs then. And the answer to that can be given if you look a bit in the two diagrams on the left, which shows you the wind speed with the altitude. It shows you that you have to go above the jet streams. You have a certain, you have to go above the tropopause, that is the area where normally most of the weather takes place. There are still, where also most of the clouds are. There are some clouds, especially cirrus clouds, in the stratosphere, but not so many. So we have to go in the stratosphere. The air traffic stops at about 11 kilometer altitude, and the jet streams, as you see from the diagrams at the left side of this slide, they are also mainly in altitudes lower than 17 kilometers. So if we take all this together, the ideal band to be with a high altitude pseudo-satellite is 17 to 22 kilometers, and this is exactly what is targeted by all these technologies. So let's look into some applications. So here for the balloon technology, which is already operational, there is Loon, is a company, sister company, if you want, of Google under Alphabet. They have already demonstrated with stratospheric balloons that you can have payloads to rebuild after, for example, the flood in Peru and the hurricane in Puerto Rico, to rebuild an LTE communication, mobile communication system coming then from the balloons, because all the masts on ground were, of course, damaged by the natural disaster. So they were in 20 kilometer height for more than 100 days, but of course they are drifting, so you have to relaunch stratospheric balloons, and you also lose the stratospheric balloons then at a certain point. But this is already operational. Sapphire will come very soon. The first test flights are now taking place, and also the Zeppelin technology will come. With that, I would like to move to the more classical platform planes. They are used for many years now, and they are already standard for applications like photogrammetry, for mapping. So most of the topographic maps in the past were made by airborne sensors, by stereo cameras, photogrammetric cameras. They are partly replaced nowadays with very high resolution stereo photos coming also from satellites, but they are still a very important platform. Also hyper and multispectral scanners, for example, for agriculture, flying on planes, radars, altimeters, laser scanners. So very different types of Earth observation sensors are based on airplanes, and also atmospheric sensors for air quality is also validation of satellite instruments, because whenever we make a satellite mission, we have also a series of underflights to validate the instruments in orbit. So what are the advantages of planes? Is still the very high resolution, because you fly low, some thousand meters usually. You have, or some hundreds even. You can carry big instruments compared, for example, to hubs, and you have a reasonably stable platform. The disadvantages, on the other hand, is that they are expensive. You need a pilot. You have small areas which you can cover compared to satellites. You need permissions, and you are very weather dependent. So depending on these different pros and cons, you see also what is the criteria to choose then the platform for your Earth observation sensor. And the last I would like to mention in this model are so-called UAVs, or unmanned aerial vehicles. It's not only a toy. Of course, our kids really like to play with UAVs, but there's also a very serious market for them, and there are professional UAVs with cameras, with multispectral cameras also, which are used today already operationally for agriculture, but also, for example, to assess storm damages after the storms, also for media. And again, here on the advantage side is that they have a very high resolution. They can fly some 10 meters high. They are easy deployed and very easy to transport. The costs are low compared to all the other systems. Disadvantages, again, you still need pilots. You have a very small area which you cover compared to satellites. You also need permissions, and you are also in a certain way weather dependent. So again, all these platforms are complementary. From all these platforms, we get similar data with very different resolution on ground, but they are very complementary, and we have to regard all of them nowadays when we speak about Earth observation. So with this, we are at the end of this module on data sources, and I would invite you to the next data module, which will give you insight into data archives, access and processing systems for Earth observation data. Thank you for attention. Welcome to Module 4 of our online lecture, Digitization of Remote Sensing. It has the title Data Archives, Access and Processing Services. And it is covering the ground infrastructure which is necessary for Earth observation systems and which are nowadays the key to the success of the Earth observation systems due to the high amount of data. Let's look first into the data access. Data access means how can the user access the data, also this huge amount of data. So what we need is a user interface, at least a catalog system, an ordering system, and a download functionality. If you look in the past, before the World Wide Web and web browsers, we had dedicated clients running on each PC computer of the users. Later, we used World Wide Web as user interface with FTP downloads. And today, the download comes from what is called hubs, that is physically data archives which are connected to a broadband network. And even more modern in the next step than cloud archives, cloud-based archives. The disadvantage of hubs is, of course, that you need to download very, very big amounts of data. We speak about many petabytes, and this big amount of data can block even very broadband networks and take a long time. So there is the newest trend to have more and more data cloud-based, to replace physical archives, which are slower, by cloud-based archives, and then to download from there, or as we will see in the next chapters of this module, to process the data even in the cloud, because this is a possibility when you have the data in a cloud, and then avoid to block our networks with this high amount of data. I will give, again, two different examples also in this module. The one is what is called DIAS, or Data Interface and Access Service of the Copernicus system, and for a public offering, and the other is, again, a commercial system. It's a One Atlas cloud platform of Airbus. To give you an idea of the amount of data we are speaking about, when we record this online lecture, the archives of Copernicus are about 16 to 17 petabyte, and every day about 10 terabytes are coming on top. That means about 3.5 petabyte per year comes on top. So it's really a big amount of data, and this is only the satellite part. There is other parts we are speaking about. Here you see a diagram of the Copernicus archives with the different access capabilities which exist nowadays. So you have the classical hub, which is still available and in parallel to the DIAS systems, and there's another bubble which indicates the additional functionality of processing in the cloud, which we will look at a bit later. On the other hand, the One Atlas platform, a cloud archive from which you can download the very high resolution data on the commercial side if you are an inscribed user, and where you have also interfaces to the Copernicus system, so also the Copernicus data are downloadable. It's via one of the DIASes. I will speak about that. It's called Soblo. And there's another bubble in this diagram, which is for data processing in the cloud. It's another offering. It's called UP42. I will show you this as example when we speak about the processing services and more. So, as I said already, to avoid downloading all these big data, and in Copernicus, for example, this 16 petabyte of data in the archive, statistically every datum is downloaded 10 times. So this immediately multiplies into something like 160 or more petabyte over the time which users would download. And to avoid that, we have nowadays the possibility to process in the cloud and download only the results. So I have here as example the analytics toolbox in One Atlas. You see here on the right side different functionalities and analysis tools. When you offer on a cloud platform a toolbox software which you download and then you process it on your own computer, this is called software as a service, SaaS. These terms come from the National Institute of Technology as definitions, and these definitions go far beyond Earth observation. It's for the whole cloud IT activities where the same terms are used throughout. New cloud platforms offer software collection. Another example is the ESA toolboxes, which are available. You can go on ESA.int and in the Earth observation part, and you will find also toolboxes for all missions of ESA for all type of Earth observation data. So software as a service is already reality. Another acronym you should know is PaaS, or Platform as a Service. This means that a computer platform for the development of applications is offered as a cloud service. And here a good example is UP42, which is an Airbus startup based in Berlin, which offers for geospatial data a platform where you can build your own business on or other services. But let's look first into the access to Copernicus data. I already mentioned that these data are open and free, which has brought through in also the number of people working with this type of data. As I mentioned, about 300,000 people are downloading Copernicus data at the moment. And at the moment, there's a hybrid system. That means you have access either via the so-called hubs. So the Copernicus Open Access Hub would be, for example, the hub you as a user would choose. So again, if you go to www.copernicus.eu, you can find the data hubs and the links, and then you can download data directly. After 3 hours after acquisition, Copernicus data are usually available on the hubs in a processed form, and then you can work further with them. There is also other elements of the ground segments which are described here, so the Copernicus Space Component Data Access, CSCDA, that is to offer also access to certain collaborative ground segments. Collaborative ground segments is ground segments which are built by third parties connected to Copernicus, and it's also very useful, and usually you find many additional data there. There's also EUMETSAT, the European Meteorological Organization, which has connected to the Copernicus system. So for those who come from the meteorological end, they can access it, the data via EUMETCAST, which is the distribution network for meteorological data. And this is also open concerning the Copernicus data. And then there is there are thematic hubs, which you see also in the graphic here. They don't offer the original satellite data, but they offer data which were processed to certain products. And there is thematic hubs for land, atmosphere, emergency, marine, climate, security data and services. So here, depending on the user community, you find derived data, value-added data coming from Copernicus, also from the Copernicus services, which are operated by the European Commission or by organizations which do that for the European Commission. And then parallel to the hubs, we have the DIAS, the data interface to and information access service to access the data which are on the cloud platforms. And the EU has decided that there should be 5 in parallel. It's PPPs, so public-private partnerships. That means that the partner who is operating and has created this system has chosen more or less the composition of what is offered. It's usually more than Copernicus. For example, Cerebro, this is the one which Airbus is running for Copernicus, contains also access to One Atlas, to the commercial data of the Airbus satellite fleet. So the users who are interested in the combination of the two find here both. The same is true for the other DIAS systems, which come from different ends, and you find the link here on this slide for all of these, and you should try out what is the best for you. If we look on the commercial side again, in the commercial Earth observation clouds, One Atlas I already mentioned, which is the access point to very high resolution industry imagery and certain evaluation tools and analytics tools for processing services. So it includes a GeoStore, it includes also what we call One Atlas Sandbox, which is an area where you can test and develop applications, new analytics. It is also possible to connect with an application programming interface, API, which is what is used, for example, if you want to have then results of what you do, what you analyze in the cloud on your mobile phone, for example, or computers, and you make this accessible via the application programming interface. And then there's the open platform UP42. It's a marketplace for Earth data and analytics, which includes, again, One Atlas data and application programming interfaces. So if you want to build a business, for example, based on Copernicus data plus One Atlas data plus many, many other geospatial data, you can choose a platform as a service provider, example here, UP42, but there are others on the market. Here you see a little video of what is possible in terms of analytics in One Atlas, for example, and to give you an idea what you can do in the cloud already without programming. Of course, you can also program your own applications. So you can, for example, take satellite image, you count the cars over the time, you count the trucks over the time, you count aircraft over the time. You can make certain land use classifications, you can distinguish water, buildings, streets, forests, vegetation. Yeah. So these are all analytics which are already built into the cloud processing, and you can monitor in general changes of infrastructure or land use evaluation, very important informations concerning the development of our cities, and all the growth of population on our planet will be in cities in the future. Therefore, this is really an important focus also of the analytics, but also very interesting for the economies. So with this application example, I would like to close to also this module, and I thank you for your attention. I hope you have learned a little bit about the importance of the ground segment and processing part in the times of big data and cloud computing. And I leave you now to the last module on artificial intelligence. Thank you very much.
Welcome to the online lecture, Digitalization of Remote Sensing. We are at the Module 5, Artificial Intelligence and Data Science in Earth Observation. So our mission in Earth Observation is that we research and develop solutions for major challenges in the society. For example, Earth system research, global change research. Meteorology is a typical research area and the sustainable development goals of the UN, and also down to very practical things like security, mobility, resource management, and city planning. And we are now entering the big data era of Earth observation. This you have heard already from the previous module. And the game changer, as you probably already know, is the Sentinels. You know that through the ESA's Copernicus program, we have now the Sentinel fleet, which provide free and open data to everybody who are listening to this lecture. And more importantly, it also have a long-term perspective. Basically, now we have guaranteed data access till 2030, and in ESA, people are already discussing plans for 2040. And another aspect I would like to mention is that complementary to these agency-based missions, we now have entered the blooming era of new space. For example, Planet Lab is a new space company. They have more than 140 small satellites. Where they have capacity is they are able to map the Earth on a daily basis. And because of availability of this big Earth observation data, nowadays we also have internet giants and startups who are entering EO. And the challenge we have, however, is that the classic methods we have for Earth observation could not anymore be sufficient. We really need artificial intelligence for Earth observation. And this is not as simple as that we motivate some data scientists to join Earth observation. Instead, because we have very high quality requirement for wide applications, we really need EO-specific AI research and innovative AI for EO methods. Actually, in this era of big Earth observation data, as competence, what we need to have is, for example, data fusion. Nowadays, for every single application, we will not anymore restrict ourselves to any individual data source. We have radar, we have optical sensors, we can also have atmospheric information and so on. So therefore, it's very important that we try to get the complementary information from different sensors for different applications. The second point is data mining. So we are now confronted with petabytes of available data. So how could we dig out actually the relevant information for us? And also, if we have time series data, how could we, without any supervision, to find out if there any interesting phenomena happens, such that you don't have to scream all the data you have? And the third point is machine learning and deep learning. So this will be the main topic of this module. I will talk about this later. Last but not least, also big data management and HPC. So if imagine that you are doing any kind of global research, you will be asked to processing and managing petabytes of data And for sure, then you definitely need the competence that you will be able to have smart geodata base, and you will be able to use the supercomputers for this kind of task. As I was mentioning, today we mainly talk about machine learning and deep learning. And actually, 20, 30 years ago, there was a wave of neural networks, because scientists have demonstrated such kind of neural networks is very powerful in modeling nonlinear process. For example, if you would have two hidden layers, theoretically it is possible for you to modeling any nonlinear process. But after a while, the winter came. The main reason is threefold. Firstly, we did not have actually enough training data at that time. And also, we don't have smart training algorithms which allow us to train models with a lot of parameters. And the third one is we did not have the computing capacity for doing that. And actually, exactly because of the breakthroughs in these three directions, since about 2006, we now have a high season of deep neural networks, which is neural networks with much more hidden layers compared to the shallow networks. And we have a lot of breakthroughs in many different fields. I don't need to mention all of them because you are reading this already from the news. Let's look at what is happening actually in remote sensing. So this is some literature research we did actually in the end of 2017. If you look at the papers which is related to deep learning remote sensing, you will see it shows really much more than linear increasing. Much more papers are published on this topic. So I would say this is a hot topic, maybe even already a hype. And we have been actually observing the whole community from the beginning. And what we observed is there are actually clearly three phases of deep learning and Earth observation. Phase one, we call it quick wins and quick papers. This is basically people get excited about the power of deep learning and download some networks and to do the things what they can do yesterday, but now with deep learning, with a 2% improvement of the accuracy. And about 3 years ago, we start to understand, okay, Earth observation is different from internet image labeling. Therefore, we start to design new architecture that are fitting perfect to Earth observation data. We also start to train models really from scratch. And about 1 year ago, then people again figure out, okay, even though I train tailored architecture with Earth observation data, still I'm consider this as a kind of black box. We do have actually decades of EO expertise. We should try to make use of them. So this phase is called opening the black box or turn the black box gray. Basically, we want to implant physics, space, and the domain expertise into the learning process. So here is just an example of our phase one success. This was, we are participating in the data fusion contest in 2016. And at that time, we are using deep neural networks to analyze the space videos. Eventually, we are able to also get the traffic density from a video which is taken from the International Space Station. At that time, we actually won the data fusion contest. And I always say this is probably a big part is because we are the first ones who are actually making use the power of deep learning. And such success, of course, will not happen anymore today. And what I would recommend young scientists is that if you are using deep learning for Earth observation, you need to think about what actually makes it special for Earth observation use case. Here I listed a few of them. The first one is that classification and detection, which is the problems we usually have in the computer vision community, is actually just really a small fractions of Earth observation problems. Instead, we are rather focused on the retrieval of physical and biochemical variables. And we also have a very high accuracy requirement. We need traceability, reproducibility of the results. And more importantly, we should be able to quantify the uncertainties in our results. Any measurements without an error bar has no meaning in Earth observation. And our domain expertise, this I mentioned already, we should make use of it. And compared to region community where we have internet images, we actually have well-controlled data acquisition, which is radiometric, geometric, spectrometrically very well calibrated. For many cases, we even know the signal-to-noise ratio of our data. And our data is also different from your handy images, which has red, green, blue 3 channel. Our data is the so-called 5-dimensional data. And sometimes it's complex valued if you think about radar, and also multimodal if you try to combine different sensors. And what is a 5-dimension? X, Y, Z is of course the 3D world coordinate. And we have the time, as I was mentioning, Sentinels provide more or less a weekly measurements of geolocations. And the lambda stands for the wavelength, so we have different sensors ranging from visible light to microwave range. And we can even also make use of citizen science, social media data, and etc. Anyway, the data is much, much more complex than the internet images we have. And also, one downside of Earth observation is that we don't have ImageNet, which is more than 40 million labeled images. In many of the cases, we are actually lack of sufficient training data. So these kind of things you always need to consider if you try to make use of deep learning for Earth observation problems. And today, I give you a menu. This is basically the deep learning research we do. For example, we are detecting tracking of ships and the vehicles. We do the segmentation, classification of buildings, slums. And if we have the global data, of course, we can do the land use land cover classification on a global scale. We can even go to individual building level to get the settlement types. Or if it's related to climate research, we could also classify the local climate zones. And this is more detection, segmentation, classification tasks. We can also analyze time series data to detect changes in the certain geolocation. And a very important aspect is data fusion. How could we match SAR and optical data, which is actually not as trivial as you may think? And also, how could you fuse different type of data like optical SAR, polarimetric LiDAR data in 2D and 3D if it's in particular in very high resolution? And how could we synthesize optical data from SAR data and vice versa? This is, of course, very relevant if you want to combine SAR and optical data, for instance, for change detection. And how could we remove clouds from optical data? And we can even do more fancy stuff. For instance, we can try to estimate the building heights from a single image, and we could try to detect all the buildings, building footprints from a single image. We can even fuse Earth observation data with social media data, and the list actually goes on and on. And today, and here is basically a small selection of the tailored deep learning architecture we have developed. This is what I usually call our deep labs tool, but today we will not go to many details of them. Instead, I want to showcase you some successful examples. The first example is related to hyperspectral image analysis. You know, the hyperspectral sensors, they have hundreds of continuous bands, very narrow bands. The power of such a sensor is that you can actually discriminate different material in the scene. And one actually practical problem we have is the so-called intra-class variability. So basically what you see on the screen is a patch of tree. If we plot the spectral signature, you see, of course, we have detailed spectral information, but even for the same material, they show variabilities. And this is a video I would like to share with you where you can see how advanced machine learning algorithms can extract discriminative features from this type of data. So you can see after the iteration, actually spectrums of trees, soils, parking lots, they are separated much better and better. This, of course, helps us to make use of hyperspectral data. And what do you see? The most stretching one is the soil. So this is also very reasonable because it has a much stronger spectral variability compared to other classes. And the second example is the time series data analysis. And here I showcase you one of actually state-of-the-art architecture we could use. On the left-hand side of the screen, you see the images from different times. We first use a convolutional subnetwork to extract the high-level spatial and spectral feature from the data. And after that, we will stack it with kind of a recurrent subnetwork to model the sequential behavior. And then afterwards, by a sigmoid or softmax layer, we are able to get the binary change mask change and no change, and even multi-class changes, what has been changed to what. And here is the result you can see. Left-hand side is the multispectral data with 3-year interval. In the middle, red color means where change actually happens. And on the right, different color stands for different type of changes like city expansion, soil change, water change. And this is a general framework. Of course, you can do it also with time series data. Basically, here you see with 30 years of data, you see how a city like Beijing has been expanding. And the more yellowish color means it's a newer urbanized area. And the last example is about Munich Airport. I usually make joke about these results because you can see from the past 30 years how our airport has been gradually built. This is more or less the evidence, the most expensive evidence of the time-consuming construction progress in Germany. But I always say that maybe with data of the next 30 years, we can prove the German engineering quality as well. And the fourth example is about high-resolution remote sensing image analysis. So if you have optical data, in this case is from Planet, it's a new space company. And if you generate also ground truths, for instance, using OpenStreetMap, and with fancy architecture, here is a graph convolutional recurrent neural networks, you can train it, and finally you will be able to extract the building footprints from the optical image, which is about 3-meter resolution. And also, if you use multitask of kind of network, you can also get the building instance. Here, different color stands for pixels, belongs to individual buildings. And you know, Planet data is globally available. Basically, with such architecture, you will be able to map actually the building footprint and building instance on a global scale as well. And if you have videos, you can even do more fancy stuff. What you see on the screen is that we are detecting and tracking the vehicles. And here is we are using a rotatable anchor. And the strength of such a technique is that you will not lose the cars if they're turning. And we can even apply deep learning for citizen science. You know, if you have social media or street view images, and you can actually use them to determine the building functions. How could we do that? So from remote sensing data I showed before, you can get the building instance. If we would have a library contains more than 10,000 of ground level images about building facades, and we give a label to them, and of course then you can throw it into a deep neural networks, and finally you will be able to get the building functions for different cities. Here is the example of Chicago, Vancouver, and Munich. And with about validation with 7 cities, with street view data alone, we are able to reach accuracy up to 80%. But of course, for actually larger scale study, we need to do more research on that. And the last example I prepared is global application with Sentinels, and also actually another very concrete application. You know, if you are working with the Sentinel-2 data, the biggest problem you usually have is the clouds. Basically, here is the statistic showing that 67% of the Earth's surface is actually covered by cloud. And there are a lot of the previous study which assume the cloud is only visible in the visible bands. But here on the top, you see actually they are everywhere. So what we are doing here is we are using conditional guns. So input is the cloudy Sentinel-2 image. We are using the Sentinel-1, which is a radar image independent from weather, to make use of the geometric information as the condition to produce cloud-free Sentinel-2 images. And if you look at the preliminary results, on the left you see the Sentinel-1 image as the condition, and you see the Sentinel-2 inputs with clouds. And in the middle is the ground truth, on the right is what we can get from a deep learning architecture. So you see it's actually quite promising. Yeah, now we come to the concrete application I was talking about, is the global local climate zones classification. Why I'm mentioning this example? Because I want to demonstrate you the actual work behind application if you want to really do it on a global scale. So local climate zones is actually a schema actually proposed by urban climatologists. And it has 17 classes describing basically the compactness, height, percentage of green of the urban area. It's more like kind of a morphological description. And we want to do this on a global scale, and also because actually we are interested in semantic functions of the urban structure. Why this can help, I show you an example. The 7th class, lightweight, low rise. And it actually fits very well to our expectation of the slum areas, which is actually what we care a lot. And now, coming back to the global LCZ classification. If you are working with machine learning and you want to do a task, the first problem is always, how could we generate a training data set? So in this case, you see that we actually hand-labeled 42 cities selected across the globe, covering all the cultural zones. And also we give a labeling confidence, which means for each label, we are letting 10 experts to give a vote, such that there's also a way to quantify the uncertainty. In the end, it ends up about 400,000 pairs of Sentinel-1 and 2 image patches with the labels and the label confidence. And we actually made this free accessible. You can also download it and try with your toy examples. And this is a benchmark which is very suitable for image classification, data fusion, quantification of uncertainties, computing in AI, and even automatic deep topology learning. And here I'm showing you the first global urban local climate zones classification we derived. So basically, what you see as color, this is not a simple base map. It's actually the local climate zones classification with the schema I showed you before. Of course, we are more interested in this reddish area. These are the urban areas. I can show you tons of classification map, but I decided to show you a very detailed example, which is Munich. So the background, you see these buildings are the 3D building models, and we overlaid with the LCZ classification. Basically, you can clearly see the dark red areas as compact areas. If you look at the orange areas, these are areas with a lot of green. This is most stands for the rich area. And if you look at the gray areas, this is more industrial areas. And you can also even distinguish dense trees, scattered trees. And by the way, we are doing this actually on a global scale, both 3D and the LCZ. So basically, we wish to have this data also openly accessible for everywhere, including developing areas. Well, these are the examples I want to show. As the last slide, I would share with you the current research agenda we have. Firstly, we are always encouraging young scientists try to actually make AI for you all to tackle grand challenges, not do the things which you can do yesterday, but with 2% improvement. We can do things contributing to monitoring urbanization, try to derive indices for the sustainable development goals, or we can even deliver geoinformation for climate change research. And if we look at the open issues about AI for you, one very important topic is how to re-implement physics-based and the domain expertise into deep learning. Another aspect I want to mention is reasoning. So far, basically all AI for your research still stay with recognition. So you know where, what. But how could we then derive knowledge out of that? The spatial relation of different objects and which kind of phenomena it is. So this would be the next step we need to go. And also, if you want to use deep learning for global research, transferability is, of course, a very important topic. You cannot use your model trained in Europe simply in Africa. That would never work. And name a few more examples. It's very important to quantify the uncertainty. This means both actually the model uncertainty and also the data uncertainty. We need to actually make thoughts about this before you start the whole pipeline. Explainability of the deep neural networks, computing in AI, and the last point is actually I want to make awareness, is the ethical aspect. You know, we are now having actually global data for many of the applications which we could not do yesterday. We have a very good wish to help to improve the society, but on the other hand, we really need ethical guidance to make sure such information will be not misused. For instance, by some authorities, simply use this information to throw out people from slums. These things we should actually make clear thoughts and try to follow the guidance. Okay, this brings me to the end of the module, and thank you for your attention.
Dear ladies and gentlemen, it's a great pleasure for me to say a few words at the launch of your new online course. My name is Judith Gerlach, and as the new Bavarian State Minister for Digital Affairs, it's my job to set up and shape Germany's first ministry dedicated to digitalization. And it's a real interesting and exciting job. My ministry's self-conception is to be a governmental think tank on the ongoing disruptive digital transformation. I coordinate strategies that already exist, but I am also responsible for developing new ideas and keeping an eye on inventions. What's needed, therefore, is creativity, visions, but also pragmatism, as well as the willingness to get things done. Digitalization has to make our lives and work easier. Talking about our digital future, there is one thing I consider as extremely important. All technical solutions have to serve the people. People have to be in its focus. Digitalization exists to serve both the individual and our community. That is why the whole society needs to discuss, for example, about how far and how deep digitalization should go, where are our ethical limits and in which cases the usage of artificial intelligence should be allowed. We must prevent that digitalization will split our society by excluding or leaving people behind. In my opinion, the main task of my ministry is to serve as a communication hub and to bring digitalization to the people, easily, in a smart, in a human way. With our program Bayern Digital, we are investing about 6 billion euros in digital projects until 2022. Our program consists of 170 sub-projects ranging from broadband expansion via digital classrooms to digital business, incubators and artificial intelligence. This one takes up a special role in future technologies. On the one hand, we are already investing 218 million euros and round about 100 jobs in a competence network for artificial machine intelligence. On the other hand, my ministry keeps pushing the topic by developing an own Bavarian blockchain strategy. One other extremely important technology, but I'm pretty sure that I do not have to point this out, is aerospace. Aerospace is another key driver of technological progress in many ways. In the age of the Internet of Things, Satellites can help terrestrial providers generate connectivity. But most important, and that's where I draw the bow to you, the aerospace sector is also a guarantor for high-quality jobs and highly skilled young talents. That's why we expand capacities in Bavaria in a huge way with a new faculty at the TU München in order to ensure jobs for the future. In general, we find satellite research being an extremely important domain. Concerning this, the Bavarian aerospace program announced by Bavarian Prime Minister Markus Söder provides significant impetus. Bavarian invests heavily in this sector over the coming years and is set to become Europe's #1 aerospace location. Here in Bavaria, we already have a good standing, but we know that we have to be prepared. There are a lot of players on the market, some of them well-known, others new, that are challenging our current position. For example, we can see that the battle for the most talented engineers started already. In a world without borders, employers are looking for the best conditions wherever they want. We are responsible for offering our talented young academics best conditions for a good education and afterwards for the best working environment. I am sure that we can face this challenge together, and I am already looking forward to getting the most fruitful environment to assist our industry and our young researchers. I wish you a very instructive and fascinating course, Digitalization in Aeronautics and Space.
The digital data and assessing data, especially for the aircraft design and how to come with new configurations, especially also in unmanned flying, has a large impact because especially small aircraft, we can do a lot of building different concepts for different tasks. And there, when you take a look at the data, you can improve models which are not really consisting and existing today, really to derive data and better design processes for the future.
It's more interdisciplinary. We have to work with colleagues from robotics, we have to work together with colleagues from sensor systems to understand the physics behind this and to deal with it, to use it for our application. And so world life is more complex but challenging, but also with a lot of advantages.
What digitization will bring to us is really more flexibility. In the past, in order to change a signal, we had to wait that a new satellite was launched, or that even the system was completely replaced by all these new satellites. Now we can easily change signals because we have a very flexible signal generator.
We use it for better machining, we use it for better assembly, for more quality, for less cost. There are a lot of challenges, but also chances.
Well, coming from the, let's say, the traditional aeronautical engineering field, we see that its foundations lie in the classical mechanical engineering, which is more like, or often mistaken as, okay, we're doing like sheet metal bending and drilling holes, stuff like that. But that's not the case anymore. We have to focus more on being, well, system engineers. We're engineers in all aspects of the flying platform. And that does not go only into propulsion and structures and lightweight materials, stuff like that, but also into functions. And those functions are realized using IT systems, using software.
I guess we should use or make use and test all the capabilities that digital data and also the analysis of data does bring. But we shouldn't forget that we have to match it also against our experience from the past. So basic models, basic expertise, knowledge that we have should also be matched against what we can get out of data. Because it's not just that we can now assess data that are available. We can forget all about the physics and the baseline that we have in there. But nevertheless, we have to test what we can do and what we can get from a benefit by using digital data.
Yeah, do it and give examples. I think it's very important to give people, give the society good examples to show what is possible and to deal with the risks. Of course, there are risks in all new technologies, but showing examples, showing successful examples, I think that helps a lot.
I would say use it, try it, be open, but also be critical. Try to understand what's happening with your data, what are the risks and the threats. Try to be aware, but of course use it. It's a big chance and it can be very beneficial to us.
Welcome to this course on aircraft design. My name is Mirko Hornung. I am the head of the Institute for Aircraft Design at Technical University Munich. At the same time, also Executive Director of Research at Bauhaus Luftfahrt, a research organization for long-term developments of aviation. My main industrial and research background is aircraft design, which will also be the main topic of today's course. The dedicated title is Collaborative Aircraft Design, and we will dig a little bit into what's specific on those two elements, collaboration at the same time as aircraft design, and I will try to show it to you on some dedicated examples. The key design challenge of an aircraft design is really to find a concept of an aircraft in a very initial phase. So if we take, for example, the A350 as one example of a long-range passenger aircraft, we have dedicated options how to design the aircraft. What you see is the final product, but in the initial phase, you have to decide, is it like that, like the competitor aircraft, the Boeing 787, or the A350? On the first look to the configurations, they look very similar, but in detail, there are huge differences in how you do the technical detail design. But even more, in very early phases, these are not the only solutions. You can even consider a radical different configuration like you see on the Concorde. So I'm looking into supersonic aircraft, that could also be a viable solution. This is the kind of design challenge you have to face at very early conceptual design phases, where you have to settle the characteristics of the aircraft on that overall configuration. So going to a very old chart, which is sketching a little bit the problem that we are facing in early design. So we have to consider a lot of details to get to know the final solution of the aircraft without having all the tools and measures in place really to get the details at very early phases. So the general problem is in preliminary design, we have a lot of know-how assembled by a variety of experts contributing to an aircraft. So this is a phase where you already know a lot of details about the general configuration. So the general sketch of the aircraft is available. You can split the work to a lot of experts that provide you the data to derive with good performance data to get an assessment of the aircraft itself. Nevertheless, the initial phase to come up with the right concept, you are in the very early phases of the phase, so where you have to rely on limited information and to do the selection and to fix the concept already. So this has a high flexibility, but bears a high risk of unknowns that you don't have the expertise at hand really to do the right selections. So what we try to do now with more digital models and tools that are available to shift that knowledge base forward. So what we want to do is get more sophisticated tools and know-how of the experts into the process at very early concept definition. So this is the target, and we'll see some of the problems that arise with that and how we have to tackle that in a collaborative manner. So the aircraft design process itself. So before we go into the dedicated problems in doing aircraft design today, especially if you have multiple stakeholders involved, we have to spend a few minutes on the aircraft design process itself. So how does it work? So in general, you have a dedicated customer requirement basis. So this is about coming from market forecast, identifying which kind of characteristics like number of passengers, range, and also destinations you want to fly to do specify the basis for your aircraft design. At the same time, you also have a set of technologies that are currently in research, which might be viable to be inserted into the new aircraft product. So what you do is you start an iteration to see between the specifications, so the top level requirements, and possible concepts of the aircraft to find the best trade-off between both. So you are looking for a big compromise on the technology side with respect to requirements you want to have. So this is coming to the point where in roughly this phase over here, where you're just stepping into the preliminary design, you have that concept, one or two concepts frozen. So this is a general layout of the aircraft configuration that you want to concentrate on. So going into the phase of preliminary design, this is more or less the phase where you're working on specifications. So this is where you try to define all the details of your different components, subparts, engine, landing gear, and so on to a dedicated detail where you can start the development later on. So we have to differentiate between conceptual design, where you are laying the foundation of the basic concept of the aircraft and then specifying it to the details. The problem is that only in preliminary design you have all the information available to see if your initial concept really worked out the way that you want to have it. And then you go into detail design. So this is really getting down to the nuts and bolts, where you do all the sketches of detailed manufacturing sketches to support the initial production of the aircraft. So this is the different phases of the aircraft design process that we have to tackle. What we're now trying to do is to somehow combine the conceptual design with the preliminary design if we want to shift knowledge from the expert level to early conceptual design phases. And this is what we want to tackle in that. So how does it work? So we are starting from design requirements, looking at the available technologies, and do concept sketches. It's still like in the old days where you just take a napkin and start to sketch some kind of aircraft configuration, which you do as a baseline. Now you do it with modern tools, but nevertheless, it's still the baseline. You come up with an idea where you do some kind of initial configuration study. You do an initial sizing, and sizing in that context means that you try to scale the aircraft to a size where it does fulfill exactly the mission requirements that you want to have. And then you go in that initial layout and try to work through the different disciplines. And this is all the characteristics coming from aerodynamics, structures, which means in the end weight, which is driving the performance of the aircraft, and the propulsion system, which has a big contribution to the overall performance of the aircraft. And then you try to bring all the elements or the description of the configuration together, do the sizing and the performance optimization. So once you have somehow settled and scaled to a dedicated configuration, which does fulfill the requirements, you are still at the top level of the knowledge of the different disciplines, which means aerodynamics, structural design, and also propulsion and engine sizing. Then you have to go into more detailed estimations of all the different disciplines. So you go into a revised layout, and then you're digging much more deeper using more sophisticated and high fidelity tools and methods really to grow the knowledge about the different disciplines to mature the overall concept of the aircraft. So finally, you end up on a refined sizing and performance optimization, where you come with a more mature concept after that phase. But this already includes that you have to insert, especially in this process, the expert know-how from the different disciplines. And this is what we have to tackle in an overall digital design process to feed in these kinds of models and know-how into that design process. So how does it really work in a sequence? Most of the aircraft design processes in that initial assessment do look quite similar. So once you have an aircraft design, you really start with the geometry. So this is always the baseline. So this is why still today you start with a kind of sketch of the configuration. Today it's much more sophisticated than in the past, but nevertheless it stays the same. Out of the geometry, you start to define and specify your aerodynamics. You start with very low fidelity models in the beginning, and then you dig much deeper by using higher fidelity in later phases. Then you have to estimate the propulsion system over here, where you have to gain thrust data at the same time, which is very distinct and very important for the design, is the fuel flow, because this finally derives your mission fuel requirement, and this drives definitely the weight of the aircraft. This is followed by the weight estimation, where you have to do the structure layout, or you start with semi-empirical estimations of how the weight distribution in very early aircraft configurations looks like. And then you have to go back into aerodynamics, because out of the weight assessment, you get your center of gravity. And just with the center of gravity, you are able to see which kind of stability margin your aircraft has, and you are able to trim the aerodynamic data sets all over the mission performance and to get all the data that you need. So at the end of this assessment phase, you will get all the different data that will allow you to estimate your performance of the aircraft. So you have the aerodynamic data sets, you have the weights, you have the thrust, and you have the fuel consumption of the configuration, all in a consistent manner before you do the performance assessment phase. So here in that part, in the lower part of the chart, you take a look at the design performance using, on the one hand side, dedicated points, which might be due to certification aspects, and you also take a look at the design mission. This gives you finally the feedback how much mission fuel you need to perform the mission, and this is an indicator on how well your aircraft is efficiency-wise in the overall design. Nevertheless, what you also do in that design process, you also assess different off-design missions and off-design performances to also see how robust is your configuration to get to a stable design. So this is the overall process. So we have to separate it in two blocks. The one is describing the aircraft, the configuration with its characteristics like aerodynamics, weight, and also the propulsive forces. And the other one is the assessment with respect to the dedicated mission the aircraft has to do. So these are two blocks that we have to do, and they are more or less independent of each other. So what you do in the different phases is you start with the design space exploration. So this means you want to do a lot of trade-off investigations of multiple concepts using multiple technologies, which means you have to be fast. You have to have fast tools that allow you to sweep through all the different possibilities that you have to come up with the best compromise of the different elements in there. So this is where classical multidisciplinary optimization plays a role, and more generic semi-empirical methods are used to keep the speed in the process, because once you insert higher fidelity tools, it will take much longer to get to a dedicated results of the different parameters. So out of that, you define initial concepts. Out of the initial concepts, you do an evaluation, which is the best compromise, and you come up with a reference design, which is your baseline solution. And just from there, you now start to use much higher fidelity methods to get into the details and to mature the design in its characteristics. So you're looking into aerodynamic structures, but also systems beside the propulsion system, and also mission systems could also play a role if we are not only talking about manned passenger aircraft, but also like unmanned systems as we see them today. And finally, you do with all the details that you now have available, and those details can even go up until wind tunnel testing, so really testing results out of different disciplines. You do the scaling and optimization, which doesn't mean that you change the overall configuration anymore, but you're trying to match the size of the aircraft that it just fits the mission performance that you want to see of the aircraft. And finally, you have to bring it all together in a visualization where you have all the details visible, because this, in the end, defines the overall concept of the aircraft. What is the problem with that? Once we start in the conceptual design, so with very fast MDO-based processes to come up with a possible configuration, we are on that phase one according to that chart. So we are working with very rough descriptions of the overall configuration. So we have main parameters like length of the fuselage, diameter of the fuselage, the span of the aircraft, the aspect ratio of the wing, and so on. So it's very high level where you can easily address simple formulas like semi-empirical methods, but also simple numerical models to specify the characteristics of the aircraft. This is very fast, so you just take a couple of weeks or months to come up with initial concepts really to be the baseline of your design. And then once you go into the next phases, you get to much more detail. So the complexity drastically increases. At the same time, the fidelity of the individual tool and methods that you apply is also increasing, and therefore also the time that it takes. So you see the phase two, where we talk about preliminary design, we're talking about a couple of months to even 1 or 2 years, where you do detailing of all the subsystems and the sub-elements in the aircraft. In the phase three, where you do the detail design, this is really about structural layer build-up and also how you manufacture dedicated parts. So this is, in most of the cases, on the final design side itself. So we will concentrate just on phase 1 or 2. But even in that phase, you have that problem that you have on the same baseline configuration now have to insert more sophisticated tools and models to mature your design. And you don't want to lose the data that you had with initial phase, where you did just the estimation with rough models or with initial low fidelity tools and methods. And this is what we have to tackle. So once we have now addressed the aircraft design process and also the related activities that you have to perform, we now look into a dedicated topic that is coming up in the recent time, really, is about the collaborative design aspects. And here, one of the key elements is that we have a work-sharing environment in the aircraft design. So it has increased over the recent decades, that more and more activities are spread into the community, and already suppliers doing a risk-sharing role at very early phases of the design process. So this provides a dedicated problem to the design task itself. While in the past, the OEM, the aircraft manufacturer like Airbus, like Boeing, but also others, have been doing much of the conceptual and also preliminary design work within their own expert departments. They now have to insert already suppliers at a very early phase, which means while in the past the key element of defining the aircraft has been more or less in this part, all under the responsibility of one single company, it was quite easy to bring all the expertise together and to do that design process. And now with that support and with the early introduction of the suppliers already in the design process, you now have to find a solution how you can cut somewhere elements out of that process and insert the capability that the suppliers does bring into the aircraft design already at very initial phases. So this brings up a couple of problems and challenges to that. The first of all is how to insert somebody who's external to the company into the design process, where they are responsible to define some of the technologies, but also some of the systems, and do provide data to describe the characteristic of the aircraft, which in the end is performance driving. The second one is how to ensure in an overall data set, which is describing that aircraft concept during that phase, in a consistent manner. And this also has been in the past, in a lot of design processes of existing aircraft, been a main challenge, that not all the expert departments have been working on the same data set, leading to difficulties and mismatches of different solutions once it comes to preliminary or detailed design later on. So this has been a classical problem, and now we have to find solutions if we want to work together more integrated and to shift the knowledge even of the suppliers into the process very early on. We have to find solutions how to do that. To understand what this means in the process, we have to go a little bit more into the detail how we have to separate the knowledge generation and the knowledge capturing in the data sets itself into the system. So what does it mean? In the initial conceptual design, you are more or less defining the aircraft with its main characteristic, which means you have the aircraft, you don't care exactly how it looks like. What you try to summarize is the performance characteristic with respect to aerodynamics, which means lift generation and drag generation. And you have the engines with their thrust potential and also the fuel consumption. And you have the weight of the configuration, which is also a sum of all the different components ended up into a weight breakdown and also a center of gravity. So if you now have to split it into different responsibilities, the picture changes, because in that case, you're talking about individual parts of the aircraft having dedicated expert groups or even external suppliers being responsible for some of those elements. And now we have to find the link between both sides, because you have to work on a different component, but at the same time you have to provide your contribution to the overall data set of the characteristic to describe the aircraft, which means, for example, lift generation of the overall configuration, which is not only the wing, which can also be other parts. And this is the kind of bridge that we have to take. So what does it mean to cover both aspects? We have to provide an overall system which is set up of two parts. In the one hand side, we have the aircraft architecture, which is more or less the geometrical representation of the aircraft itself. So you see the wing, you see the fuselage, you see a landing gear, you have the engines, you have a landing gear, so all the different subcomponents that do assemble finally the aircraft. So this is the physical representation of the system. On the other side, to do the performance assessment, to do that matching to the requirements that we have to fulfill with the aircraft, we are talking on properties or characteristics of the aircraft, which are more related to aerodynamics, thrust behavior, fuel consumption of the engine, also the power consumption, like the air conditioning being the highest power consumer on board of the aircraft. But we're also talking about weight, which is mainly structure, but also all the other subsystems on board of the aircraft that need to be put together to get to an overall weight breakdown. And finally, it's the performances. So this is the integrated assessment with respect to the design requirements on aircraft level. So to be able to do that, you have to ensure that this side does match this side. And you have to be able to integrate now a supplier or some external party into the process that they are consistently connected on both sides. So to do that, we also need to do the system analytics to that. So we do the performances and also system consistency. So this is what you do in the assessment of the aircraft configuration. You still have to match it to the requirements, which means mission performances, point performances, and also certification requirements. And you want to do an optimization and all together with all the different know-how, with all the different baseline concepts you have on your bench, which you want to include in the assessment. So you're doing scaling out of parameter optimization. If you now take the different contributors into that process, we have to disassemble this setup into different elements which we can use to foster that collaboration in the design task. And to do that, we have to consider what are data that we are handling and what are tools and models or expertise that we are handling in the process to come to those data. And this is a chart where there's an initial separation of what we have. So if we talk about requirements, for example, we are definitely talking about data that can be put together and which are not changing too much, except you want to discuss with the customer that some of the requirements doesn't match, so you cannot find a compromise aircraft that can fulfill it, but nevertheless, it's a data set that you can describe. There you got mission performance data, you got design characteristic coming from certification and so on. The same is true for the aircraft data sets, where we have all the information on geometries like the wing surface, the aspect ratio, the span, but also the aerodynamics, which means lift, drag, and also moments characteristic, but also all the different masses and weights. And this is where you can see directly the masses and weights are strongly affected by the aircraft architecture, but we have to separate them. One thing is on the left-hand side, on the aircraft architecture, you find models, expertise, how you derive those data. And then you have to all get them into one consistent data set. And this is quite important. So each consistent data set does describe a dedicated aircraft. And this is very important that we have a consistent data set to describe the same aircraft, although we got the information from different sources. And also with different views. And this is again back to the left-hand side, where we see there are different ways how to tackle the data that we need to have to do the performance assessment. So also on the aircraft optimization, we are also talking about a data set, because there we're talking about scaling laws, parameters that we want to achieve, key performance indicators that we want to have as our final goal. And then we again have a toolbox which allows us to do that integrated system assessment later on, to do the point performance, the mission performance, also dedicated certification requirements, assessments that we can do with the overall aircraft design. So this is the first step really to segment the design process into knowledge and data. And this is quite important really to enable the collaborative design aspect. So now we would like to go into one dedicated example. So at Technical University Munich, we have worked on an aircraft conceptual design environment, which does enable and also test some of the features. So we call it ADIBO, which is the aircraft design toolbox, which we would like to take as an example to show how this can be done and how we also have to implement some of the elements that we have discussed before. So you can also see on that slide, it has been built to feature all kind of different designs. So ranging from small scale unmanned area vehicles up to different configurations on the civil air transport sector, but also tackling some of the military aircraft products. So you already see there has to be a big flexibility to support initial conceptual design studies, but also, as we said before, we have to provide the baseline to get more knowledge into later design processes, also to support the preliminary design phase. So what is the basic concepts behind that aircraft design box that we have? So as we said before, we have the necessity to take data in there, so knowledge, which means databases and functions. We have to have tools available, which will start with very generic semi-empiric methods in the very beginning. But the more mature we get in the design process, we have to get medium and high fidelity tools also be possible to insert the quality and also the amount of data that we can incorporate in there. And this is all integrated into the consistent data model. And this is the representation of the aircraft concept that is the baseline and also the derivatives of that. To do that, to come to that aircraft design, we somehow have to be able to define the process, because we have seen it before. There's a standard sequence of coming from geometry over aerodynamics, engine sizing, the structural layout, which derives the weights and the center of gravity, back to the trimmed aerodynamics. We somehow have to tailor that process using the different tools and methods that we have to come up with a mature design. So this is the general information, and that all has to be controllable with the user. And in that case, it's not only one user, it also has to be able to be split among entities, so that you are, even in a company, are possible to have multiple experts working on that at the same time, and also external companies doing that. And in this respect, you have to keep in mind that an expert may be just interested to work on his single system. So he will concentrate on his expert module to specify and mature the technology and also the subcomponents that he's responsible of, and then insert it back into the overall system. But nevertheless, we have to ensure the consistency in there. And this is what's quite driving. So to get a feeling about what this would mean on a tool repository, what we have currently integrated, you have different fidelities. Like we do the design chart, and the design chart is a very simple semi-empirical methodology to come up with the first solution of how an aircraft should look like. So it's very simple equations that you insert in there, which are very quick, very intuitive, so you can come up with a very early design. Then you get into a more sophisticated one, like certain elements like XFLR5 or XFOIL, where you already go one step deeper into describing the aerodynamic characteristic of an aircraft, for example. Or you have a PAVAT tool, which is an in-house tool that has been developed also to match propulsive devices, which means propellers or other propulsors interacting with the aerodynamics of the aircraft. And this has an effect on the trimmed aerodynamics and also on the performance that the aircraft is seeing. So this is a kind of fidelity level, which on the university level we can insert. But nevertheless, there is that flexibility once we talk about toolboxes to even integrate much more complex tools like, for example, high-scale, multi-fidelity CFD solutions to do the aerodynamics, or even structural analysis to do the structural layout. But we also have visualization tools in there to show and see on an easy possibility to see, does the aircraft match with all the configurations? So do we have a consistent data set? So this is where we use currently models like OpenVSP, which give us a very quick graphic representation of the configuration that we have at hand. So the key challenge now is, once we now separate the data set from the tools itself, we still want to rely on expert know-how from that expert that has been working on a dedicated technology in a subsystem over decades, probably in a company. So they have been building up tools by themselves. So either it's a tool that's publicly available, but there are also tools that have been growing over the design experience within the company, which is inherent know-how of the company itself and mainly focused on the expert. So the key challenge with all those design processes is how you insert this kind of knowledge in the design process. And this is where you have to get a connection from the tool, from the dedicated expert tool, to the database, because this is where you have aggregated all the information about the configuration, which does form the baseline for the analysis the expert has to do. So what you have to do, you have to work with a kind of wrapper that enables you to get the communication back and forth, so input and output, with the database, which should provide a consistent single database capturing all the aircraft characteristics. So this is what you have to do. So you have to find a wrapper concept that enables that. How you do that, we don't have to address in detail, but nevertheless, it's important that you take an existing tool, bring it into the process chain by interacting with the core database, which is describing the aircraft. So finally, it gets the data from the database and also puts them back in. And now, once we talk about expert know-how, we also have to trigger a process because this could mean there's a part of that data set describing the aircraft configuration has changed. And that change might have implications to other disciplines and other experts that need to get a trigger now that they have to redo some of their assessments and their modeling approaches because some of the assumptions and the baseline data have changed over time. And this is something which you have to capture in that process, really to get that expertise into the process and still enable that this final configuration really is consistent. Because if you have a change in that area over here, it might lead to a situation that in that area over here, you're no longer consistent with those data. And this is what you have to trigger, and this is what you also have to capture in the design process. So how is it done? A general layup of the Adibo tool environment that we have set up. So the upper part is describing the ADAM, which is our data model behind it. So this is the central entity which will capture all the data from the models to ensure that you have a consistent approach. So which means we have the database describing the aircraft configuration itself. But what you can see is we have here a kind of an artificial engineer inserted, which will take care that some of the elements in dealing with the database does ensure consistency among the different contributors, which means elements like checking if the units are correct, checking if the values that a tool or an expert try to put into the database does fit with the kind of physical dimension that you want to have in that area, and also to do some conversion elements that will help you in handling the database. At the same time, you can also rely on data from existing aircraft configurations. So studies that you already have done before, or configurations that are similar to the kind of design tasks that you have to tackle. You can also use those data to bring them in as a baseline configuration, and then you work from that starting point to come up with a new derived configuration from that. So this is still all on the data side. And then you have that interface to that toolbox. And that toolbox is nothing else than providing expertise in changing the aircraft concept. And it's from aerodynamics to weights to aerodynamics to even performance assessment. Everything can be in there. But to get to an aircraft design, you now have to bring it into a dedicated process of how you want to do it. And the following two slides will show you two examples of how this could look like, because depending on your design task, you might have different focus areas where you want to concentrate on. The first one is for a classical transport aircraft. So you have a definition of your top-level aircraft requirements, so initial assumptions that you want to take, how the aircraft should look like performance-wise in the end. So this is your starting point. Then, as we said before, you start with the baseline aerodynamics, do with the baseline aerodynamics an initial performance assessment. So what is the benefit, what is the key element that this aircraft will bring to that? So this is a kind of a slightly different setup to what we have seen before. So you do an initial step to get an estimation of where we are performance-wise. And then once you have the results and giving you the first estimation about performance parameters, but also fuel consumption that you have over the mission, you can then go into the different sub-modules which will now describe the single disciplines of your aircraft design, which means gas turbine sizing, so the kind of scaling of the propulsion system, giving you the right technology, which means thrust levels and also fuel consumption. Then you have the fuselage sizing, so which kind of passenger compartment you want to have in there, and also how does it match the overall aerodynamic performance of the aircraft. You do the weight estimation, also the center of gravity estimation in there, tail sizing, which is the next step, really to come up with a trim configuration. And this already includes flyability assessments. And then finally, with all the components sized and scaled to what you need for that configuration, you will get up with a component mass estimation. And here you have the flexibility by building up the database that you can just integrate over all the subsystems that you have assembled in your database. You can just sum up the weight and also automatically derive the center of gravity, which will then get you back to the performance assessment over here. So this is the second time once you go through that loop, and then you have different convergence loops which will ensure a fast calculation of that configuration. The big benefit now is if you take a look at the different jobs, here you can now work with your tool set and come up with different levels of fidelity in the tools and just insert them in the process. And this is how you can now mature the knowledge and the details of the configuration. At the same time, the database itself, so what we have seen before on the ADAM database, the number of details in that database will increase. So also other disciplines can now take additional data out of the database and also increase the level of fidelity in their assessment. If we now take a look at another example, like an unmanned air vehicle, there might be different tasks to that, because an unmanned vehicle, in most of the cases, as we use them today, are more for electro-optical sensor carrying, so more surveillance tasks, in contrast to the classical transport tasks that we see in passenger aircraft. So this might be a slightly different focus on where we have to look into to get the best design at the end. So you see some of the elements are still the same. So initialization, which means top-level requirements, also the assumptions are the same. You also start with wings, aerodynamics, and masses to get the tail sizing and mass. You see, in this respect, you dismiss that part of initial performance assessment. So you directly try to figure out a consistent aircraft design. Then you go into the required energy and power, battery selection. Also in this case, on an electric motor chain, you also have to consider the electric components like motor controllers in there, the electric motor and so on, and the propeller selection. And then in this case, if you have an electric propulsion system, you first of all need to converge this solution, because otherwise it doesn't match the aircraft performance requirements. And in the next step, you will again take the overall mass, and which is also something specific for unmanned vehicles, you have to find a configuration layout based on the components that you need to install. Because if your main mission is to carry a sensor, to do a surveillance task or a communication task, you want to have a dedicated performance characteristic, like on an electro-optical sensor. You want to have as much visibility as possible, and that might be achieved at different positions of the aircraft. Now you have to really do a component arrangement in the fuselage, which can drive the overall mission performance of the aircraft. So with that known, you can do the fuselage loft creation, because you're no longer bound to something like a passenger cabin, but you can arrange it according to your components. And this will definitely, again, affect your configuration aerodynamics. And so you have to close the loop again to get back to the trimmed situation on the overall aerodynamics, and then closing the loop again, which will drive you to a converged design. So what you can easily see, depending on the design task, it might be necessary that you assemble different steps of the process in a different manner, also using different tools and also other fidelity levels to come to that solution. And this can only be done by separating the tools and methods block from the database itself, which then in that case also supports that collaborative aspect that we have seen before. How is it implemented currently to also foster that collaboration over entities, that we have a dedicated setup, which means you have a distribution part, which is the upper part here, where you have all the tool repository, the databases, but also the baseline software in an online available manner. And the key element here is that you can now do a mirroring between the centralized database to your local computer. So you can work on your discipline, but you always link it again and see the differences in the center database, which is on the network. And this always ensures that everybody who is accessing that database gets an information if something has changed from an expert level, from a user level, into that main database where you have to redo your calculations. And this is the core element, how it has been set up to really ensure that you're always working with consistent data, which again has been a major driver for a lot of redesign work that was necessary in previous aircraft design tasks. To sum up the challenges and also the solutions that we have seen on collaborative aircraft design, a few comments on this one. So what we have seen that the aircraft process, design process, has to deal with multiple levels of tools and also methods to be used. So in initial phases, we have to rely on fast, simple methods, but we have to mature, and this means we have to integrate higher fidelity solutions in later phases without dismissing the knowledge that we already have assembled on that aircraft configuration. At the same time, to enable that, we have to consider framework tools that allow this kind of increasing fidelity in the design process. At the same time, also to increase knowledge that has already been assembled either in companies or on experts that have been working on dedicated solutions and products. This means to get both views together, we have on the one hand side to consider discipline-centered representation of the aircraft configuration, because the overarching disciplines like aerodynamics, weights, and also the propulsive forces do assemble the performance of the aircraft, the final product. At the same time, with the work sharing setup, we have to consider also that we have to do it component-centered, because this is where the expertise is going in. And if we go much more into detail of the aircraft configuration, we also have to work on the component level. This to ensure the consistency on the different groups working on that aircraft design, we have to work with the centralized database. And this is key because this is the only guarantee how you can have consistent data, multiple experts or entities working on the same configuration so that the results are really fused into one consistent aircraft design. So this is quite important. So the data management on that central database is one of the key elements that you have to ensure if you want to support collaborative design, which is necessary in that work sharing environment. And also to ease that working across boundaries of entities and also teams, you also have to work on standards and also some conventions that you have to take in the team. And this is quite important to just smoothen the process in that design exercise. So these are the overarching topics that you have to address to get collaborative aircraft design working in an organization. So good luck on your next design task, and thanks for watching this online course.
Hello everyone, my name is Peter Stütz. I'm Professor for Aeronautical Engineering at the University of the Armed Forces in Munich. And today I'm going to talk to you about digital avionics networks. So the first question that arises, what are avionics? And it's very simple actually. It's an artificial, a mixed word comprised of aviation and electronics. So it actually means all kind of electronic equipment on board of the aircraft. And again, today we talk about digital avionics networks. So first I'll give you some basic ideas about networking technologies and then lead you into 3 examples of existing networking technologies. This will be the ARINC 429, the MIL standard 1553, or also called MIL-bus, and the ARINC 664 AF-DX. So, since the invention of aircraft, it was always the goal to sample information, to sample data in various points of the aircraft on certain aircraft state variables, on the state of certain aircraft systems, and relay this information to parties who are interested in that data. Usually, that data sampling was achieved by having sensors, and such as, for example, if you want to measure altitude or airspeed, you need to have some pressure measuring devices at certain parts of the aircraft. And then the information, the data, was then relayed, for example, to instruments in the cockpit and displayed to whoever is interested in that case, let's say the flight crew, and the display of the data, the presentation of the data was done via analog instruments. Actually, the whole data processing or data transmission was analog. Analog in this case means that, analog voltage values, for example, were transmitted via a standard copper wire and then put on some kind of analog display or instrument. The problem with that was that this kind of data sampling and information transmission was added additional weight and complexity to the overall aircraft system. In the 60s and 70s, the idea was born, why not having a common media to communicate with? At the same time, digital data processing came up, and we all know that. We all have our experiences by now with that in our everyday life, using our computers, using our smartphones, using the internet and the web. All that ideas then came into the aircraft by using digital avionics networks. The most important point of this idea is so that now several components use the same media to communicate with. We see that in the lower part of the slide, where you see a kind of networked component system, which we now call the digital avionic network. In the community, it's also called the avionic bus. Bus here doesn't stand actually for the vehicle, but it's an abbreviation, it stands for binary unit system. So, as said, the goal of avionic networks is to enable communication between digital IT components. I already mentioned some kind of those components. Those may be sensors, computers, displays, actuators, just to name a few. There are specific requirements we put on these kind of networks. First, it's quite self-understanding, I guess, high data rate. And now comes something that's really airborne specific, high reliability, integrity. Real-time capability and deterministic behavior. In terms of safety critical systems, we have a couple of those on board of aircraft. It's very important that those networks work reliable and in an integer way. Please think that the failure of that networks might cause the loss of life, because certain systems, if they fail, would lead to an aircraft crash or accident. Now on to some more basics. Let's talk about transmission modes. In the easiest way, we talk about simplex systems or simplex transmission. Please imagine a regular radio broadcast station. Here, one entity, the broadcast station itself, communicates to a receiver, just some people having a radio with them. So here the communication is only one way, and there is no way for entity 2, if you have a look at the slide in the upper part, can come back to entity 1. If you want to achieve that both-way communication, we have to go into duplex transmission modes. Also here we can discriminate between half duplex and full duplex. Half duplex uses the same channel, the same media. However, only one sender at the time can send a message. So if entity number 2 wants to send a message back to number 1, it has to wait until 1 has sent its message and the message is processed. So no simultaneous transmission of messages is allowed on half duplex transmission. If you want to achieve a simultaneous transmission, then we need to have full duplex transmission mode. This usually requires a separate channel for sending in any direction, or a very sophisticated way of managing messages on one single channel. The problem with using a single channel for both-way simultaneous communication is that it would lead to collisions on the wire if two messages more or less meet during their travel through the wire, and therefore usually get either eliminated or garbled. Another thing we should talk about is topology. Here on that slide you see 4 types of topologies. On the upper left you see the star topology, and its unique feature is a centerpiece, which we used to call either switches or router. We all know that because that kind of topology is what we usually have also in our homes, in our offices. The switches are those we connect our computers, our laptops to if we have a wired connection or even a wireless connection, although that would connect directly to that central component. So that's the star topology. It can be even more complex. So we can form hierarchical architectures from star topologies and then with that create tree topologies, which is symbolized on the upper right. Another way to interface those different networked components is the linear topology, which you see on the lower left. Its feature is the backbone media, where all computer components connect to. And of course, again, if that fails, similar to the switch in the star topology, then the network would go down. A fourth topology type is the ring topology. It's for mere completion actually displayed here. It doesn't have a great meaning in the world of avionics. However, star and linear topologies, we will come back to that just in a few minutes. Now a word to the actual transmission media. For now, we do not have a widespread usage of wireless communication in aircraft. Usually we have wired, cabled networks, and it's worth to mention 2 important attributes of those cabling. First, and it's all about how to prevent interference with other networks, other components, other electronic devices. First, that's what you see in the upper part, is we are using twisted pair wires which are shielded. Ich wiederhole es nochmal. First, we are using twisted paired wires which are shielded. The twisting helps us to accept interference and disturbing signals from the outside in an equalized manner on both wires. And with that, it's easier for us to eliminate actually those disturbances later on. The shielding, prevents the input of outside interferences just into the wire pair. The second part I would like to mention is symmetric signaling. So again, think of the wire pair. We need to, well, bring on a certain wavefront that's traveling here to transmit that. And it's not that one wire just carries the reference mass and the other wire carries the information signal. No, we're doing it a little bit more complicated. We have the signal wavefront going on one cable, okay. It's different. We are having the signal front on one wire traveling as it is designed and having the same signal but just inverted on the other wire. With that mechanism, we help to prevent interference to other circuits. On the lower right, you see two different ways of such symmetric signaling which are used on digital avionic networks. And now last, within the section of giving some basic ideas, is what a generic network would look like in a linear topology. Again, you would see here the backbone consisting of a twisted pair wire. You would see several avionics components which would like to communicate with each other. They are called avionics LRUs, a very common abbreviation again. And LRU stands for line replaceable unit. I think that every avionics engineer once in his lifetime will deal with that abbreviation. And now we discuss several different implemented avionic networks. Here in this table you see a variety of realized networks, and you also see in which aircraft types they are used in. We're going to talk about three different types here, those marked in blue and bold letters. So the first network we're going to talk about is the ARINC 429. Well, some may call it, it's the mother of all avionic buses, and it's heavily used in large airliners still up today. The second avionics bus we are talking about is the MIL bus, the MIL standard 1553. And it actually comes from the military world. It has greater performance than the ARINC 429, was developed a little later. And lastly, we come to the ARINC 664, or also called AFDX avionics bus, which has been developed by Airbus and now is adopted also by Boeing. So now for the first, let's have a look at ARINC 429. The characteristics are actually pretty simple for a bus, and now you know all the basics and you can judge that by yourself. It's a simplex bus. It's unidirectional. So there's only one sender which talks to a lot of receivers. A lot means up to 20 receiver maximum. The wiring, as you already know also, is regular shielded twisted pair. It's a linear topology. And the actual message that's gonna transmit it is a 32-bit word. The bit rate is 100 kilobits per second. So please mind, we are talking more or less the 70s and the 80s. And at that time, this was pretty fast actually. Now in what you have at home is gigabit networks, or gigabyte networks. So that's a multiple times faster than that. Here you see, again, a generic architecture, and this now belongs to an ARINC 429 network. Again, it's unidirectional. What you see here is a sending entity, LRU0, that's transmitting, and it's marked with a TX for transmit. And you see 4 receiving entities marked with an RX. The wiring itself, it's only one twisted pair cable, as you have gotten to know before. What you don't see here is redundancy. If you want to prevent a breakdown of your network occurring from cabling problems on the backbone, you would need to install a second identical bus and also introduce some kind of redundancy management. This is done with ARINC 429, but per se, it's a non-redundant bus. Here you see the data word, the message that's relayed on a 429 bus. You see a container for the label, you see a container for the data, and some auxiliaries. On the lower part of the slide, you see an example of a message that might be transferred through the bus. So the label is 102. It stands for selected altitude. You would find all those labels and the affiliated values in the ARINC 429 specification, which by now has more or less the size of a telephone book. So selected altitude can be transmitted here. What is selected altitude, by the way? Well, it's, for example, the value a pilot would dial in his flight control unit in order to hand it over to the autopilot, to hand it over to the flight control system, to have that altitude acquired and maintained. The specification also helps the engineer to better formalize the message. It says, okay, the unit is feet. The range that can be dealt with 16 significant bits goes up to 65,536 feet, and therefore resulting in a resolution of 1 feet. It also goes into minimum and maximum transmission rates. And with that, you can build, or the engineer can build their own transmission system, having component 0 talking to component 1 to n. The problem with simplex buses is that usually you have a demand for communication in many ways, not only in one way. So if you want to also to have LRU 0 receiving messages for LRU 1 to n, you would need to install other 429 buses. Here you see 5 buses installed on LRU 0 to 4, just to enable communication in every thinkable way. This, of course, is a disadvantage of simplex buses, and the next example, the mill bus, deals with that. The mill standard 1553 network, or as we also call it, the mill bus, now is bidirectional, and more specific, it's half duplex. You know what that means. It can have up to 32 sending and receiving entities with it, and it's already dual redundant by design. It is based on shielded twisted pair again. It's again linear topology. The word size is only 20 bits now, and the bit rate is 1 megabit per second. So it's 10 times more performant as ARINC 429. Here we see the architecture. Well, looks kind of similar to the one before, but please mind first the second here backup bus called additional network. There is internal redundancy management. So whenever there's an error or a flaw on primary bus A, the network switches over to backup bus B. So that bus can be used already for safety critical applications. And another very important thing is that in order to realize half duplicity, we have a so-called bus controller, entity number 1, BC, that actually controls and orchestrates all the communication traffic on the bus. So nobody sends and receives on the bus unless told so by the bus controller. With that, collisions can be prevented by that managing agency, the bus controller. On that slide, you see some transmission control schemes. The bus controller actually orchestrates and manages all the communication traffic that's going on the network. No remote terminal, which are all the other components on the bus, are allowed to either send or receive a message without the explicit direction of the bus controller. On this slide, we see transmission control schemes for the mill bus. If the bus controller wants to send data to a remote terminal, it sends a receive command to the remote terminal, sends away the data, and then commands a status word from the remote terminal. If data has to be sent from a remote terminal to the bus controller, then the bus controller sends a send command to the remote terminal, which by itself then sends first its status, then the data. And last, if data needs to be sent from one remote terminal to another, then it's the task of the controller to tell the receiving remote terminal to get ready for reception and tells the sending entity to send off its data. So again, no communication takes place without the explicit consent of the bus controller. Now, the last network type we're going to talk about is AFDX. AFDX also stands for Avionics Full Duplex Switched Network, and the abbreviation already tells something, so it's full duplex. And please remember what full duplex means. It means all entities on the bus can talk simultaneously, and of course also receive simultaneously. So besides being full duplex, the number of network entities on AFDX networks is very high due to the possibility of hierarchical networking. And most important, AFDX, or talking about its specification, ARINC 664, is based on COTS Ethernet. You might have heard about Ethernet. It's the way of network communication you are all using back at your home. We're all using usually in our labs. We are using in our local area networks. And that was actually also the idea behind it. And I'll come to that in a second. The wiring here, It's unshielded twisted pair. It's a star tree topology, so we have a router or switch in the middle. The word size has dynamic sizes, and the bit rate now is 10 to 100 megabits per second. There even talks about 1 gigabit implementations here. Here we see the architecture, the typical star architecture with the switch in the middle. Now here we do not have remote terminals as we have it with the MILBus. We call those the end systems. In the most simplest way, you can think of a network card put into one of the LRUs. Here we have 5 LRUs, or 4 plus N. And we also have a second switch, which symbolizes the hierarchical decomposition of the overall network. And please feel reminded on, as I've said before, on the networks you're used to in your offices, in your labs, back at home. The idea to have that commercial off-the-shelf approach came from seeing the advantage of already developed IT components and system in the consumer area, in the industrial area. Before that, again, ARINC 429, MILBus, these buses were developed solely for avionic purposes, which is good on one thing, but makes it very, very expensive to develop that and also to advance the technology. The idea that was lying behind the AFDX network was to use already existing technology in industry and consumer areas, IT area, to be reused within the aerospace domain. In that specific idea, it was the Ethernet network as it was defined in the IEEE 802.3 standard, to use that as a baseline and adopt it to aviation needs. The advantages are at the hand. Most of those components were already developed, they were there. And not only developed for aviation, but to all other needs, which are actually more manifold than aviation. And further on, technological advancements were now expected, actually not only coming from the aviation community, but from the overall IT community. Before that, ARINC 429 and MILBus was solely developed for the aerospace community, which made the development very unique and also very expensive. Now having, let's say, the whole knowledge of the IT world at hand, it was expected that the technological advancement, the development of the AFDX bus was easier, faster, and also cheaper. However, of course, the specification of the, let's call it the standard Ethernet, did not meet all requirements with respect to determinism, real-time capability, and low latency on one side, as well as reliability, integrity on the other side, that were needed by aerospace applications. So that standard or that technology needed adaptations to fulfill also these requirements. And now we have a look on those. So the measures taken to fulfill those requirements, determinism and low latency on one side, reliability and integrity on the other side, are as follows. First, determinism and low latency. Here it was desired to realize full duplex communication without the danger of collisions. First generation regular Ethernet didn't care about collisions. Messages were just sent like that, and hopefully they went through. Usually they actually went through, but there was no guarantee they really were reaching that. If you have, well, regular, non-critical communication, that didn't matter much. It just, your message was resent. But that wasn't bearable for a lot of avionics communication where a certain transmission time shouldn't be exceeded. So for that, separated wire pairs for transmission and reception of information between the end systems and the switches were introduced. So no fear of collisions anymore. Further, static routing. The neat thing with Ethernet when it's used like an application of the World Wide Web is that the route, the package actually travel is not prescribed. By that, a dynamic structure of the whole network system can be achieved. That's nice for realizing a World Wide Web. It's a nightmare for having it on the aircraft. In the aircraft, you want to have a controlled system. With that, you also can allow a static routing. This means you can prescribe the individual way a packet travels through your network. And with that, also the time of travel is kind of prescribed. And as a third point for determinism and low latency, we have the possibility to have a strict bandwidth management by limiting transmission rates and frame sizes. Talking about reliability and integrity, redundancy was introduced to AFDX by a mere doubling of all components. So you have 2 switches and doubling the harnesses, also doubling the end systems, and by that you have already dual redundancy. And of course, as we've already seen with the MILBUS, you need integrity monitoring. That means you have to listen on both lanes actually if some messages are garbled or if you can detect any errors or invalid frames. So this was my short presentation on digital avionic networks. I hope you enjoyed it. If you want to have more details, feel free to have a deeper look in those 2 references I'm giving at the end of the slides. Thank you very much.
Hello, my name is Dirk Zimmer. I'm from the German Aerospace Center, or Deutsches Zentrum für Luft- und Raumfahrt, in short simply DLR. More precisely, there I'm located at the Institute of System Dynamics and Control at Oberpfaffenhofen near Munich. Here we engage in a lot of multidisciplinary activities, such as the modeling and simulation and control of robots, the design of Mars rovers, the optimization of electric vehicles, but also there is aviation, and this is going to be today's topic. If you look at a conventional aircraft of today, we find that it is mostly driven by 3 domains of power. There is the pneumatic power that is taken directly from the engines and mostly used to drive the environmental control system. There is the hydraulic power, which is mostly used to drive the actuation system for the control surfaces. And there is electric power used for almost everything else, the cabin lighting, the galley ovens, the avionics, you name it. There is a certain trend, due to the advancement in power electronics, to go towards a more electric aircraft, so to reduce or get rid completely of the pneumatic power and to reduce the hydraulic power and make more electric power. The Boeing 787 is such an example. But is this really a better aircraft? It's difficult to tell because there is also the Airbus A350 XWB, and this is still a quite conventional aircraft, but it is competitive. So in order to really say how you should build a future aircraft, we have to look at all the systems in total. So the electrical system, the climate and cooling system, the actuations, also the engines, the landing gear, and many other systems. And we have to create one common methodology to model and simulate these systems and bring them together for a flight performance evaluation that tells us how to design the system optimally. Well, I want to give you a short glance at what we do in our modeling and simulation activities regarding these highlighted areas. So, for instance, there is an electric system. Here is an example of a classic single-aisle aircraft with 2 engines, and each engine has 2 generators. And there is the APU. You see there is an AC bus bar and a DC bus bar for the essential avionics. We can use such models to, for instance, model a failure case. So when the engine is failing, the 2 generators will fail, and the corresponding bus bars need to reconfigure. This here is an example model of something that is on board of almost every aircraft since about 70 years. This is an air cycle. When you fly in a plane, you like to have good climate around you. You prefer probably to have 21 degrees of Celsius. The point is the air that you breathe is the one that is taken from the engines, and that enters the fuselage with roughly 250 degrees of Celsius and 2.5 bars. A little too hot for you as a human being. So it needs to be cooled, and for this, outside air is being used. This is a device called a ram air channel that's typically situated beneath the wings. Then the hot air from the engine is coming in, it's going through the heat exchangers, a compressor, heat exchanger again, water is being extracted, and finally it can be brought to the mixing unit and later on to the cabin. Such a model can be integrated into an overall aircraft model where we model the complete cabin air recirculation and also other aspects. This here are components used for the modeling of electric mechanical actuators. There are motors, electrical motors, inverters, gear models, ball screw elements, all what you need to model an electric mechanical actuator. We'll come back to that in a few minutes. These models can also be validated using, for instance, a test rig here. Last but not least, we shall not forget that all these systems need to be integrated into a flight performance simulation. Here you see an aircraft flying over Munich. The blue surfaces represent the load on the wings and on the fuselage, and there are 2 aileron surfaces modeled as well. In our tech lab at the German Aerospace Center, we brought all these modeling and system capabilities together. This is an overview of the whole. This is me driving a virtual aircraft in a virtual cockpit with a virtual reality glass. So a lot of stuff is virtual here. So I'm enjoying the view, and the motion is reflected by the robotic motion simulator, which you see here. The aircraft systems are simulated here. This is the electric system, the climate system, and the aircraft flight dynamic simulation with the wings shaking. A pilot can sit on board of the robotic motion simulator and experiencing the G-forces. This is a very flexible environment that can be used for a multitude of applications. We use this to check flight dynamic control laws, early testing. For instance, if there are new electromechanical actuators concepts, we can first test them here before we go on quite expensive flight tests. And it is a good thing to test the real-time capability of all our models. Instead of studying the dry theory and history behind this language, I think it is best learned by jumping right into practice and look at an example. And since we are from aviation, let us look at a fitting example of a hydraulic-driven actuation surface. Well, this here would be the corresponding modeling diagram, and the program that you are seeing is one of the tools for Modelica that is available. Since it is a standard, it doesn't really matter that much what tool you use, this diagram will look more or less the same in all of them. Let us go from modeling to simulation, and there we can simulate the system for 10 seconds and look at the result. So you see here the actuation control surface moving around the hinge line here. The green arrow represents the aerodynamic force. So I'll show once more. Acting on it. We can also look at the plots to see the quality of this control. So the blue line represents the control signal, and the red line is the actual motion of the system, and you see it follows the control motion quite well. Also, we can look at detail at the mechanics. So this is the hinge line. Then there are 3 revolute joints, and this red element here represents a translational piston, causing the actual motion by extending and retracting. And you see here, this is a kinematic loop, and we do find the same loop in this modeling diagram. So this is the hinge line here, and this is the revolute joint. The actuation control surface mounted to it is represented here by the mass, and mostly we care about the inertia, and visualized by this box. This here is the prismatic joint extending and retracting, causing the actual motion of the system. The aerodynamic force is modeled very simply. You could say simplistically, by taking the angle of the control surface, doing a very simple computation with a few parameters like ratios for lift and drag, and getting the force out of it. Furthermore, this prismatic joint is driven by an hydraulic piston. There is a hydraulic fluid coming in and going out. If we look at the model itself, we find a simple hydraulic construction. First of all, there's a double piston element that can move upwards or downwards, and then there is this valve construction where I can switch the piston either upwards or downwards, causing the fluid to flow either in one of these directions. In between, the valve is a little bit leaky, so that the fluid flow is damped, and in case of a malfunction, the piston wouldn't jam, it would still be able to move and give way to the aerodynamic forces. If you look at this element itself, we do find that there are a few basic equations actually modeling it. So there is simply the law that pressure times area equals force. And there is the corresponding law for this energy transformation, that the translational motion times the area is the volume flow of the hydraulic fluid. That is very simple, and so does every component has ultimately, in the end, a few equations. And if you collect the complete system together and we check it, then we see that this complete system has 1,355 equations. That seems like quite a lot, but please keep in mind, many of these equations are quite trivial and are optimized away once you generate simulation code out of it. The thing that I haven't mentioned so far is the controller here. So the control signal coming from the aircraft is simply assumed to be a timetable, and then I have a simple PID controller trying to get the measured angle in alignment with the set point by opening and closing the hydraulic valve. I can see, for instance, the impact of the pressure level. For instance, if I lower it a little bit and simulate again, I will see that with less pressure I have less control authority, and the quality of my result is worsening. So, since I talked about the electrification of aircraft systems before, let us do this here in this model and replace the hydraulic actuator with an electromechanical actuator. So, first I have to make place for this electromechanical actuator by deleting the hydraulic parts. Well, then I need the components for the electromechanical actuator, which in this case can be found in the standard library. Fortunately, many volunteers and smart people did us a favor and created a huge Modelica standard library that contains various domains. And you see there's also an electrical domain, and within this we have machines, and with this I, for instance, find this simple DC permanent magnet machine. Whether it's suited or not, I'll just take it here because it is simple to control. Well, I now need to bring the rotational motion of this motor to transform this into the translational motion that is needed by the piston. So I'll need gears for that. Again, I can look at my libraries and, for instance, find here there's a rotational part in the mechanical libraries. There's an inertia. Well, I should probably model that because my motor is going to run at high speeds, so it will matter. Then there's a gear. I should move it the other way around so that I go from a high-speed motion at the motor side to a lower speed motion at the load side. And then I'll need an element to translate the rotational velocity into translational velocity, and this would be the corresponding part. Again, I have to enter a parameter. Let us say it takes 200 radians to do a meter. So now I have done the mechanical part. I still have to complete the electrical part. So my motor needs power, and hence I'm looking for a power source. I find that here under the sources. There's a signal voltage. That's just what I need, because I also want to control the voltage so that I can control the speed. Also, I should ground the complete circuit, which I can do like this. And then I need to adapt my controller. Well, that would actually be quite a job, but I replaced the control design here with educated guessing and simply adapt the parameters a little bit. So first of all, I need to allow a higher output. So maybe I work with 270 volts, a plus and minus. And hence I also should increase the gain by a similar factor. Let's put 1000 in here. Then I need to specify also the parameters of my motor. Well, let us assume I have plus minus 270 volts, so it's 50 volts in total. 1000 rads per second, 50 amps. That's a bit of a lot, but who cares? All right. Let's see if that works. And indeed, it does. But you can see we do have now a few problems. The inertia of the motor and the concept of the control is causing now an overswinging behavior, where we had a lagging behavior up front with the hydraulic element. With an electromechanical actuator, I really need to care about the inertia of the system. So that would, for instance, then be the job of a control engineer to devise a better control scheme for this motor than the one that I've presented here. Maybe I can play around a little bit. Reduce. Let's see if it does have a little impact. Maybe I'm making things worse. Well, I improved it a little bit, but sure, there's a lot of work to do. And this is, for instance, what you can need such models for. Now, where we have seen a practical example, let us review the underlying principles of the Modelica language. First of all, it is an equation-based language. That means all the things ultimately consists in differential and algebraic equations. It also means you can take your textbook and open it and apply the equations that you have learned during your engineering classes. Also, you can write these equations down in an acausal form, which means, for instance, if you have the law of a resistor, Ohm's law, which states a voltage is equal to a resistance times the current, then you can just write it down like this. You don't have to concern yourselves whether the voltage is computed out of the law or the current. It doesn't matter. The tool will do the job. This not only applies to individual equations, it does apply to the complete model. And this is quite a powerful tool. So instead, for instance, of doing it the classical way, where you prescribe the thrust and then compute the trajectory of an aircraft, you could do it the other way around. Take the same model of the same aircraft, prescribe the trajectory, and then compute the required thrust out of it. Also, Modelica works with physical connectors. We don't work that much with signal flows. The actual physical connections are represented by the principles of thermodynamics using pairs for a potential variable and a flow variable whose product often is power. So for instance, electricity is a good example. Again, you have the voltage potential and you have the current. The product is power. And mechanics, you have the velocity and you have the flow of impulse, also known as force, and again, the product is power. Using these principles, you can model across the domains. Also, this is done in an object-oriented way. We have seen that our total system model of before had over 1,000 equations, but they were spread among many different components and levels of hierarchy. Furthermore, whereas all the basic model is done textually using equations, all the higher level modeling is done graphically. Let me conclude by a final perspective why the simulation of systems will become increasingly important for the future of aviation. This is simply by extending a well-known trend. If we look at how thrust is generated, it is always a mass flow times the delta in velocity that you impose on that flow. Well, if you're in space, you have to carry the mass around with you, hence you'd like to have a large delta V and use as little mass as you can take. But in aviation, we fly in a medium. We want to use this medium and hence we would like to have a small delta V and hence increase the mass flow that we accelerate. And you can see this is what's happened in aviation history so far. We started, for instance, with the jets. Then the jets were bypassed and you had a turbofan. And ultimately, there is the geared turbofan with an ultra-high bypass ratio of today. How can you go further? Well, you could, for instance, electrify the system by boosting the fan, making an even larger fan. Another concept for an even higher bypass would mean that you have a parallel hybrid. So you use only one of your engine cores in cruise and transfer a good part of the energy to the other fan, where the core is inoperative. And ultimately, you could build one central power source on board of your aircraft and distribute the energy to many distributed fans distributed along the aircraft fuselage. So you will see these more and more become system topics, and it is important to model these different architectures. And again, language like Modelica can be used for this. Here you see the example of a serial hybrid. I may show you here with my mouse pointer. You'll see this is the energy generation part. So that's a gas turbine, an electric generator, and then the power electronics. Alternative, there is a battery for an emergency scenario, or for instance to be used at top of climb. And then there are two fans being used to propel the aircraft, also connected here with the power electronics. And this model is even incomplete yet. For instance, a lot of waste heat is being generated by such an architecture, and this heat needs to be dissipated from the aircraft. And this is quite a difficult task, so we would need to enhance this model with a thermal model and then study the impact on the flight performance and aerodynamics. Well, I guess that will keep us busy for quite a while, but for the moment, I want to say thank you. I want to also thank all those who contributed with their material to the slides. And I hope you enjoyed the small lectures, and maybe we see each other again.
Welcome to our lecture on parameterized reduced order digital models in aerospace, which is composed of two parts, namely part A, which we will just discuss today, which I called hard computing methods. We will also discuss later a part B, which is called soft computing methods, and both parts are parts of our Munich Aerospace online course on digitalization in aeronautics and space. Let's look to the title, which sounds a little strange. First of all, the question is, what do such reduced or surrogate digital models mean? The second point is, why do we talk about their parameterization? And the third point is, why do we have two parts, part A and the part B? And today we will focus on part A, namely the fundamentals of the related methods, and equally important, a series of applications, and not only from a numerical and digitalization point of view, but also from a physical and technical background point of view. Before we jump into details, I would like to make some remarks on myself. After having finished my doctoral dissertation at TU Darmstadt, I was working for 20 years in aerospace industry, followed by 20 years in TU München at the aerospace department and with lectures on aerospace structures, materials, and related subjects. So the detailed points we are now looking more into is, what do these reduced digital models mean? Why do we want to parameterize? And why is our lecture composed of this part A and later on the part B? So let's discuss this with a typical example. And first of all, we have to observe that, especially in the development, but also in the operation of aerospace systems, we have to observe parameters which might vary a lot. For example, in operational conditions, the operational parameters which relate to aircraft are the payload mass composed of fuel and passengers, and also the center of gravity of fuel and the center of gravity of the aircraft, the Mach number, the flight velocity, the flight level or flight height, and so forth. And in order to achieve a good design, we have to treat in the development and design phase possible structural and generally system design parameters, which are the plan form of the aircraft, which are certain shapes of the wing and of structural parts, stiffness position, geometries, types of materials, and so forth. Generally, in the design and development phase, we want to achieve some goals, but most of all, we have to satisfy a lot of requirements. And the important point is that these development design steps very much depend on digital models where we carry out the optimization steps to achieve the goals and to satisfy the requirements. So let's continue with this example by looking on the dynamic gust load elevation in aircraft wings, which means that we first look onto the stationary lift distribution, neglecting effects of the fuselage, shown here in the dotted line. Then we have the gust load effect. If the aircraft is flying through a gust and excited by a gust or turbulence, the lift is significantly increased, especially so at the outer wing edges, and which means that the wing root bending moment is increased, which is not so nice, especially also for the aircraft structure and for the required mass and weight needed. And in order to control this and to alleviate this, we are applying the so-called wind load alleviation. There is a passive means, which means a proper aeroelastic tailoring of the wing such that it deforms under such gust loads in a proper way and does not increase so much the outer wing lift. And secondly, an alternative and often investigated also are active means, namely the proper use and proper control of flaps in order to influence the aerodynamic forces acting on the wing. In the end, for such alleviation problems, we are talking about mechanical system or structural control interaction problems, which means that we are dealing with a plant, the aircraft especially, which is disturbed from outside by a disturbance W, and this disturbance and the output from this disturbance is measured by certain sensors, which the result of which is an input to our controller, which actuates the plant, the aircraft in a proper way in order to optimize and maximize the performance. And to determine the parameters, especially those of the plant and of the transfer function of the controller, we have to deal with these transfer functions G and H. And the essential point is, and the basic idea is that these transfer functions are often a result of large system models, which specifically relates to the transfer functions G of the plant or aircraft. And this is the reason why we are looking to the condensation and reduction of such large systems in order to properly determine the interaction of G and H for the overall system. So let's briefly outline why we have a lecture part A and a lecture part B in order to determine such reduced models which are also parameterized. In the approach of part A, which is the subject of today, we are starting with a large-scale system model, which is drastically condensed and reduced, which we see in the center of this view graph. And the concept and idea is that the parameterization shall also work on this drastically reduced model. So in parametric studies, in optimization studies and so forth, we then only deal with such reduced models, which from time to time, of course, might have to be updated, which we will see later. Such a technique very well runs on so-called clearly structured problems. And there's another technique which is subject of our approach and discussion in part B of our lecture later on. We again have two parameters, parameter 1 and parameter 2 on the x and y axis. We have the response or output of the system, and we have some reference points which might be either taken from simulation, which might be taken from experimental results or databases, might be taken by from knowledge bases and so forth. And these reference points help to establish and serve to establish so-called approximation functions. And instead of the overall large-scale model, these approximation functions as functions of the parameters are used to investigate the system. In both type of approaches, our aim is a drastic reduction of the computational effort during the design and development process. But at the same time, we have to take care that the surrogate response, which is given by this A circumference, very well represents, or sufficiently well represents, the high fidelity model, or in other words, the approximation error shall be small. So let's look into the basic and fundamental steps of such reduced and parameterized models which come from our part A type of problems and methods. We have seen that we are starting with a large-scale system model, which somehow is reduced to a small-scale model and which shall represent the overall behavior. But if the small-scale model is not yet parameterized, we have to parameterize and do the parameterization process again, apply to the original large-scale model when we are modifying the parameter. And modifying of parameters is a process and step often done during the development phases of any system, including aerospace systems. And so the reduced model has to be parameterized. So we are again starting from the large-scale model, which you see on as a symbolic representation on the lower center side of the view graph, which is condensed, but also which is represented as function of our parameters, which determine the behavior of the overall system parameter-wise. So we can investigate the parametric dependence and parameter study on this reduced model instead of using large-scale models and doing the condensation again and again and again. So let's look into even more detail of this approach. Again, we are starting with a large-scale system model represented by a large-scale matrix representation, which shall be shown here on the left upper part of this view graph. And often different subsystems of the system, of the aircraft, of the aerospace system, contribute in a different way to this overall model, and this means that different submatrices are contributing to this. And one has to find, in order to reduce these submatrices and to superimpose them to a small-scale model, one has to find a proper projector. And one has to find, from a mathematical point of view, a projector operator V, which projects these subsystem matrices into a very small space, which might be a Grülow space or any other small space in vibration. It might be a modal space or other possibilities exist. But the important point is, you see on the lower part, that typically such a projector is composed again on large-scale matrices. And this shows that the application of such a projector after modification of the system matrix due to parameter changes, this application and determination means a lot of computational effort, and it shows you that it is better to modify and to use this parameterization already on the small-scale model and on the reduced system. So in order to really save computational effort in a sequence of parameter modifications, it's relevant and important that not only the models are reduced and the projector is determined, but also this projector V is parameterized by these parameters which influence the behavior of the system under investigation. This view graph kind of summarizes the previous 2 or 3 view graphs, namely we have the large matrix, the large system model on the left-hand side, the contributions of the blue, yellow, red, green parts of different parameters and subsystems. These matrices are projected into a significantly smaller space via the projecting operator V, and the superposition of these projections results into this very small, rather small scale system model, which is shown on the lower part of this view graph. What's left over is, since we have to deal with parameter variation in the design and development process, the question is, how is this projector V to be parameterized? Okay, the parameterization of the projection operator V and the contribution of the different subsystems and submatrices is done in the following way in principle. And in principle means there are also again different means to do this. One fundamental principle is, and often used, is to use linear or nonlinear Taylor series expansion. Let's assume that this matrix A, which we are parameterizing, depends accurately or approximately on this parameter P to the power R, and then the Taylor series expansion says that the new matrix A, due to parameter modification of delta P, is the original matrix A plus the summation which we see in the center of this view graph, where the partial derivatives of this matrix A with respect to these parameters is used, and the delta Pi, the different parameters, are then applied to. The crucial point here is to determine this gradient dA via dP. And this in well-structured problems can be often done by so-called semi-analytical means. So this derivation, this differentiation can be done on the matrix itself in a semi-analytical way, and semi says it's done on a computer numerically. If this does not work in certain circumstances, one can apply finite difference. Of course, it means more computational effort, but keep in mind that finite difference can be done in parallel on many processors in parallel, and then again, at least computational time, wall clock time is saved. What's also important is that possibly the chain rule should be applied if one knows and if one can estimate the influence of this parameter on these different matrices. Namely, let's assume if this parameter is a 1 over P influence, so an inverse influence, then the gradient of this matrix A and the coefficients of this matrix A are as function of this parameter P, and the gradients are obtained via this chain rule, the original coefficients divided by P squared with a minus sign, and all other terms of this matrix A which are not influenced by this parameter are set to 0. It's a partial derivative. And let's assume alternatively that this parameter influences this matrix A in a quadratic, by a quadratic term. Then the chain rule tells us that the original coefficients of this matrix A can be determined by multiplying these coefficients with 2 and the parameters P. And again, because it's a partial derivative, all other parameters not influenced by P's are set to 0. And this way of expanding and parameterization very much determines the quality of the interpolation and the parameterization and the quality of this approximation itself. Let's look into this digital model reduction and at the same time its parameterization more in the sense of a flowchart. First of all, on top, we are starting with an overall system model. It might be a finite element model, a computational fluid dynamics model, a coupling of both, and so forth and so forth. Any proper matrix modeling method can be used. Then we have to consider the projection, the model reduction, and its parameterization. For finding such a projection, there are different methods, as just previously mentioned, and the parameterization means either Taylor series expansion or an interpolation technique and so forth. Once this reduced model and this reduced parameterized model has been established, the simulations can be done on this reduced model, and it's not only the simulations, but essential is, and keep in mind, for practical applications in the real-world development processes, one has to consider the iteration steps on modifying the parameters, so one has to repeat this again and again, but on the condensed and reduced model. Okay, doing all these steps, we have to know, is it good enough? Can it well represent the behavior of the system? Can it well represent the behavior of the system even after modifications of parameters? So we have to assess the reduced and parameterized model. An often used technique is to look into relevant transfer functions, especially in computational and structure interaction problems, the transfer functions of loads to responses, the transfer functions of actuations to the system responses and system outputs are looked into with and without model reduction. And here in the center of this view graph, you see such a typical transfer function over the frequency of the system. Originally calculated with the blue curve, which is hidden behind the red curve, which represents the large-scale models where 1,400 so-called states or modes or eigenfrequencies or vibrations are determined. And on the reduced model, only 26 states or eigenfrequencies and modes are used. And you see that such a transfer function and the representation of the significantly reduced model and the original larger scale model can be assessed by such transfer function. At least it tells us that up to 20-30 Hertz, this reduced model works very well. And if we are looking into this assessment, we have to, as always, when one is looking into assessments, to establish assessment criteria, which means in this case we are looking into the covered frequency band and the covered modes. Covered means in the relevant frequency band and relevant modes. Effective masses are the residual modes which are not considered. And from a control point of view, of course, controllability and observability plays an important role. And because we are talking about parameter variation and parameterized reduced order model, we also have to look to which extent these parameterized reduced order model are valid for these different parameter changes. In order to better understand what we mean with this gust load behavior or this aeroelastic behavior under turbulence, we see here the performance and the behavior of a simulation model. Namely, when we start this model, we see that these aircrafts and this finite element model of this aircraft, this aeroelastic model of the aircraft, experience a rigid body deformation, which also causes or may cause some discomfort of the passenger. But also we see at the same time the wings of this aircraft are kind of vibrating and get an elastic deformation and a vibration dynamic deformation, which in this case is relatively small, but there are other cases where these vibrations might become large. Now, to make things more concrete, we are looking into a series of applications in aerospace systems, and not only from a model reduction and model condensation and parameterization point of view, but also I will address some points of the physical and technical background of these applications. Let's start again with this aircraft model and aircraft simulation model and behavior model, where we are looking into different lift load distributions. As mentioned in the introduction, we have three different lift load distributions. The first one is a so-called stationary one. When we neglect the fuselage influence, it's the elliptic lift distribution over the wing. Assuming that the aircraft is flying into turbulences and into a gust, the wing might torque and the angle of attack might increase, especially at the very edges of the wing. And this means that the lift is increased at the outer part of the wing. The overall lift is increased, which causes not so comfortable behavior of the passengers, but at the same time also causes an increase of the so-called bending loads and bending forces at the wing root, which are shown here in this red diagram. So in order to reduce this gust load effect, one is looking into such a load control technique, which are different ways to achieve this, namely the so-called passive way via aeroelastic tailoring. The wing is designed in such a way and the parameters of the wing are determined in such a way that due to the natural pressure distribution over the wing is deformed in such a way that this negative effect of gust loads is minimized and reduced. Alternatively or additionally, one can do this also by active means, by a properly controlled use of flaps, where these flaps are used to enforce this proper bending torsion behavior to get a good overall lift distribution, which minimizes and reduces the bending moments and at the wing root, and also reduces the not so comfortable behavior for the passenger. So from this behavior we see that these strong interactions of aerodynamics and vibration has to be avoided. These flutter cases, as they are called, have to be avoided, not only in order to avoid large deformations, but also to avoid such large forces that the structure, the wing, and in this case also the bridge, starts to break. So the modeling of this behavior results into so-called aero-servo-elastic simulation models. Aero means aerodynamic, servo means control and actuation, and elastic means the vibration and deformation behavior of the aircraft. This means that we first of all have to establish a finite element simulation model for structural dynamics, which you see here for an aircraft, so-called half model on the left-hand upper side. The differential equations in time in the left center side, and also including rigid body modes on the lower part. The upper part of the aircraft shows an elastic eigenmode, a vibration frequency of the wing, together with a smaller amplitude in the fuselage. Assuming this structural dynamics behavior to be well represented by these models, we have to also take into account the aerodynamic behavior. It might be either a steady behavior or, especially in gust, it's an unsteady behavior. So one takes usually the doublet lattice method or any other computational fluid dynamics analysis technique. And these two large models have to be combined and coupled together. And in order then to carry out the parametric studies, one does not want to treat these investigations on these two coupled large-scale models, but on the reduced model and the parameterized reduced model, like the determination of the eigenvalues, which are sketched on the lower right-hand side, whether they are, what are the real parts, what are the imaginary parts of these eigenvalues. So what does active dynamic load elevation means technically for the aircraft? This can be seen in this figure and in this sketch for the splendid wing body configuration, where we assume that this splendid wing body aircraft is excited dynamically via disturbances, aerodynamic disturbances, and these disturbances are measured by sensors in front of the aircraft, for example by certain radar techniques or pressure sensors, but they are also, the response is also measured by acceleration sensors in the wing, which gives for the feedback loop of this overall control loop the sensor input of this behavior of the wing. And by applying then a combined feed-forward, feedback control loop, means that the overall response, the dynamic response of the wing can be drastically reduced. This is shown here in this transfer function, where a typical displacement at the wing tip is shown versus the frequency of this wing, the resonance or eigenfrequency of this wing. And we see here this blue curve where no active action is taken, no flaps are used to counteract the disturbances and the influences of the gust. And when the control loop is applied, which triggers the flaps such that this influence is reduced, this is shown in the red curve, and we see that practically the response now, the overall response now is only half of that of the uncontrolled behavior. The next application is taken from space engineering. We are looking into the vibration control and the vibration design of very flexible solar arrays. I'm saying very flexible because these solar arrays, as one can see here on the left-hand side of a satellite in orbit, of course it's an artist's view, and a solar array on ground in a test hall, in a test laboratory. These solar arrays are quite large and floppy structures, so their eigen or resonance frequencies are also very low. They might be even smaller than a tenth of a hertz. So in case such solar arrays start vibrating, they might introduce disturbances on the satellite, which one wants to avoid to the most possible extent, because it might cause small tumbling movements of the overall satellite, which influences its overall performance and behavior. We were looking into more detail, and we are looking into more detail of such a solar array panel. Namely, you see here on the right-hand side such a single solar array sandwich panel, which we want to control in its vibration behavior both in orbit and during launch. And for investigation, we first started with the overall full-scale model, and we simulated the behavior of and the influence of 10 parameters of such a sandwich panel, namely the modulus, Young's modulus, the thickness distribution of this sandwich panel, and also the possible positioning of non-structural bases. The original simulation model had more than 11,000 degrees of freedom, and the drastically reduced model, which we were looking into and handling together with parameter studies and together with interfacing with control behavior, only finally had 51 degrees of freedom. And what we did, we were looking into different modes, vibration modes, also among others to determine proper positioning of actuators to control vibration. And control always means to always have a proper positioning of sensors in order to guarantee good observability of the behavior of this plate. As mentioned in our introductory part and in our basic discussion of the methods, the validity of these reduced and parameterized models has to be checked. Of course, this was done here also. Namely, different parameter modifications of these 10 parameters have been carried out, and you see these parameter modifications were between 0 and 40%, depending on the different type of parameters. And what's given in the main graph are the different frequencies and modes, starting from frequency in mode number 1 up to frequency in mode number 20. The lower curve shows the behavior, the frequencies without parameter modifications, and the two upper curves, which practically match each other, shows the behavior of the results of full model simulation and parameter modification, and reduced model simulation and parameter modification. And you see these well matches with each other. So this gave us sufficient confidence that at least in this variation range, which is showed at the upper part and left upper part of this view graph, this reduced model and parameterized reduced model can be reasonably applied. As always in development of aerospace systems, we should correlate, once hardware is available, we should correlate the simulation results with the test results. And this is shown here. This is a transfer function of such a sandwich panel versus frequency, where the response is shown with uncontrolled vibration behavior. These are the large peaks, and the blue and red curve shows the behavior under vibration control. And when we correlate this with tests on such a panel, you see that this behavior from simulation and from test correlates very well. These are nearly quite identical curves, and of course can apply different mathematical criteria for correlation, but also this qualitative correlation tells it's quite good. And by the way, this control and vibration control in that case was done by applying control actuation via attaching piezo ceramic plates on the sandwich and properly triggering this with a control loop. Our final example is taken from high-precision ground telescopes and their active optics. What do we mean by this? There's just a large ground telescope under development in Europe, which is called the Extra Large Telescope, ELT. And this extra large telescope has a main mirror diameter of close to 40 meters, which is quite large and a big step in astronomical ground telescopes. And these mirrors and these large mirrors have to keep their shape very accurately, even under very different disturbances. And in order to guarantee this, one is sectioning this large mirror of 40-meter diameters into many small sections. And we see here a single panel or a single section of this large mirror, a view from the rear side. First of all, if you have a closer look, you see it's a finite element model in this case. And we also see the structure on the rear side, where also the actuators are integrated in order to control and counteract the deformation of such a panel due to external excitations. So it means that one has to deal with very large models, and one has to deal with controlled structure interaction problems, which in the end require many thousand, even more than 10,000 actuators. And these very large models have to be properly condensed in this overall simulation on structural, control, and optics behavior. And the overall integrated model, the structure, control, optics, end-to-end model of this telescope is shown in this view graph. Take first the structural model, the optical model, but also we need to properly model the actuators which are attached to the rear side of this main mirror. We have the controllers and so forth. And we have to take the disturbances, which are wind load, seismic disturbances, even solar pressure and thermal behavior, temperature changes. But it's also interesting to consider this disturbance shown on top, which is the so-called atmospheric turbulence. The atmosphere always is turbulent, and which means the air has different densities, and optical waves going through this air with different densities are disturbed, and this is also to be compensated by this active control technique. As mentioned, we have now to assess the validity of this reduced model and the validity also with respect to parameter variations. And the validity can be well checked via transfer functions. We have seen this graph already. It comes from this large ground telescope. Remember, the original model had, with respect to finite element degrees of freedom, 500,000 degrees of freedom. The reduced model only, in quotation mark, now has 200 degrees of freedom. Or from a control point of view, in the original model we determined 1,400 states, while in the reduced model we only determined and had to determine only 26 states. And this transfer function shows us that it really works for frequencies and eigenfrequencies which are relevant here from a structural and structure optics point of view for up to 10, 15, 20 Hertz. And what's important now is the result or the behavior of this main mirror, of this large mirror, under different external disturbances or loads. The left-hand side shows deformations of this mirror, a view from top of this mirror with isocontours of deformations. They are in the nanometer range, but we see that they are differently distributed over the overall surface of this mirror. While once control is applied to each of these segments, these behavior is very smooth and there's practically no real variations and practically no deformations of this mirror. And this very well also shows in the optical results, in the astronomical results. The lower figure and lower picture shows a photograph of an observation made from such telescopes from ground into a stellar object. So it's practically the same photograph taken from a satellite or space telescope is shown here. And you see it's even a little worse, mainly because one can put in a lot of control activity, actuators and so forth on ground telescopes, which in the visible wavelengths and in the near visible wavelengths very well improves the behavior of these ground telescopes. Let me summarize with some final remarks and a brief outlook. First of all, I think we have seen that reduced order models, and especially so also parameterized reduced order models, can be beneficially applied to different aerospace systems, and especially when several disciplines are involved in so-called multidisciplinary problems, structures, fluid dynamics, control things, and so forth. And we have also seen that also there is a reasonable need for parameterized reduced order models to carry out this parameter studies, this optimization also on the level of reduced order models. Of course, the final step should be then done again on the full model. We have also seen, I think, that the whole process is not really an automatic process, but one has to introduce significant engineering knowledge in order to well investigate and establish a proper sequences of sub-processes in this context. And it's good that this knowledge has to be introduced, because it means that these engineers and people are doing this are still needed with their knowledge. One example for future research activities is that the people are more and more looking into doing reduced order modeling and parameterizing in nonlinear systems, and also doing control on this level. Those things which I have shown you are not only done by myself only, but they are contributions from different doctoral students which I had in our institutes at TU München. And I would only like to mention two of them. It's Dr. Enyung Yo and also Michael Müller, who did these activities in the large ground telescopes. And I would not only like to thank our doctoral students, but I would also like to thank the audience for taking part in this video session. Thank you very much. And this final list of literature, which is a very short list by intention, shows you that there are further sources and references and textbooks available you might look into. I would specifically like to attract your attention to this toolbox, which is published by the Chair of Automatic Control of Technical University of Munich. Their homepage is also given here, and you can find here as well. Thank you very much again. Welcome to our lecture on parameterized reduced order digital models in aerospace, which is our second lecture on this matter, which we call the part B, where we mainly focus on so-called soft computing methods to establish such models. And again, this lecture is part of our Munich Aerospace contribution on the online course Digitization in Aeronautics and Space. So aerospace systems are characterized by a wide set of different parameters, namely operational parameters, which have to do with the payload mass, the flight Mach number, the flight height, flight level, center of gravity of the mass, and also certain design parameters, which mainly relate to topology, shape, geometry, material properties, and so forth. And in the end, design and development means to select these parameters such that requirements are satisfied and design goals are achieved. And this process, which might take several years to come to an end and to an optimal solution, is heavily based on digital models, and so it's a digitally driven development process. Why do we have these lecture parts A and B? You might remember in our lecture part A, we were focusing on so-called large-scale discretization methods, which result into large matrix equations, and these matrices are reduced, significantly reduced in size, which means that then it's the lower order model or reduced order model. Today we will discuss so-called surrogate models, which have a little bit different approach. Namely, parameters are also varied. Maybe the exact response for these parameters, system response for these parameters, is obtained by high fidelity models, and then with a certain set of such reference points and reference values, approximation functions are established which shall represent the behavior, also covering the variation of many different parameters around these reference points. So our goal is a drastic reduction of the computational effort by these surrogate models, but at the same time they should be sufficiently accurate, and the deviation between assumed accurate results and those coming from the surrogate model shall be small. The assumed high fidelity response, which we assume to be accurate, shall be y, and the approximate response shall be only deviate from this with a small approximation error. But again, since in the development process we are varying these parameters, our design and operational parameters, this approximation shall be also valid under this variation of parameters, or it might even be that we have to update our surrogate models from time to time. Let me discuss the basic concept of the soft computing approach and establishing surrogate models. Again, we start with parameters 1 and parameters 2. Unfortunately, when explaining something with a set of parameters, by explaining it graphically, we cannot usually use more than 2 or 3 parameters because one cannot easily represent 4 parameters graphically. So let's assume we have 2 parameters describing our system behavior, the relevant response, the relevant output, and from certain sources, either from a high fidelity model or other sources, we have and can get the behavior of the system and the response of the system, assuming quite accurately. And we use these reference values to interpolate and to establish an interpolation function and polynomial function which not only covers these reference points but also covers variations of such parameters, that we can use these interpolation functions as a kind of surrogate model of our parameterized system. What also gets kind of obvious from this graph is that this process and its quality is affected by different aspects, namely the distribution of these reference points plays a role, and the number of these reference points plays a role. It's obvious that the larger the number it is of these reference points, the better the approximating polynomial would be. But on the other side, we want to limit effort to determine reference values, possibly and especially also with high fidelity models. The type of this approximation function, of this, which is shown here in a mesh shape, also plays a big role. The better this approximation function represents the real physical behavior, real technical behavior, the better this approximation function will be, and the better its validity we have also for varying parameters. What's still open is, where do these reference values come from? There are different options. As mentioned, they may come from high fidelity models, they may come from experimental data, but they may also come from educated guesses and also knowledge and insight. In development teams, one has different specialists around, and one via discussions, I will show you an example, one could also establish such surrogate models. And so on the one side, it's then once the surrogate model is established, it is a fast evaluable and can be quickly evaluated, and it's the better it represents the real behavior, the better it is also for larger variations of these parameters. But this process can be quite cumbersome if many different responses are relevant. That's one thing. But on the other thing is if we determine these reference values via high fidelity models, which we want to limit in quantity, we can still use so-called parallel processing, but because there is no requirement to determine these reference values in sequence, but they could be determined in parallel on so-called parallel processors. Let me first explain this use of multiprocessor systems or this parallel determination of these reference values of high-performance computer systems with many processors. Here we see such computer systems. On the left-hand side, we see such a collection and such a cluster of many processors, usually applied in departments, and also in some special cases, very high performance clusters might be available, where even thousands of processors are available. But that's not standard, and I will not go in more detail on this. But irrespective of this, the basic idea is the same in both types of high performance computers and multiprocessors, namely this COOT or crane parallelization can be used by implementing the high fidelity model on each of these processors, being either 50 or 500 or 5000. And these models then are run in parallel with different parameter inputs, or in other words, with different positions of our reference points in the parameter space. And so in the end, we get distributed responses or distributed reference data on many of our reference points in the parameter space simultaneously. So once we have then the surrogate model established via some interpolation through these reference points, we have this reduced or surrogate model, and we can have a kind of digital twin, as it's sometimes also called, on the run, where we are no longer relying and have to no longer rely on high performance computers. So let's jump into more details on constructing such response surface or establishing such surrogate models. First of all, we have to establish a polynomial function as a function of our design and operational parameters. And this polynomial function relationship has open parameters which we adjust to the reference values, namely these a's and these exponential data beta. And often it's assumed that these a's are 0 if they are the a sub for I not equal j, so there is no direct coupling of the parameters, but it's a simplification, but it's not a strict condition. But what's important is we have determined in advance reference values from, let's assume, high fidelity models, and these reference values are the capital R values, and this polynomial with its open parameters A and beta are now determined by a least square problem, where we want to have the polynomial to represent these reference values, assuming these to be the exact values coming from the high fidelity models, matching well with these. It's a least square problem. The number of reference values we need is about 1.5 times the number of these open parameters of the polynomial function. And be aware of, once we have determined these polynomial functions fully, namely the a's and betas, then this ansatz or this function is then an explicit function, as mentioned in the very beginning of our lecture today. So it can be quickly numerically evaluated, and it can be also for further evaluations, like for differentiation and so on, can be handled very quickly and very straightforward. In this case, we assume these betas in advance, then only the determination of the a's is left for this polynomial approximation, and this leads to the special but still relevant case of a linearly square problem for these a's. What is recommendable is that putting into these ansatz with the star on the top of this view graph engineering and physical knowledge of this behavior. So these exponents beta shall be selected such that they represent the expected behavior of the performance of the response of the system with the design and operational parameters P. So let's assume we have selected an initial set of reference points, but it might come out during this design parameterization and even optimization process that it comes out that these infill points have been not well chosen with respect to positioning and quality of these response surfaces and of these polynomials we use for interpolation. And this leads to the point of infill reference points. Namely, let's assume that we have determined an initial set of reference points, for example, by the design of experiments technique, and the numerical simulation is also still assuming the high fidelity model. We determine the behavior, the performance, the response of the system, which we then use as reference points to construct these interpolation equations and polynomials, and use these for further design and parameter studies. But let's assume we find out by different means that the validity of the surrogate model and of the used reference point is not sufficient. So we could fill in further reference points. And so this process might be repeated in order to update and improve the surrogate model. And there are different criteria for selecting such infill points, maybe different parameter changes we have carried out during the development process, different parameter variations and modifications. Maybe we have used even optimization methods and routines to vary these parameters during the development and design process. And we could use these, a selection of these as infill points, but we could also establish and use some statistical and probabilistic means to estimate where to position such infill points where we could expect the largest improvement in the approximation model or in the surrogate model, which then is improved and can be taken further for the parameter and optimization studies in the whole development process. But we have to keep in mind, once we are talking about technical systems, we have allowable parameter variations and combinations and not allowable or infeasible ones. So it would make sense that also our initial and infill points would be feasible points in the design and operational parameter space. Let's make this use of infill points, let's make this more clear by assuming a simple example with a 1D case with a single parameter which is varied and where we applying surrogate models and polynomials to approach and approximate the real behavior of the system, which we don't know explicitly, only implicitly. And we assume the real behavior as function of the single parameter giving on the x-axis, on the abscissa, to be the red curve, and if our initial reference points would be these 3 points in the center of this graph with the stars, the polynomial function, the surrogate model, would be the blue hashed line. And it's not really a good representation over the whole spectrum of the parameters. So further infill points are introduced, like the two further infill points on the right-hand side and one on the left-hand side. And you see the blue curve better approximates the red curve, which is assumed to be the real behavior. And if even further infill points are applied, then the approximating curve, this hashed blue curve, practically matches with the red curve, which is assumed to be the hypothetical one, but we don't know the explicit behavior of this accurate behavior because everything is modeled numerically via a digital model. So far we have discussed constructing these response surfaces or the surrogate models by using reference values determined initially from high fidelity models, of course, in a limited number of reference points. But this is not the only means to determine reference values and the quantities of these reference values and the reference points by high fidelity models, but one could also apply, maybe in parallel or in addition, the use of qualitative and specialist and knowledge-based engineering models and knowledge by transferring this qualitative knowledge into numerical models, which then are established also by interpolation functions and by response surfaces. To make this approach, which is a little bit different from a computational point of view, the best thing is we use an example. Namely, let's assume we want to develop a propeller plate of a propeller aircraft such that this propeller plate has best performance, can be well manufactured, doesn't cause problems in strength and in elasticity and in vibration and so forth. So the design problem would be we want to maximize and select design parameters of this propeller blade, geometry data, material data, such that it, for example, maximizes its first eigenfrequency, of course, considering the rotational speed of the propeller blade. And we want at the same time to minimize the manufacturing effort, and assuming here that manufacturing is made of this propeller blade by a braiding process for carbon fiber reinforced plastic or glass fiber reinforced plastic. So the parameters from an engineering point of view to be determined are the braiding angles and the angles of the reinforcements, resulting into also having consequences into the braiding process, and the individual thicknesses of these fiber composite materials and fiber composite layers being either glass fibers or carbon fibers. But as always, in addition to design goals on eigenfrequencies and manufacturing effort here, we always have to consider, generally in development of aerospace system, we have to consider constraints, and in this special case we have constraints of the forces acting at the propeller hub, on the deformation of the blade per se under the different loads, on its overall aeroelastic behavior, and of course on its strength and so forth. Let me, as a kind of intermediate step, briefly explain these braiding manufacturing techniques and the relationship between the geometrical design parameters and the manufacturing efforts by braiding. Here on the left-hand side we see and on the center we see such a braiding machine. It's, in principle, it's a large wheel where the different fiber rovings are brought in, and these fibers and rovings are placed in proper angles on this mandrel. And these angles, which are shown also on the very right part of this figure, are not only design parameters determining the material behavior, material properties, and with this, the structural and aeroelastic behavior of the rotor blade, but these are also determining the manufacturing effort. So, as an intermediate step, let me also assume that, which is often the case, that at the very early development stages, we do not have sufficiently accurate, if at all, simulation models to determine the manufacturing effort of such components and parts of an aerospace system. And this might be also valid for our rotor blade. But what's often around is that we have experts around which can give educated guesses for the behavior of the manufacturing effort under variation of different design parameters. So we have manufacturing efforts we are discussing with. We have the knowledge engineer, who is a guy who helps to transfer this qualitative knowledge of manufacturing effort into numerical models. And we then have the design optimization expert, which is combining then this numerical model of manufacturing effort. It's combining it with the structural and aeroelastic simulation model for the overall and multidisciplinary optimization process. So this interviewing and collecting verbal knowledge and then finally transferring it to computational and numerical models is mainly based on fuzzy logics. Namely, one asks the specialists, the experts, let's assume to be a certain parameter, one or two parameters out of our design and operational parameter set to be either small, medium or large, and then please give your assessment on which consequences does it have on manufacturing effort. Maybe we are even asking 2 or 3 or 4 different experts. And these results and these replies and are then used, which we will see, in a certain way to establish then finally response surfaces or surrogate models resulting from this qualitative knowledge and resulting from these fuzzy logics replies. And in principle, this soft computing technique could be applied and used also for rather complex system behavior. The condition is that there are some experts around who can make educated guesses. And so these experiments are presented different parameter sets, being either small, medium or large, and assuming these parameters to occur as small to a very limited probability, so the degree of membership of small parameters might be small, while large parameters, large reinforcement angles might occur quite often. So the membership of large parameters, the membership probability might then be also large. And from their reply and their assessment and educated guess on what does it mean for manufacturing effort, such response surfaces and approximation models can be also established. So this fuzzy knowledge means we have input parameters 1, 2, 3, 4, 5, geometries and thicknesses and whatsoever, and we are prescribing, assume them to be small and assume them to be larger and assume them to be medium and assume them in this and that combination. What's your guess, you as specialist, as an output in our case, the manufacturing effort, is it small, which is given here as short, or is the manufacturing effort large? And from this interviewing and from this database, maybe established from different experts, one can also construct by these fuzzy logic techniques such response surfaces where, for example, geometrical parameters are combined together and are represented by the relevant response surface, which represents the qualitative knowledge numerically about the manufacturing effort, which for simplicity is here used as a criterion for manufacturing effort, the manufacturing time of such a rotor blade. So combining these different type of models, high fidelity, low fidelity, qualitative models determined by such soft computing and interviewing experts, we are finally achieving optimization results by applying optimization algorithms and parameter modification techniques on these different models which represent our behavior. In that case, the physical performance, the mechanical performance of the rotor blade, and of this propeller blade and the related manufacturing effort. Both we want to optimize as a design goal. And since we have two different design goals, the result of optimization can only be a compromise between these two different design goals, which we see from this what's called Pareto front, this red curve, which is given over the first design goal, manufacturing effort, but the other design goal, fundamental frequency. We see if we only spend and are ready to spend smaller effort on manufacturing, we are also achieve the design, the best possible design with respect to fundamental frequency, which is about 45, 48 Hertz. If we need a higher frequency of our rotor blade, we would have to spend higher manufacturing effort. Let's say a manufacturing effort, not 0.3, but 0.6, quite as large. But at the same time, we achieve a fundamental frequency of 65, 70 Hertz. And all these optimal compromises, these compromises between these two different design goals, they lie under this red curve, which is called the Pareto front or the Pareto curve, and which helps to assess the overall design and to select proper compromises which well represent the manufacturing effort and the limit of manufacturing effort on the one side and achieving good overall physical and mechanical behavior of the rotor blade on the other side. And since the manufacturing effort has been modeled by such a surrogate model obtained by qualitative knowledge of experts via these fuzzy rule techniques, we can also identify where does higher manufacturing effort come from. Is it more in the layer 1, layer 2 or layer 3, and the results can be also seen, which very much gives a much better insight into the overall behavior and into the overall behavior of these two design goals on performance and manufacturing effort. Now let's come to our final example, but this final example also allows me to introduce a further aspect to use certain techniques to establish such reference points and reference values to properly establish surrogate models. And this example is taken from aircraft configuration tasks. How does an aircraft have to look like in its overall behavior and in its overall properties, geometrical and other type of properties, such that this aircraft is a good, if not the best aircraft to be developed under the required goals and constraints and conditions. So configuring global aircraft parameters usually means taking into account different criteria, which means in the end different disciplines. It's a multidisciplinary problem. We have to consider the aerodynamic behavior, we have to consider weight and balance and mass and so forth, the overall performance of the aircraft, the efficiency of the aircraft, if you wish so, its flight stability. This aircraft and this configuration is described and has to be described often by quite a number of parameters, global geometrical parameters and others, which we will see in a minute. And these parameters might be determined by parameter variations in order to achieve good design goals and to satisfy requirements. But once we have established related models for this, in that case four different criteria, these parameters could be in principle also determined by optimization algorithms, like also a genetic algorithm, once we have available models of these four criteria as a function of the design parameters. And these models can be and usually are also surrogate models. So such a configuration task and its parameters are given here as an example, as a parameter list. The design parameters might be wingspan, the wing area, so very global overall design parameters, wing sweep, for example, the horizontal tail area, but also fuel mass, cruising altitude, and also the arrangement of seats and of exits and all this, which the latter ones heavily determine the overall performance. And for this activity, it's recommendable not to start with a large set of parameters, but to increase the set of parameters continuously during the development process, because starting with a large set not only means one has to put in a lot of effort to establish the relationship between the performance criteria and these parameters, but also at the very beginning it might not be easy to assess the validity of the computational results, the numerical results one gets from this modeling and parameter modification and parameter optimization effort. And as I mentioned, in addition to these global geometrical parameters, we also have internal parameters within the cabin, within the aircraft, like the number of seats, the arrangement of seats, and so forth, which of course also determine the overall performance of the aircraft from an aircraft operational point of view. So we have in these 4 criteria on aerodynamics, performance, on weights and masses, and on flight dynamics, simulation models, which might be in certain circumstances high fidelity models, or might be surrogate models, or from the beginning there might be, let's say, for example, for weights, for such configurations which are kind of standard configurations where in the last 50 years a lot of experience has been accumulated and collected in statistical databases, which can be used as a kind of surrogate modeling. So from the beginning, especially in such initial configuration tasks, the simulation models often are from the beginning kind of surrogate models. For example, also aerodynamics is not necessarily from the beginning modeled via complicated computational fluid dynamics, but like a technique like a vortex lattice method, which is approximating the aerodynamic behavior in a sufficiently accuracy, but doesn't take too much effort. So we have from the beginning kind of surrogate models and surrogate models combinations, but with the different results for these different disciplines. And we have, because of this parameter variation, because of these optimization steps, on the one side, these relatively small models, but since we are investigating many parameter modifications, combinations, we have many design points to evaluate. So the result of these are large number of data. Nowadays it's called big data assessment, big data evaluation. So this allows me to bring in the idea of using techniques of big data evaluation to establish surrogate models for such types of design and configuration tasks. And these 2 different methods, genetic algorithms for optimization and data mining, now to be applied on this large database, to be applied not only to establish surrogate models, but to be applied to speed up the convergence of this genetic algorithm and optimization techniques, is done in the following. Namely, on the one side, the genetic algorithm is a design driver which modifies the design parameters. It also can handle, such genetic algorithms can handle discrete design variables, like the number of seats in the cabin. And, which is also often the case, and also with these kind of simplified models in these 4 disciplines, it can also very well use weakly structured problems. We don't have gradients of this behavior, of these responses with respect to the parameters and so forth. But on the other side, genetic algorithms usually need a large number of design point evaluations. And this large number of evaluations shall be reduced by using data mining, a technique to evaluate large data sets. And data mining helps to identify relationships and associations between the different parameter sets, namely especially those which lead to better design parameters, which helps then to select favorable modifications, favorable mutations of the design parameters in this genetic algorithm. And we see here the consequence when using such data mining techniques. Namely, the blue curve is data mining switched off. We see here the genetic algorithm needs 40, 50, 60, 80 generations to achieve, if not more, to achieve the optimal results. And each generation might have 10, 20 or so different number of populations. So it means a lot of evaluation of data positions of the parameters in our design space. Not so much the effort per evaluation, but the large number of evaluations. But once the data mining is also used to improve this mutation, this very modification of the genetic algorithm which modifies the design parameters. Once we use these data mining techniques, you see here on the curve with the black dots that we achieve practically after 15, at most 20 generations, we achieve the optimal result. So a typical configuration task with these many design parameters on the one side and criteria on the other side might be the following configuration task. We might have to determine this design parameter such that on the one side fuel consumption is small and on the other side also the block time is small. Under block time we understand the time between undocking from the docking device at the starting airport and docking to the docking device at the airport we are finally flying to. And as always, these parameters not only have to lead to good such design goals, and good compromises between these, but they also have to satisfy certain constraints such that they do not lead to unreasonable design parameter ranges or even satisfy constraints which makes it flight behavior unstable. And the typical result from such activity is then shown here. Again, since we have two design goals, it's again a Pareto optimal curve, where on the x-axis the optimal and minimum possible fuel consumption is shown, on the y-axis the optimal and minimum block time is shown. So if we are requiring that we have minimum and small fuel consumption, we see that we have to select something between 20 and 30, whatever it is, tons, for example, on fuel. But this also means that this results into configuration which might lead a higher block time, because then the overall aerodynamic behavior is, the overall configuration is such that the passengers take more time to go into the aircraft and to leave the aircraft. So it also influences the block time. But if we are reducing and want to reduce the block time, we have to spend more on fuel consumption. And in that case, we are reducing block time, which we see on the more right-hand side of this Pareto curve. We see that the length of the wingspan is smaller. This smaller wingspan allows to operate more quickly, more fast on the airport, which reduces the block time. But at the same time, aerodynamic performance is not as good, so fuel consumption might be higher. And this shows that we have to select the proper compromises and to finally select a configuration we are happy with and which we find as a combination of these design goals to be a very good and optimal compromise. So let's conclude. First of all, we have to be aware, and might not have been always obvious during our discussion, that there is some preparation work to establish surrogate models, like determining the reference values at the reference points, like determine and transferring the qualitative knowledge to quantitative models via knowledge-based engineering and so forth. Then once these surrogate or reduced models as functions of the design parameters in the design parameter space are available, the evaluation can be done very fast, independent, if you wish so, on large computers. And we can also handle by this multidisciplinary tasks. We have also seen that establishing such models, and for establishing such models, different methods can be applied, like those first establishing reference data with high fidelity models, like those establishing reference data by knowledge-based engineering and by transferring qualitative knowledge into quantitative models and so forth. And we have also seen that different elements of such techniques can be favorably combined, namely in the example of combining the genetic algorithm with data mining techniques. The convergence speed of genetic algorithms can be significantly improved and enhanced by using data mining techniques to improve the mutation part, the mutation step in such genetic algorithms. But I want to make you also aware that once these models are established, the quality of these models has to be validated somehow by plausibility checks, by cross-checking with high fidelity models, by checking with experimental results once flight tests are done, and also by feedback from the operational behavior of this aerospace system. But taking all this together, we can expect that these soft computing techniques and this use of big data techniques like data mining, this use and application will be even grow in the future in order to cover a broad scope of multidisciplinary, multi-criteria design and development problems in aerospace based on simulation. Okay, this view graph shows you a rough selection of literature. There's a vast amount of literature available on these subjects, but this is a selection out of these. Some of these data and literature and papers are written by our doctoral students, maybe with participation of myself. And that's one thing. And what's also very important to note and to mention is that for these aspects we have discussed, also software, at least in its basic format, is available. For example, in MATLAB, where one can see and find something on surrogate modeling, where one can find something on data mining, where one can find them on genetic and other type of optimization algorithms and so forth. So you don't have to start from scratch for using such methods and technique. And as last but not least, I want to thank you for participation in this lecture and participating in this presentation. Thank you very much.